and welcome to my course, Introduction to Computer Networks for Non-Techies. I'm glad that you signed up and I'm happy that you're here because number one, I know that you have lots of different options out there on the internet that are available for you when it comes to learning computer networking. And number two, I know that I have a lot of information that's going to be value added to you both in your personal life and your professional life. So I'm glad to have you here. Now let's go ahead and let's spend a couple of minutes and let's go over the course curriculum. So what am I going to teach you, and more importantly, what are you going to get out of it? Well, the first thing we're going to talk about is we're going to do an overview and benefits of computer networks. So we're going to talk about what computer networks are, some basic ground rules for computers and how they communicate, and more importantly, why we use computer networks and how they benefit us both in our personal lives and in our professional lives as well. Then after that, in section 2, we're going to talk about the specifics of how computers work. So I'm going to do a broad overview of many different topics to give you a broad overview of how computer networks work. And this is really that 100,000 foot view. And then we're going to drop down into a lower view and get into more detail in later sections of the course. So after that, in section 3, we're going to talk about network topologies. So what do I mean by network topologies? Well, I mean logical topologies and physical topologies. Now that may not make a lot of sense right now, but it will as we go through the course. After that, in section 4, we're going to talk about the most common networking devices that you're going to be seeing and utilizing both in your own personal networks and also if you work in the IT sector or if you're a business professional and you are looking to get into IT. These are all devices that you're going to see on that side as well within your organizations that you work for. So we're going to talk about lots of different devices there. And then in section 5, we're going to talk about network cabling. So we have to talk about the cabling. We can't omit it. It's just as important as the devices. And so that's what we're going to cover in section 5. In section 6, we're going to cover something called the OSI model. And this is a framework that tells us and teaches us how information travels across the network. In section 7, we're going to talk about the process of planning a network design. So before you design a network, before you build a network, the first thing that you need to do is you need to plan. And that's what we're going to talk about in section 7. In section 8, we're going to do an introduction to the concept of the TCP/IP. And then in sections 9 all the way down through sections 12, we're going to talk about the different types of TCP/IP protocols and how they align with computer networking ports. And then in section 13 and 14, we're going to talk about IP addressing and subnetting. And then in sections 15, we're going to go ahead and close out the course and we're going to talk about the process of designing a network. And that's everything we're going to cover in this course. As of right now, a total of 94 lectures and 7 hours of material. So like I said, this is an introduction to computer networking course for non-techies. That's why we're covering so many different topics and so many overarching topics. So I hope that you get a lot out of this course. And if you have any questions throughout this course, please feel free to ask me questions on the course discussion board. So thanks for watching, and we'll see you at the next lecture. So who am I and why should you take this course from me? Well, I've been working in IT for over a decade and I've had a lot of different jobs and I've moved up the ranks throughout the years. I started at the lowest level at help desk and desktop support, and I've worked my way up through all sorts of different roles and activities from network support and systems administration and web development to where I am today in cybersecurity and IT governance. Now, I also have experience teaching this information. I actually took this course and molded it from a course that I taught as an adjunct professor at CSU San Bernardino to undergrad students. So this is actually a course that was taught at the academia level. And so I have all this experience, and plus I have a wealth of knowledge from my education. I have an MBA with a concentration in information assurance and security management, which is just a fancy way to say cybersecurity management. And I also have a Master of Science in Information Technology Network Management. And then in addition to all that, I have several different industry certifications for the IT sector. So I have a lot of wealth and knowledge that I can bring to this course, and that's my goal, is to take all of my experiences, all of my education, and roll that up into this course, which I think that you're going to find very valuable. We're going to kick off our course on computer networks by asking a very simple question. What is a network? Well, it's nothing more than two computers connected together by a single cable. And so what's the point of this? Well, in its simplest form, when we connect two computers together, the goal is to get them to share resources, whether it's sharing files or them communicating back and forth, or maybe them even printing from one device to the other if the other one's a printer. And that's really all that a computer network is at its very simplest form. Two devices connected together, shared by a cable. So now let's talk about it a bit further. Now, when we're talking about a computer network at its most basic level, there are two main aspects. And the first aspect is the physical connection, and the second aspect is a logical connection. So let's talk about the physical connection first. That's simply the wires and the cables and the wireless media. So in this example, if we're connected with a network cable, then we're talking about the wires, and we're talking about the network interfaces cards on the back of each device, and that's it. If we're talking about Wi-Fi, then we're talking about the wireless interface cards on the back of each computer and the wireless signals that are transmitting over the air back and forth. So now let's talk about the logical connection. What's the logical aspect? Well, when we talk about the logical aspect, when we're talking about computer networks, we're talking about the data that is being transported back and forth across this medium from one computer to the other. And so when you think about a computer network at its very simplest form, it's really nothing more than this. So now let's go ahead and let's take a look at a couple examples. And now for those of you that are new to computer networks, the easiest way to think about a computer network is either your home network or a small office network, maybe like a dentist's office, or maybe if you have your own small business, your own small business office. And typically what we're used to seeing is what's called a SOHO network, and SOHO stands for Small Office and Home Office Network. And what that is, that's really that device that you have connected up to your modem or your DSL router. That's that all-in-one small office and home office device, and we'll talk about that a bit more in the course. But here's a picture that kind of just shows you what we're talking about here. So this would be a typical home network or a typical small office network. We have an internet connection, we have our DSL connection, or maybe you have a cable connection. And then we have at the border, we have our wireless firewall router or modem where it's connected up through the wall into your office or your home. And in there we have what's called a switch, but in many times the switch is connected within this and it's all one big device. And then either wirelessly or wired, we're connected to some devices at home. Now, I only put this in the most simplest form with maybe you have a desktop or a couple desktops, you have a wireless connected laptop, and you have a network printer. But of course, you know, if we're thinking about even small offices like a dentist's office or your home, everybody's going to have their smart devices connected as well. They're going to have their tablets, their iPads, and their smartphones connected to the network as well. And even if you have a smart house with smart devices, you can even hook up, you can hook up your cable, you can hook up your appliances, you can hook up your home security system. So lots of different devices can be hooked up. But typically this is what we're used to seeing at a very small scale. And let's take a look at one more example just to end this lecture. So here's another example, and more so, this is based upon a small office type of a design. We have our internet connection, and we have a T1 line dedicated for this small office. They have a router on the end, and don't worry if you don't know what any of this stuff is. We're going to talk about what each device does. So if you don't know what a router is, that's okay. If you don't know what a firewall, that's okay. It's kind of expected that you don't, but I'm just charting to help you visualize how everything is connected, and then as we go through the course, it's all going to make sense. So getting back to the diagram, we have our router connected to our firewall, then we have a switch that everything connects to, and then we have a file server where maybe we share files. We have an authentication server where everybody has to authenticate to log into the network, and then we have our workstations, and we have a printer. And this is typically what you're going to see with a small office network. And again, SOHO stands for Small Office, Home Office Network, and typically that's what you're going to see. And if you take anything away from this course and you decide to try to hook up your own network, this is the type of network you're probably going to be able to set up yourself, and you're going to feel confident enough to do yourself. So that's going to go ahead and conclude our first lecture. The main key takeaway before we end this is, remember, a network is nothing more than two computers connected together by a cable to share resources at its very simplest form, and we're just going to build upon that foundation to build upon our understanding of computer networks as we move on in this course. So now that you know what a computer network is at its most fundamental level, let's talk about some basic networking rules for communication. And so what are networking rules for communications? Well, we call those communication protocols. And so computer networks have to follow communication protocols to be able to send and receive data properly and effectively, and for it to go through uncorrupted. Now, let's think about a good example. And a really good example is talking to somebody on the phone. So there are protocols, there are steps that you have to follow to call somebody and to have a successful talk on the phone call. So let's think about the steps. Well, the first thing is you have to know their number or their contact information to call them on your cell phone. If you don't know that, then your communication is going to fail. You can't talk to them. So you know their information, you dial their number. The next step is they have to hear the phone ringing and they have to pick it up and they have to respond. So if they don't hear it ringing, or if they pick it up and they don't respond, then again, your communication is going to fail. And then if they do respond and you don't respond, maybe there's something wrong with your mic, or you are just distracted and you don't answer when they talk back to you, then again, the communication is going to fail. So, we take this for granted. It's a super simple example, but it just shows how many steps are involved in just simply picking up the phone and calling somebody and having a conversation. So now let's get back to computer networks. So one simple rule, which is a general rule, and there are exceptions to it, one simple rule in communications between computers and computer networks is that when we are sending data from one computer to the other, it must be delivered uncorrupted. And if it is corrupted, then in many instances, it's going to be useless. However, there are exceptions to the rules, and just remember that there are, but for the most part, the data needs to come through uncorrupted. So think about an example where somebody tries to send you a picture over Gmail and they attach it and it comes through and it's all jarbled or you can't open it. Well, if it's uncorrupted, if it is corrupted, then it's useless. But if they send it through and it's uncorrupted, then you can open up and you can view the picture. So let's talk about this a bit more. So computers in a network must be capable of determining the origin and destination of a piece of information. And we did our example of doing a phone call. So when you're trying to call somebody on the other end, you have to know their destination number. So you have to know the phone number of the person you're trying to call. And again, if somebody's trying to talk to you, they have to know who was calling them so they could call them back. And so it's synonymous when we're talking about the computer world where we have one computer on one side of the communication, one computer on the other side. One's going to be the origin, one's going to be the destination where they're sending information back and forth. And it's the same thing for calling people back and forth. You have to know who to call and who you're talking to. Now, when we are talking about computer networks, we do use some special names, and those names are called IP addresses and MAC addresses. Now, I'm not going to get into the details of what those actually mean, but I just want you to remember that we'll be talking about them in the future, and I want you to have a basic understanding that there are communication protocols in place, and it's really going to come to light as we go through the course. And just remember the terms communication protocols and IP and MAC addresses, and you'll be good to go as we move on through the course. So we need to pose the question, why build a computer network? Why do you need a computer network? Why do we build them now, and why are we so reliant upon them? Well, to answer that question, we need only to look at the past before we had computer networks available to us. So before we had computer networks available, everything was sent by hand or by the postal service. In the office, if you had a file that needed to be sent up to a different department, you had to go through your mailing department and have somebody send it, or you had to send it yourself. If the utility company needed to send a bill to you, they had to send it through the postal service, and you had to write a check and send it back to them through the postal service. So everything was sent via hand and manually or through the postal service. And in general, this is a really slow process, and it can be very unreliable because lots of times information is lost when it exchanges a lot of hands, and especially through the postal service. Now, one of the great things of having a computer network is that it mitigates a lot of those risks that we had in the past. So computer networks enable a much faster mode of communication and a much more efficient mode of communication. And let's think about some really simple examples. So instead of using the postal service or delivering information by hand, we can simply email somebody now. And we know that it's going to get there a majority of the time. When's the last time that you had an email that didn't go through or an email that was lost? Probably never. And so let's think about other modes of communication. We have video conferencing as well, where you can have a webcam set up in your conference room and you can attend a conference by not even being in that conference room. You can log in with your laptop and have your webcam set up with your mic, and you can be there in that meeting just like you were there in person, when in fact you could be at home in your pajamas. Now, another thing that computer networks do is that they encourage the use of standard policies and procedures. And so if you think about our previous lecture where we talked about communication protocols, is that when we are thinking about computer networks, for them to be able to communicate effectively and properly, they have to follow standard policies and procedures. And because they have to do that, and there's no way to get around it, like for example, if you wanted to have a document sent up from one department to the next, and you wanted to streamline it, and maybe you paid the mail guy an extra $5 to streamline that process, well, you can't do that with a computer network. You have to follow the policies and procedures, otherwise it's not going to work. So that allows it to be much more efficient, and in general, when we have everybody using standard policies and procedures, it speeds up the process. Another great thing about having computer networks in place is that we can have modes of backup and recovery set up where our data is set up and backed up on a regular basis. And we call this redundancy in the IT world. Now, for example, when's the last time that you've had a file lost on your computer and you wish that you could back it up, or you wish that you could restore it? Probably everybody. Now, if you're at work and you lost some files, you could simply call up your IT guy and say, hey, did you back this data up? If so, can you please restore it? And me going from the realm, starting at the bottom, doing help desk and desktop support, I've done that many times. And so that's really a huge benefit of having a computer network in place. When's the last time where you said something over the postal service and you said, hey, you lost my mail, I need you to find it? When's the last time they actually found it? They never find it, because when it's lost, it's gone. And this really all leads up to one major point, is that computer networks lead to cost savings. And this is just a huge benefit. When we have faster communications, we have more efficient modes of communications where we're using standard policies and procedures, and our data is backed up on a regular basis and it's set up in a redundant manner. We have cost savings in the long run. And so these are all the different reasons why we build out a network and why we use networks today. In this lecture, I want to take a few minutes to talk about how networks impact our daily life. And they really impact every single aspect of our lives. And even if you haven't thought about it and you haven't really considered it, they really do, and they've really infiltrated every single aspect of our lives. And in certain instances, this can be a benefit. In other instances, it can be a hindrance, and it can also be a risk. And so let's talk about how networks impact our lives. And when we're thinking about networks, we're talking about very quick, instantaneous communication, because we're always connected to the internet, and most certainly today, almost everybody is connected to the internet 24/7 with their smartphones or their laptops or their tablets. And so really, we're never disconnected. We're always on the grid. And if you think about it, here's a simple image here that shows you how, we are impacted on daily life. We do our banking online now. When 15, 20 years ago, we had to go into a brick and mortar bank and do our banking there. We had to go use an ATM. Now, one of my bank accounts is online only. There's not even a brick and mortar bank that I can go to. We can see the news anywhere in the world. We can simply pull up our smartphone or our tablet or a laptop, and we can go to any website on the world and we can look at the local news there. Same thing for the weather forecast. We can check out the weather anywhere in the world. I'm in California. Maybe I want to check out the weather in Hong Kong, or if I want to check it out in Maui, I can simply get on my phone or any other connected device and find that out. And then traffic conditions. You can go ahead and pull up a webcam and see what the traffic conditions, if they have webcams in your area, or you can use Google Maps, or you can just go ahead and turn on your cable and go to the local news. I mean, it's all available right there for you. So let's talk a bit more how networks have impacted our lives. And let's think about the internet. We have wikis, we have instant messaging, we have blogs, we have podcasting, we have all sorts of social media collaboration tools and websites on the internet. It's all out there. It really has changed the way that we live. And if you think about the generations, if you think about your generation, what did you grow up doing? Were you on Facebook? Were you on MySpace? Were you on Twitter? Were you on Pinterest? Or were you outside, playing with your friends because you didn't have any of that? Maybe you had G.I. Joes and Barbies, and you had a typewriter, or you had an Atari or an original Nintendo. Now, everything's changed today, and the way that we communicate and the way that we play and the way that we live has really changed. And let's think about our work life. I work from home several days a week, and having really robust computer networks in place allows me to sit at my desk in my home office and to really feel like I am actually in the office because I have a webcam. My coworkers have a webcam. We have instant chatting features. We have phones that are actually built into our laptops where we can talk to each other with never having to even leave the laptop. It's all right there. It's all integrated, and it really affects everything. Let's talk about our school lives. My second master's degree was from an online-only school, Western Governors University. I did my thesis defense via a webcam and a video conferencing interface from my bedroom at home. I didn't have to fly out to the university. I didn't have to do any of that. All I had to do was turn on my laptop, install some software, put on a headset with a mic, and do my defense there. And it really has changed. I mean, it's amazing how it changes everything in our lives. And if you take another example here, I mean, this just reiterates everything we talked about. It really has impacted every single aspect of our lives, and even on airports now. I mean, in airlines and in airports, you can be flying at 20,000 feet and you can be on the internet now, where 10 or 15 years ago, that wasn't even a consideration or a possibility. Everything, it really has impacted every single aspect of what we do. And so I want to end this lecture with a quick question to you, and this really leads to a student exercise, and it's a class discussion. So this being an online course, I know we can't have an in-class discussion, so this is a bit of homework for you, and the question that I'm going to ask you is I'd like for you to take that and post an answer on the discussion board. So the question is, how has a computer network, or how have computer networks impacted your life, both your personal life and your professional careers? And think about how the tasks have changed. So think about, if you were born in an era before computer networks were available, think about how your life has changed. And think about what computer networks and the internet has allowed you to accomplish much more efficiently at work and at home than if it was down or wasn't available. And think about how your life would change and how your work and everything would change if the internet and computer networks completely disappeared. So just think about these and just, go to the discussion board when you have time and just post a general answer talking about how the impacts are and how they allow you to accomplish a lot more things. And if the internet disappeared, how that would drastically change your life. So thanks for watching, and we'll see you at the next lecture. So we're going to continue our discussion of the benefits of having a computer network in place. I know that we talked about this a bit in our previous lectures, but I want to continue this discussion, and I'm going to talk about some more tangible benefits in regards to from an IT perspective and a business perspective. So prior to having computer networks in place, there were computers, and before we had networks in place, computers could not communicate and transfer data from one to the other. And so when you did that, when you had to transfer data from one device to the other, you had to transport that on a floppy drive. And so you remember the days, for those of you that are older like me, you'll remember the days when we had to take our data, we had to put a floppy drive in, and it really didn't hold much data at all. We had to copy that information onto the floppy, take it to the other device, and copy that onto its hard drive. And so that was time consuming, and it was slow, and it was labor intensive. And we can even go back further. They even had punch card coding. So my dad tells me stories back when he was in college where they were doing coding and they were doing programming, and they were doing it on punch cards and putting it into the mainframe. So it was much slower than it is today and was very labor intensive. So now let's talk about the benefits of networking. Well, the first thing is centralized file management benefits. And if you think about this from an IT perspective, we can have a centralized file server in place for our organization, for our business, that stores all of our data, and it's available to everybody whenever we need them to have it. In the past, without a network, this would not even be a possibility. And when we have this in place and we have a network in place, we have shared resource capabilities. So we can easily share information on this file server from one person to the other, or even if we have somebody on their client desktop and they need to share information, they can share that to somebody else on the network. Now, another great thing about having a network in place is that we can have centralized security and configuration management set up. And so for those of you that are new to IT, you'll understand this from the perspective where you go to work and you log in. you have to set up the first day, you have to set up a username, or the IT department sets up a username and they establish the password, and you have to use that username and password to log into the computer. And you may not be able to log in before 8 a.m. and you may not be able to log in after 5 p.m. And they also may set restrictions on what you can access and what you can't access. And so from that perspective, we have centralized security and configuration management in place. And then also the concept of just having increased speed. So taking this perspective where we didn't have networks in place where we had to manually transfer data from one computer to the other, or we had to actually take information and print it off on the printer and hand it to the other person. Comparing that to when we have computer networks in place now, we have greatly increased speeds. And if you think about it, and really think about it from the perspective of an organization, if you think about all this, central file management benefits, shared resource capabilities, centralized security and configuration management benefits, and increased speeds, well, what does this lead to for an organization and a business? Well, number one, we're going to have greater productivity overall because we're much more efficient. And because things happen faster and we're using less resources and we're much more efficient overall, we're going to have cost savings. And so, the end goal, if you're thinking about it from the perspective of a business, we have greater productivity and we have cost savings. And so that concludes our lecture on the benefits of networking. In our previous section of the course, I did introduce you to the concept of network communication protocols, but in this lecture, we're going to take a deeper dive and we're going to talk about it a bit more. So let's go ahead and let's get started. So remember, when we talk about protocols in general, they are rules for communication. And when we are talking about computers communicating with one another, they have to follow what we call communication protocols. And so really, when we're talking about communication protocols, it's rules that govern how a computer can communicate with another to be able to send data back and forth. And if they don't follow these rules, then they're not going to be able to communicate because there's going to be errors that happen across the way. And we did some real life examples, and a real life example would be calling somebody on your phone. And that's a really easy way to really bring this to light and show it in a non-IT manner. Now, another one is driving your car. So just like calling on the phone, there's certain rules you have to follow. And when you're driving your car, there's rules of the road. You have to obey the speed limit. You have to put your blinker on when you switch lanes. And if you don't, then there's consequences. You can get a speeding ticket. You can get a ticket for driving improperly, or potentially you could even get in an accident. So, when we are thinking about communication protocols, or if we're thinking about protocols in general, just remember that those are rules and we have to follow those rules. So let's talk about these protocols in a bit more detail. Let's revisit our physical protocols and our logical protocols. So what is a physical protocol? Well, it's just like the name implies, it's the actual physical portion of the network. And so when we're thinking about a network at its most simplest form, where we have two computers connected by one medium, one cable. Well, that actual cable with its connectors on the end and the network interfaces that it plugs into, that's the physical protocols right there. And even the electrical signals that are going back and forth from one computer to the next, that's part of the physical protocol. Now, on the flip side, we have our logical protocols. So the logical protocols is really how software controls how the data is sent and received, and really how it's interpreted. So we have our machine code and we have all of our other programming languages in place where the software interprets that actual physical signal going back and forth, and it interprets it as a logical protocol. Now, it's okay if you really don't understand this and it doesn't make that much sense. It's going to make a lot more sense as we go through the course. So in computer networks, there's all sorts of different protocols. Physical protocols and logical protocols are just really higher categories of protocols, but there is one suite of protocols really that is the bedrock of communications on many networks today, and that's called the TCP/IP suite of protocols. And we're going to be talking about that in detail later in the course. But I did decide to give you some examples just to introduce it to you here in this lecture. I just decided to give you some of the more popular ones. So when we communicate over the internet with our web browsers, we use HTTP, and you see that every single day when you go ahead and you type in something like as simple as google.com, you'll see http://www.google.com. Now for email, if you have an email client like Outlook, and you set it up, you'll be familiar with POP3, SMTP, and IMAP. These are the standard protocols that govern how we can send emails across internets and networks. And then lastly, FTPs is a really familiar and really commonly used networking protocol in the TCP/IP suite. So if you've ever uploaded anything to the internet, you may have done it with the FTP protocol. And so those are some of the more popular and more common protocols in the TCP/IP suite, but don't feel like you have to understand them now because we're going to talk about them in a great level of detail later in the course. I just wanted to introduce them to you here in this lecture. So if you have any questions about networking protocols and communication protocols and physical protocols and logical protocols, please feel free to let me know with a question on the discussion board. If not, thanks for watching, and we'll see you at the next lecture. In today's lecture, we're going to talk about something called the OSI model, and the OSI model stands for the Open Systems Interconnection Reference Model. Now, what's interesting about this is that this is a model that we use as a conceptual framework, and it's designed to show us how networks work and how data moves across the network, but it was never implemented. So the interesting thing about this is that it was developed to guide us through how a network operates, but it wasn't implemented. In fact, another model was implemented, and that model is the TCP/IP model. And we introduced some of the protocols in that suite. So, getting back to the history of networks, a long time ago, people were competing to develop a model to build networks off of. And one group developed the TCP/IP, another developed the OSI model, and when it all came down to it, they decided to go with the TCP/IP model. However, we do use OSI model because it is a great framework to really show how networks operate at a very high level. And so we use it to teach people, we use it to reference how we're going to design networks, and we also use it to troubleshoot networks when we're having issues. So let's go ahead and let's take a deeper look at it. So what it does is it breaks down the communication process across a network where you're communicating from one computer to some other device on the network into 7 different distinct layers. And what it's composed of are upper layers and lower layers. And the upper layers are considered what we call the host layers. And the bottom layers on the flip side are what we consider the media layers. So what's interesting about this is that when we're talking about host layers and media layers, we are talking about the host computers. And when the media, this gets back to, remember we were talking about physical connections and physical protocols, we're talking about the media. Well, when we're talking about the lower layers, we're talking about the network operations. And so let me go ahead and get my drawing tool out so I can go ahead and mark this up a bit to help it make a little bit more sense. So when we're talking about the network portion, what we're really talking about are the network-centric functions like routing, addressing, and flow control. So things like that, things that operate within the network. When we're talking about the host layers, we're talking about stuff that actually goes on in the computer itself. So we're talking about the application programs where they're interacting with the network. We're talking about setting up the encryption in the software, and we're talking about data formatting. So for example, when you open up your internet browser and a bunch of data comes over the network into your computer, your internet browser is going to take that HTML and all that other stuff and output it in a manner that you can understand. So let's go ahead and see what it looks like. And like I said, it's composed of those different layers. And when we're talking about those different layers, we have our host layers at the top, we have our media layers at the bottom. So this is what's taking place at the network down at the bottom, and this takes place at your computer. Now, I don't want you to get worried about the details in this lecture because we're going to spend a lot more time talking about the OSI model. So this is just going to be your introduction. So I'm just going to briefly go over what the layers are, but we're not going to get into all the details. We'll do that later on in a later lecture. So when we're looking at this, what happens is that data starts and what it does is that it adds on layers of information. And at the top, it's nothing but raw data where it interacts with an application. And then once it goes down the layers, this data is then segmented and created into what we call segments, packets, frames, and bits. And by the time it goes all the way down from the application to the actual network cable, then it's broken up into actual bits of data. But at that point in time, there's all sorts of information added on. And for example, if we need to encrypt it, then the encryption's added on. If we need to set up a communication, the communication's set up. If we need the communication to be reliable, we can have different protocols that are reliable or unreliable, then we can set that up as well. And then of course we need to know where it's going, so we have our destination address and our source address. So we have our IP addresses and our MAC addresses. And then once it gets down to here, it's really the physical communication. We send it out across the network. And that's really how it works. Now, when a computer receives it, instead of going down, it has to go up. So when it's receiving it, it's going to go all the way up, and it's going to go into this application, and then it's pretty much going to do the exact opposite process of going back down. And this is going to make a bit more sense. I'm going to go ahead and show you a representation on the next screen. But before we get to that, there is one thing that we can use. A lot of people like to come up with different phrases to understand and remember this. And a really easy one here is, please do not throw sausage pizza away. And what you'll notice is that the first letter aligns with the first letter of all these. So for those of you that want to get into networking and you want to take the certifications such as the CCNA or the CCNT or the Network Plus, you're going to have to understand and memorize OSI model. And so having these little phrases here is going to be an easy way for you to memorize that. So please goes with physical, do goes with data, not goes with network, throw goes with transport, sausage goes with session, pizza goes with presentation, and lastly, away goes with application. So if you remember little phrases like this, like please do not throw sausage pizza away, or programmers do not throw sausage pizza away, it's a really good way to memorize these layers because there are 7 of them to memorize. So now let's go ahead and jump to the next slide. And this is really going to visualize this whole process that we were talking about. If person A over here, and we'll just say A, wants to communicate with the file server and he wants to send a file and save it onto there, then everything starts here where he types it in. Everything starts here where he's typing it in on his computer. And then when he saves it and he chooses the file folder that's on the file server and he says, I want to save it there, it has to go down all these different steps here from step 7 all the way down to 1 to make that data prepared to go across the network. Now again, we're not going to talk about what all these different things do here. We're going to talk about that in separate lectures, so don't worry about all this detailed information, but just understand that it has to go down. And really what happens is it goes down, it goes all the way down, and this here is the network cabling, goes across the cabling and all the way across the cabling to the file server and back up that stack and into here. And when I'm talking about stack, I'm talking about all these different layers in the OSI model. Now, like I said, this is a conceptual framework and it was never fully implemented. However, it is really close to the TCP/IP. So when we talk about the TCP/IP model, it's going to make a lot more sense because the layers are going to coincide. Not everything is going to be 100%, but it's going to be close enough so we can understand what's going on. So let's go ahead and jump to the next slide. And this is going to be the last slide for this lecture, and we're going to just quickly talk about some of the benefits that we get from using the OSI model. And so let's think about it. It's a reference model. We never fully implemented it. We use it as a guide when we're designing networks. We use it as a guide to teach people like I am to you. And we use this as a guide for when we are troubleshooting networks. So what are the benefits? Well, the first one is that it reduces complexity. If we're breaking down the way that a communication works and how we understand it across the network, then it makes a lot more sense when we break it up into 7 discrete layers versus if we have no layers at all and we're trying to explain it. So when we break up the communications into smaller parts, it's easy for us to understand. Now another thing is that it standardizes our interfaces and it standardizes the way that different components are going to communicate from one device to another. So when you have multiple different vendors creating different applications, different devices and so forth to communicate across the network, you need a model. And this model helps standardize the way that they understand how they can communicate, simply because this is so close to the TCP/IP model. Another thing too, because since we allow this standardization, then we also allow for the ability to have modular engineering. So what do I mean? Pretty much think about plug and play. So if you think about the PC world, if you've ever built a computer, you can get a motherboard from one vendor, you can get a CPU from another one, you can get a hard drive from another one, you can get a memory from another one, and so forth and so forth. And so when we talk about modular engineering, it means that we can have all these different vendors making all these different devices communicating together. So you can buy your router from one vendor, you can buy your switch from another vendor, you can buy your network cabling from another. If they're all following the same standard and the same rules for communication, then we can have modular engineering. And that leads us to the next point. Because we have that, then it allows for interoperability between these different types of technologies and these different vendors. And that leads us down to our final point. When we bring all this together, we have a reduction in complexity, we have more standardized interfaces, we have modular engineering, and we have interoperability between different technologies and vendors. Overall, it really accelerates the evolution of the networking world and the IT world. And so for those of you that are familiar with Moore's Law, this will make a lot of sense because, the way that the IT world and the way that the computer industry and everything in regards to technology, the way that it has evolved over time is just amazing, and it's much faster than anybody could have guessed. And when we're using models like this, it really accelerates evolution because you can have a lot more updates, you're going to have a lot more improvements across these different vendors working separately and working together, and so it just really improves it all. So anyways, that's going to go ahead and conclude our lecture on the OSI model. Like I said, I just want you to have an understanding of what it is, why we use it, and a brief understanding of how it operates in this lecture. You don't need to worry about memorizing all the different names of the layers or what they do at this point in time. I just want you to be familiar with it. We'll get into those details in another lecture. So thanks for watching, and we'll see you at the next lecture. So now that we talked about the OSI model, we need to talk about the TCP/IP model. So what we're going to do in today's lecture is we're going to do an introduction to the TCP/IP model. Again, just like the OSI model, I don't expect you to memorize everything I'm talking about here in this lecture, so remember, this is just an introduction to the TCP/IP model. So let's go ahead and let's talk about it. So remember, the OSI model is a conceptual framework and it was never implemented. However, on the flip side, the TCP/IP model was. And so if we're thinking about, we're talking about the internet and networks today, this is the most common used protocol suite in the networking world. And it's really the protocol suite that the internet was built upon. So when you're out there connecting to a network at your work or you're at school and you're connecting to the internet, you are on a TCP/IP network. And so it is the standard today for computer networking. And pretty much everything is on a TCP/IP network for the most part. And it is very similar to the OSI model, and it's a 4-layer model instead of a 7-layer model, but you'll see the difference on the next slide when I talk about them. Now, in regards to the name, it's based upon 2 major protocols. There's the TCP protocol and the IP protocol, and we'll talk about those in the future, so don't worry about it. Just understand that that's how it was named. So let's go ahead and jump to the next slide. So let's take a look at these 2 different suites side by side. So we have the OSI model right here, and we have our TCP/IP model on the other side. And what you'll notice is that we have the application layer, the presentation layer, and the session layer side by side. Now on the flip side, we only have the application layer. Same thing goes for down here. We have the network interface layer, but we have the data link and the physical layer. And so let me draw a line here as well. And so what they did is, all they pretty much did, and I'll put a line up here to show the difference, is that instead of naming these 3 layers that work at the host layer, they decided to bundle them together and call the application layer when they implemented it with the TCP/IP. These 2 layers are the same. So our transport layer is the same as our host-to-host transport layer here. Our network layer is the same as our internet layer. And down here at the bottom again, they combined the data link and the physical layer on the OSI and just called it the network interface layer. So if we think about it, all the different things that we're going to talk about down here when we talk about the OSI model, it's going to align to this one layer right here. It's going to align to the network interface layer. And then same thing when we talk about the OSI model and we talk about these 3 top layers, it's going to align with this layer. And then whenever we talk about these 2, they're going to have their own separate layers at the TCP/IP model suite. So that's the difference, and that's how they align. It's really not that big of a difference between the 2. It's just that they bundled certain layers together in the OSI model and they implemented it as a TCP/IP. Now, we talked about the TCP/IP being a protocol suite, and that's really what it is. And so when networks communicate, they use protocols to communicate. And so we have these communication protocols, and they all act at different layers because they have different roles in communication. And so what we're going to talk about in this course is, in different lectures, we're going to talk about some of these more important and more common protocols. And for example, some of the ones that we already talked about, we talked about FTP a little bit. We talked about HTTP, and that's up here as well. So we talked about HTTP. We talked about some of our mail protocols. Again, those are up here as well. We didn't really talk about any of these. Now, these are the ones that are really taking place on the network, down here at the bottom. All this stuff up here takes place on your computer, interacts with applications, and then they interact with the network down here. So that's our really quick introduction to the TCP/IP model, suite of protocols. So we talked about what it was, and we talked about how it relates to the OSI model, and I gave you a brief overview of the different protocols in the suite. So again, you don't have to memorize all this. I just want you to understand what it is, how it differs from the OSI model, and how it has a bunch of protocols that interact on the network at different layers in the TCP/IP model. So again, we're going to talk about the TCP/IP model and the different protocols in detail in future lectures, just like we are with the OSI. So just stay tuned for that later in the course. Don't worry about memorizing it now. So thanks for watching, and we'll see you at the next lecture. In today's lecture, we're going to talk about MAC addresses, but before we talk about MAC addresses, I want to do a quick overview of what a MAC address and an IP address is. So for any device on the network, it's going to have its own address, so anything else on the network that wants to communicate can reach it and communicate, and its address is going to be a MAC address and an IP address. So the MAC address is the physical address that's actually a unique identifier that's burned onto the network interface card that's never going to change. And the IP address is an address that's assigned to it by the software, and that can change based upon what network you're on. So just remember, the MAC address is a physical address, the IP address is the logical address. So now let's talk about MAC addresses in detail. So again, the MAC address is called the Media Access Control Address, and it's the actual physical address of the network adapter. And so what do I mean by the physical address? Well, I mean it's an actual unique number, such as a serial number, that's actually burned into the card itself. So on the actual network card, it's an address, such as a serial number, that's never going to change. And when we're talking about a MAC address, when we're referring to the OSI model and the TCP/IP model, we need to understand what layers they associate with, because we're always going to be referencing back to the OSI model or the TCP/IP model. So for the OSI model, it's going to be layer 2 address. So the MAC address is going to be operating at layer 2. And for the TCP/IP, it's going to be operating at the network interface layer. And the reason I brought this up now before we go any further is we're going to be discussing this later, and I want you to kind of start to get this in your head and start to get into your memory that MAC addresses operate at OSI layer 2, which is a data link layer, and MAC addresses operate at the TCP/IP network interface layer. Because once we start talking about those different models later again in the course, it's all going to start to click and make sense. So with that said, let's go ahead and let's get back to our discussion on MAC addresses. Okay, so getting into all the details. So remember that the MAC address is an actual address that's burned onto the card and it's unique. So what's the formatting? Well, it's composed of two different parts. There's a first part and there's a last part. And it's composed of 6 bytes, which equals 48 bits. Now the first 3 bytes, which I have listed here in blue, these are going to be what's called the OUI, which is considered the organizational unique identifier. And so, for example, every single different manufacturer of network interface cards, whether it be a company like Dell or HP or Apple or Belkin or Linksys or any of these companies, they have an OUI that's associated with their network interface cards. And those are handed out by an organization called the IEEE. And the IEEE is the one that holds on to these and manages these different unique identifier serial numbers, and they say, okay, Dell, you can use this, HP, you can use this, and so forth. So with that said, when we're looking at these, the OUI is going to be the first part. It's going to be the first 3 bytes. And that's going to be a total of 24 bits. And for a total of 24 bits, I have it listed down here. So if we're talking about 24 bits, it's 2 to the 24, and so we can have roughly 16.7 unique different manufacturers of network cards, and they can make a total of 16.7 million network interface cards before they need another OUI. So this is always going to be the same for the manufacturer. However, this is going to be unique, and I'm just going to say U here for unique. So every single network interface card built by a manufacturer is going to have a unique serial to it, and that's going to be the last part. And I listed up here duplications are rare because each manufacturer, when they get one OUI, they can make this many different unique MAC addresses for devices on the network. 16.7 million. So here's a question. Has Dell produced 16.7 million computers? Probably not, but maybe close. What about HP? What about Apple? Maybe. Out of all of them, probably Apple, because they have iPads, iPhones, iPods, laptops, desktops, servers, you name it. So what happens when they run out? What happens if they use up all 16.7? Well, they simply go back to IEEE and say, give me another OUI. And they'll give them another OUI, and they'll use that, and they can use that for another 16.7 million. So if you think about it, that's a lot of unique network interface cards that we can have on the internet. But that's the formatting, and that's how it works. Now, for those of you that just want to understand how networks work, you don't have to worry about this. But those of you that want to go out and you want to get your CCNA or your CC and ENT or your Network Plus, you're going to have to understand this because you may get asked these questions on the exams. So let's talk about determining how you can find out what your MAC address is. And so let's jump to the next slide. Well, it's really simple. And I'm actually going to do a live demonstration in 1 second, but let me go ahead and show you how it works. So let me go ahead and get my highlight tool ready. You would go and open up your command prompt. So if you have a Windows machine, you go to Start. And if it's a Windows 7 or greater, you would just go down to the very bottom Start menu, and where it says Search Programs, you would just type in command.exe. If you have Windows XP, you'd have to go to Start Run and type in command.exe. And then that's going to pop up for you. And then once you get there, you're simply going to put in this information at the command prompt, ipconfig /all, and then it's going to output a whole bunch of information. And this right here, where it says physical address, this is going to be your MAC address. And what you'll notice, and let me change my color on here so you can see the difference. So we'll make it green. This first 3 numbers here, that's the unique identifier for the manufacturer, and this is off of Dell, so this is going to be Dell's unique identifier. And then the second portion, and let me change that to white, hopefully you can see it, and it's not too dark. The second portion over here, the 93FA9D, that's going to be the unique number for my actual network card. So let me go ahead and let me pull up a command prompt. And let me bring it over. So I'm going to go ahead and type in command prompt, slide it into the screen, and we'll go ahead and make it a little bigger. So you would type in ipconfig /all, type enter, and it's going to output all sorts of different information. Now, lots of computers now are going to have more than one network interface card, so we can actually look them up. But I'm going to go ahead and scroll up to my Ethernet card, which means this is my local card that connects in with the network cable. And you'll notice here, and let me get my screen draw ready again, and we'll highlight this. So let me highlight this, and we'll go ahead and we'll do green again. So here's my physical address for my Ethernet card. And then for my Wi-Fi card, again, I have a different one. And so let's find that. Here's my wireless card for Wi-Fi. It has a different card, and here's my Ethernet address here. My physical address, sorry, not my Ethernet address. And this is our MAC addresses. So here's my MAC address for my physical connection where I plug in with the network cable right here. 3417EB730FEF. And then for my Wi-Fi card, my MAC address is 34DE1A14FBF9. And you'll notice that the first 3 numbers, the OUI, are different. And if we think about that, why is that so? Well, maybe they have more than one OUI and they're using different ones, or they outsourced. I am on my Dell laptop right now. Maybe they outsourced the Wi-Fi card or the Ethernet card to a different company, and that's their OUI. But anyways, that's MAC addresses. That's your quick introduction. I hope it was beneficial. If you have any questions, let me know. If some of it doesn't make that much sense, just go back through the lecture and also reference guides on the internet. So I didn't go into a 30-minute presentation on MAC addresses, but I did my best to be thorough without going into too much information. So thanks for watching, and we'll see you at the next video. So we talked about MAC addresses in the previous lecture, which is the physical address of the network interface card on any network device that's burned onto the network interface card, and it never changes. Well, in this lecture, we're going to talk about its counterpart, and we're going to talk about the IP address. And the IP address is a logical address that's assigned to a network device by the network itself. And for example, what we're used to seeing is something like this: 192.168.1.131. And I forgot to put my dot in there, so let me put that in there. So this is what we're used to seeing. We're used to seeing this 192.168.1.131. And what this is an address that's assigned to your computer or your server or your tablet or your iPhone or anything else by a router on the network or a server that gives out these addresses. And so, this is what you're used to seeing. For example, if you set up your home network and you have it with Comcast or somebody else or some other provider, and you're having issues and they say, okay, well, what's your IP address listed at? Tell me what your IP address is, or here's the IP address to get access to your router. This is what we're used to seeing. And this is a specific type of internet protocol, and specifically it's version 4. And so you'll notice up here I have v4, and down here I have version 4. So this has been around for quite some time. Version 4 has been the standard protocol. However, there is a newer one called v6, so version 6, but we're not going to talk about this in this introductory lecture. We'll talk about it later on in the course. So what does IP stand for? Well, it stands for a very simple name, Internet Protocol. And that makes sense because this is an address that you need to access the network and the internet. And so when you need to get your computer device out on the internet so it can communicate across the internet with Google or your Gmail or your online banking account or another server out there, you need an IP address. And this is it. Now, we want to talk a bit further about this. So we're used to seeing this 192.168.1.131. What we call that is we call that dotted decimal format down here. However, when a computer interprets it, it interprets it as something else. It interprets it as a bunch of ones and zeros. And what is the ones and zeros? Well, that's pretty much machine code, and what we consider that is binary format. And so when we're talking about binary format and machine code at the lowest level, 1 means it's on, 0 means it's off, and that's how it's going to be interpreted by your computer. However, for us to understand it, it's converted into this dotted decimal format. And so dotted decimal pretty much converts binary numbers into decimals. And we'll talk about how to do this conversion later in the course, but we're not going to focus on it right now. All you need to know is just be aware that when we see 192.168.1.131, we can convert it into its machine code, its binary code, and we can go back forth. And that'll make a lot more sense when you get further into your career if you decide to go into the network and you understand subnetting and everything else. But this is just the standard format. So let's go ahead and let's take a look at how you would find your IP address. So what if you wanted to find your IP address on your computer? Well, you know what? We're going to do the same thing that we did before. We're going to use that same thing that we did in our previous lecture where we went to the command prompt and we did command exe. So we'll use that again, and let me get my highlighting tool out and ready so I can show you what I'm talking about. So we would go to our command prompt, and let me highlight that up here. And once we get in there, we would type in our ipconfig space /all, and then we'd look down and we're going to look for IP address. And let me show you on both sides. And there's your IP address. And you'll notice that it says IPv4. Now, some of your systems might be set up for an IPv6, and here's an IPv6 right on top of it. And what I'm going to do is I'm going to demonstrate this. So I'm going to go ahead and I'm going to pull up my command prompt. So remember, if you're on a Windows machine, you're going to go to the start, you're going to go to run and type CMD, or you'll just go to the search bar in Windows 7 or Windows 8 and type in the CMD, and it's going to go ahead and pop this up. Now let me go ahead and slide this over. Now if you're on a Mac or Linux, it's going to be a bit different. You got to go to the console, and the code is ifconfig instead of ipconfig. I'm not going to cover that because I'm on a Windows machine, but you can look up the exact code to get this as well on a Mac or a Linux. So I'm going to type in ipconfig space /all, press enter. And remember, I'm on the same system as I was before, and I have all sorts of different IP addresses configured on here. I have a wireless card, I have a wired interface card, I have Bluetooth, I have all sorts of different things. So we're just going to look at the wireless card for this lecture. And let's identify it. So let me get my highlighting tool first. Let's find our IPv4, and it's right here. Do I have IPv6 set up? Yes, I do. Here's my IPv6 right on top of it. And just for fun, where's our MAC address? Because we covered that in our last lecture. Well, our MAC address, remember, is our physical address, so it's right there. And so we'll go ahead and we'll highlight these on the other side. So here's our MAC address. We didn't talk about IPv6, but here's our IPv6 address, and here is my IPv4 address. So for my Internet Protocol version 4, you'll notice that my address is 192.168.0.106, and we didn't really talk about IPv6 yet, so I'm not going to go into any of that. You'll notice that's a lot harder to read. However, we did talk about physical addresses, so the physical address is 34 DE 1A 14 FB F9. And that's it. And that's how you do it. You go ahead and you look it up, and you can find it that way. And it's always good to know this, even if you don't decide to go into networking. If you're just taking this course to find out more about it, it's always good to know for home troubleshooting if you need to call up your service provider for your internet and they're going to ask you for some information. So that's going to go ahead and conclude our introductory lecture into IP addresses. If you have any questions, please post them on the discussion board and I'll be happy to answer. Thanks for watching, and we'll see you at the next lecture. So in this lecture, we're going to talk a bit about IP addresses and MAC addresses side by side. I know we've done previous lectures on MAC addresses and IP addresses separately. However, now I want to put them side by side so you can see the differences, and I hope it really makes all of it make sense now. So let's go ahead and let's start with the basics. Let's talk about the OSI model. And remember, this is something that is a conceptual model, and it's something we're going to be talking about throughout the course, and we want to use it to understand how networks work. So we need to understand what layers IP addresses and MAC addresses are on. Remember that IP addresses are going to be on layer 3, which is the network layer. And MAC addresses are going to be on layer 2, which is the data link layer. And this will make a lot more sense as we go on into the course. Now also, remember that a MAC address, that's that physical address. And it's never going to change. Remember, it's actually physically burned into the network interface card, so it's never going to change. However, an IP address, your 192.168.1.1 or whatever it is, that dotted decimal notation that we talked about. Remember that that's going to change based upon whatever network you're on. If you're on your iPhone, you're on your home network, it's going to be a separate logical IP address than if you go to Starbucks and you get on their network, you're going to get a different IP address. So that's the main differences. However, there is a really big difference that we have yet to talk about, and I'm going to introduce that right now. So let me get my highlighting tool out so I can help highlight this and make a lot more sense. So IP addresses are used to communicate in different situations than MAC addresses. So let's start with MAC addresses. MAC addresses are used to communicate in what we call internetworks, meaning one specific network. However, an IP address is used to communicate between networks. So, for example, if you have a home network set up, let's say that you have a home network set up and you have your laptop and you have your desktop and you have your network printer, your MAC address is what's going to be used to communicate on that home network, because that's one network and we call that an internetwork. However, when you're at home and you're trying to communicate, let's say you're trying to get onto Gmail and you want to check your emails, or maybe you want to go to wellsfargo.com and check your bank account. That's what we consider network to network communication, and your IP addresses are the addresses that we're going to use. So to communicate from one network to a distant another network that's not connected to yours, we have to use our IP address. And what we call this is that we call this WAN communication. We call this wide area network communication. And let me change this color so you can see what I'm talking about. So this is what we call wide area network. A wide area network is something like the internet because it's multiple networks connected together. However, your home network is what we call a LAN, which is a local area network, meaning everything's local. And so that's a new concept that we introduced now. IP addresses are for network-to-network communication where you're trying to connect and communicate with an entirely different network. MAC addresses are for communication within a single network where you're trying to connect to local devices and communicate with them. And so just remember that and remember these few key things because we are going to go into details and we're going to talk about this more when we talk about hubs, switches, and routers and network communication in the same network versus network communication in other networks. So if you have any questions about this, please let me know. If not, thanks for watching and we'll see you at the next lecture. In this video, we're going to be talking about local area networks and wide area networks, and we're going to talk about what they are and how they differ. So what is a local area network? Well, first of all, a local area network is commonly referred to as a LAN, and all it is a collection of computers and other networkable devices connected together within a single physical network. And the key word is that we're talking about a single physical network. Now, we haven't really talked about what composes a single physical network, but we'll get into that later in the course. But let's go ahead and let's talk about some examples. And I have some examples down here on the bottom of the screen. So let's start with an office building. Let's say that you are renting out maybe the 4th floor of an office building for your law firm, and you need to set up a network. Well, that would be considered a local area network. Another one would be, for example, let's say that you own a 4-story building and there's different departments on each floor. And let's say the marketing department is on the 2nd floor. Well, if you set up a network for the marketing department, that would be considered a LAN. It would be considered a local area network for that department. Another one would be your home office or simply your home, where you have your home network set up with your laptops and maybe a desktop, maybe a couple tablets, maybe a couple smartphones. That would be considered, again, a local area network. And then another good example would simply be a classroom. Let's say you have a classroom on your campus where there's 30 different desktops, one for each student, and it's connected together. And so it's a network for the students in that classroom that would be, again, considered a local area network. And so the one major thing behind this when we're talking about local area networks is really the constraint upon it. And the constraint meaning that it's constrained to one specific area. And really we're talking about being constrained to one geographic region. So it's not spread out across multiple different areas, but it's really, and I'm going to highlight this whole portion here, it's restricted to one particular geographic region. And that geographic region could be an office building, could be a single department within a corporate office, it could be a home office, it could be a classroom. But we just need to think about it as being its own single entity as a local area network, and it's within the same geographic region. So now that we know that, let's talk about wide area networks. So a wide area network, on the flip side, is multiple LANs connected together. And I'm going to introduce a new term to you right now, and that new term is intranetwork. So what do I mean when I say intranetwork? Well, an intranetwork is multiple LANs connected together. However, a WAN is multiple local area networks connected together that spans a large geographic region. So we're talking about multiple different locations connected together. And the key point to this is that, let's say, for example, if you had an office building for a large corporation, one in San Francisco, and you had another one in New York, and you had another one in Dallas, and you needed to connect all those together, well, those would be either LANs or a connection of LANs as an internetwork at each site, at each location. However, when you connect them all together across the United States, then it becomes what we call as a WAN. And so it's no longer a local area network when you connect them together, because when you connect it across a large geographic region, then we can no longer consider it a local area network, and we have to call it a WAN. And this will make more sense when I show you some diagrams in the next pages. Now, when we are talking about wide area networks, they usually employ routers. And so if you see a router in the network and a router connects one device to another, then we're usually talking about either an internetwork or a WAN. Typically a LAN's only going to have a router at its edge to reach out to another network, but it's not going to have it within its network. And now another thing with wide area networks is that it really includes and uses public links. So what I mean by public link, I'm talking about a publicly leased link to connect to the internet to get to another site, such as, for example, the San Francisco office connecting to the Dallas office. So, they reach out to the internet service provider and they say, look, either I need to share one of your public links to connect to my other site, or I need my own private link that I'm going to lease from you. And really the best example in the whole entire world is going to be the internet. So the internet is nothing more than a wide area network. It's hundreds and thousands of local area networks connected together, and that's how we've reached and that's how we've built up the internet. Another example would be a campus network. Let's say, for example, Stanford University or Cambridge University. Now, it is within the same geographic region, but really these campuses are immensely large and they span the size of a city, so we can consider them a wide area network because there are multiple small networks connected together. So that's the one thing about a WAN, is that it doesn't reside in a single location. It resides in multiple locations. So let's go ahead and let's look at a couple of diagrams. So here's the first one, and hopefully this one's going to help bring this all, into fruition and really make it click and make it kind of stick into your head. So in this example, we have multiple different office buildings across the United States, and we're trying to connect them together so they communicate. We have an office in Montana, we have an office in California, we have an office in Texas, and we have an office in Virginia. And when we start connecting them together, these local area networks within each one of these buildings, when they connect together across the US and they connect across public lines through your internet service providers, they then become a WAN. And that gets us to our definition at the top, is that really what this turns into is that multiple local area networks become a single wide area network. So, we can even build this out further with, say, this network connects to this one like so. This network can also branch off and connect directly to this one. And again, it looks like they're almost all connected. Maybe this network can directly branch off or connect to this network as well. And so we can have all these different links and they're going to combine together, and this 4 different LANs, one for each corporate office, becomes one big wide area network. So let's go ahead and look at this again from another perspective. So we have 3 different LANs, and what we're doing here is we're connecting them together. So we have our LAN over here. So let's say we have LAN number 1, and then down here at the bottom we have LAN number 2, and down over here we have LAN number 3. So we have 3 distinct LANs, but when we connect them together across a single communication line here, then they become a wide area network. And let me change this to a different color so it helps make a little more sense. Let's make this blue. So when they connect to here and now they're able to communicate, these 3 LANs become a wide area network. And so we have 3 different LANs becoming one. So that's the difference. Remember, a local area network is a single network. It's usually in a single geographic region. And a wide area network is just nothing more than multiple different LANs connected together, and it's dispersed across a wide geographic region. So that's going to go ahead and conclude our discussion on local area networks and wide area networks. If you have any questions, please let me know. If not, thanks for watching, and we'll see you at the next video. In today's video, we're going to talk about the peer-to-peer network architecture. Now, there are 2 different types of architectures in the networking world. There is a peer-to-peer network architecture, and there's a client-server network architecture. And you either have one or the other, and we're going to start off a discussion talking about what a peer-to-peer network architecture is. So what is a peer-to-peer network? Well, it's simply the type of a network where every single computer on there is a client machine, but it also hosts resources, and we consider those peers. So what do we mean? Well, I mean that there's no dedicated servers, not a single dedicated server on the network. So a really good example would be a small office, maybe a 3-office small business where there's 3 different owners and everybody buys their own laptop and they hook them up, and you have a wireless router and everybody connects to the network. And everybody creates their own files and shares their own files with everybody else. That is what we call a peer-to-peer network, because there's no dedicated server. On the flip side, there's client server. And so with the client server architecture, there's people that have client computers and there's servers that do the role of a server. However, in a peer-to-peer architecture, there is no centralized control of shared resources. And so that gets me to this next point. And I'm going to highlight this because I think it's vitally important for you to understand, is that when we're talking about a peer-to-peer design, there is no centralized control. And so no centralized control means that, for example, for those of you that work in a large corporation and you have to log into your desktop every day and you have to connect to your email server to get your emails, or you have to connect to a file server to get your files, or you have a SharePoint set up to share your files, well, that's what we call a client-server architecture, because there is a centralized system set up in place where it controls access to everything. However, in this type of a design, there really isn't any at all. Everybody has full control. And what I mean by that is that every individual machine on the network can share its own resources as it pleases. And so that's really important to think about it, because it's really up to, let's say we have an example. We have Millie, Pluto, Louie, and Mickey, and they all have their own machine on the network. Well, they can determine who they want to share the files with. Maybe Millie wants to share files with Mickey. Well, she can do so, but she doesn't have to share it with Pluto, or she doesn't have to share it with Louie. She has complete control. And the one really important thing to understand with this architecture is that all the computers on the network can either act as a client or a server. And so when we're talking about a client, we're talking about receiving resources, and we're talking about a server, we're talking about providing resources. So that's the distinct difference between a client server, and we're going to talk about this more in the next lecture. So for example, every single computer on here can receive resources from everybody else, but at the same time they can provide resources, and there's no dedicated server set up. Another thing is that each person owns their own specific machine on the network. So Millie has full control over everything on her device, Louis has full control over everything on his device, and so forth. And they set the passwords up, they set up the access to all the other users on the network, and they determine what's going to be shared and what's not going to be shared. So let's go ahead and let's talk about some of the pros and cons. So now that you have a basic idea of what a peer-to-peer network is, let's talk about the advantages and the disadvantages. And let's start with the advantages. Well, the first thing is that it's really easy to set up. You don't have to rely on anybody to have this really in-depth knowledge of setting up a network to get a peer-to-peer network set up. In fact, if we think about it, almost everybody here watching this video is on a peer-to-peer network a lot of the time. So for example, if you're connected to the network at your home, that's a peer-to-peer network, because you don't have a dedicated file server set up, you don't have a dedicated authentication server, you don't have a dedicated SharePoint server or email server. Everything on your network can be a server or a client where you are sharing resources with other devices on your network, or you are consuming them, you're taking them from other devices. And with that said, because we don't have to have this expertise to be able to set up a file server, an authentication server, an email server, it's really easy to configure. So it's easy to install and configure. And this is really the driving force for people that decide to set up a peer-to-peer architecture. It's because you don't need that expertise. And so with no presence of any sort of a dedicated server, we don't have to worry with having the expertise to set it up. The other advantage is that when you have a small business or you have your home set up, every single user has control over their own resources, so they can determine what they want to do and they feel like they have ownership over it. Now the third reason is that it's very inexpensive to set up and operate. So you don't have any dedicated servers that cost thousands of dollars to purchase, and then also thousands more dollars to have an expert come in and set them up and run them. You can just go down to your local store. You can go to Amazon.com or Dell.com or HP.com, buy some laptops or buy some desktops, hook them up to a switch and a router that connects to the internet, and you're all set up. Now, the other benefit, and a lot of people with small businesses and small home networks, one of the reasons why they set this up is that you don't need dedicated administrators to run the network. So you don't need system administrators to run the servers. You don't need a network administrator to run the network. It's just a very simple network. It's easy to set up and it's easy to start running. So there's a lot of advantages, and that's why you'll see a lot of small businesses take this approach and they'll set up a peer-to-peer architecture. And that's why all of our home networks are peer-to-peer architecture, because it's just too expensive to do client server. But there's also some really major disadvantages. So let's talk about those, and instead of highlighting those in yellow, let me go ahead and highlight those in a different color. So we'll go ahead and we'll highlight these in cyan instead. So network security is a huge issue and it's a huge disadvantage. There's really a lack of proper network security in place when you have a peer-to-peer architecture, because when every single person on the network has full control over what they're going to do with their system, then we don't have any control over how network security is set up and how our cybersecurity is set up in an optimal manner. Really, there really isn't any at all. It really depends on that person. So it only applies to each single resource on the network. So every single device may have different settings, and one may be more secure than the other. And if we're talking about passwords, that's also another issue. If you have 5 different machines on the network and different people set up different passwords to their shared folders on the network, then that's 5 different passwords you have to remember. Versus with a client-server architecture, you don't have to do that. You have a single password. Another thing is, if you don't have a file server and every machine is hosting and sharing files, well, we have to back up every single machine. So every single machine on the network has to be backed up itself. And that can be a huge burden. And in fact, how many people taking this class, watching this video right now, how many of you back up your data on a regular basis on your home network, on your desktop or your laptop or your tablet? Do you back up your data daily? Do you back up it weekly? Do you back up it monthly? And do you back up every single device on your network? The answer is probably no for a majority of us, because a lot of people, a lot of us don't experience system failures, and when we do, it's very rare, so we have this false sense of security. But when you're in an enterprise network environment, we have failures all the time, and so we understand the need to back up our data. But that's the disadvantage of having a peer-to-peer, is that you have to trust that everybody's going to back up their own data and they're going to do it on a regular basis. And the fact of the matter is, a majority of the time, they're not. Now, the other issue with this is that there's no centralized organizational scheme. And this is really important. So when we talked about how we set up a network and how we standardize and how we have modularity, it's based upon having a centralized organizational scheme, and everybody's following the same rules, and everybody is using these certain protocols to access one another and communicate on a network. Well, when you have a peer-to-peer architecture, yes, you're on a network, but there's no centralized control over how data is accessed, who can access it, when it's going to be available, how we're going to secure it, how we're going to back it up, how we're going to manage our passwords, or any of that when you have a peer-to-peer architecture. So, with that said, there's some huge disadvantages to go along with those huge advantages, and mainly the main huge advantage is that it's inexpensive and anybody can set it up, and it's really easy to get a small business up and running or a small home network up and running. The downside is that we have a lot of holes in regards to network security, information security, data integrity, and really having full control and understanding how our network's going to work. So that's going to go ahead and conclude our introduction to peer-to-peer networks. If you have any questions, as usual, let me know. If not, thanks for watching, and we'll go ahead and we'll jump to the next video, which is going to be our discussion on client and server network architecture. So we talked about the peer-to-peer architecture in our previous video. Now we're going to talk about the client-server architecture. And what we want to focus on here is we want to focus on how it differs from the peer-to-peer architecture. So remember, in the peer-to-peer architecture, every single device on there shared resources and they also received resources. So we called them a peer because they were a combination of a client and a server. Well, in a client-server architecture, we only have clients and we only have servers. We don't have a combination of both. And so how does that differ? Well, clients receive resources on a client-server architecture, and servers provide resources. So we don't have a peer that does both. We don't have a peer that receives resources and provide resources. In this architecture, we have dedicated servers that provide resources, and we have dedicated clients that we use as employees in an organization to access those resources on the servers. And I have a really good example over here. We have a dedicated server here, and I'll highlight this so you see it. And it shares resources with the 4 systems on the network: Millie, Pluto, Mickey, and Louie. And with this, we can determine what type of access these people have, when they have access, and how they access it. And you'll notice is that we can control everything right here on the server. We can control their passwords, we can control what type of access they have, and we can also control when they have access. Now, a couple of other things to take away from this slide is that when we're talking about servers providing centralized control over network resources, we're not only talking about file servers. There can be all sorts of different servers on a network. We can have print servers to control who has access to what printers and when. We can have authentication servers to determine who has access to network and when, and it controls how they access it and how they log in. We can have streaming media servers for types of companies such as maybe we're Yahoo or we're a multimedia company, where we determine what type of media can be streamed across the network. And so there's all sorts of different resources that we can think about that can be shared on a network. And we really, in this architecture, we use servers to provide those resources. So let's go ahead and let's talk about the pros and cons. So we talked about the pros and cons of the peer-to-peer architecture. Let's talk about it for the client-server architecture. Because now that we understand that this is a more robust network and it provides greater cybersecurity and information security control, there's got to be some pros and there's got to be some cons. Well, the first major advantage is we do have that centralized control over everything on the network, on the user accounts, on the resources, and on access to the servers. And so that provides us greater security. It really simplifies how we manage the network. And having those two features, having enhanced security and really having simplified network administration, because we're only focused on securing and managing and backing up and making sure that data and information is there on the servers. We don't have to worry about the clients as much. Now, another benefit is that when we do go with this architecture, when we do set up servers, they're typically going to be a lot more robust than a client computer. They're going to cost a lot more. However, because they're more robust, they're going to be much more efficient in the way that they provide resources on the network. And so they scale up a lot easier, and they are going to be more efficient, and they're going to be a lot faster than if we had a peer-to-peer network. Another advantage is we have our single password. So remember when we had the peer-to-peer, everybody set up who had access to what on the machine, and they could set up whatever password they wanted. So if you had to connect to 4 or 5 different computers, you could potentially have to remember 4 or 5 passwords. However, in a client-server architecture, if we have an authentication server, then we set up a single password and everybody has access with one login to all the resources on the network. And so for those of you that work in a large environment like me, you're going to be used to this. So there's a lot of pros, and that's why all the larger organizations use a client-server architecture. However, there are disadvantages. So let's talk about those disadvantages. Well, the first one is, well, what happens if we have a server failure? What happens if our file server goes down? Well, it could potentially render the network unusable because we don't have access to the data that we need. And so we'll have a loss of resources on our network if it's not set up properly. And you can set these up with redundancy, but it's expensive. Now, another issue is the complexity. A client-server architecture is a lot more complex than the simple peer-to-peer architecture. You can't simply go down to Best Buy or go onto Amazon and buy 4 of the same laptops and set up a client-server architecture. You have to go to HP or Dell and you have to purchase server hardware and server software to set that up. And then you also have to set up your clients with client systems and client software. So it's a lot more complex and it's a lot more expensive, and it requires more expensive hardware and software, but it also requires expert staff. So we have to have system administrators, we have to have network administrators, we have to have help desk people and desktop support. So again, it's a lot more expensive. And this really increases our cost of ownership. And it really comes down to this last point here, is that the cost of ownership is so much higher that smaller businesses can't afford to set up a client-server architecture for the most part. They're forced to go with the peer-to-peer architecture. And until you have a larger organization with a lot more money, then you really can't go with a client-server architecture, or if you do, you're not going to be able to set it up properly. So that's the pros and cons of a client-server architecture compared to a peer-to-peer architecture. If you have any questions, let me know. I know we just skimmed the surface on this, but hopefully it gives you a level of detail and a better understanding of what these are if you haven't heard of them before, or if you have heard of them and you just didn't know that much. But if you do have any questions, as usual, let me know. Post your questions to the discussion board for the class. If not, thanks for watching, and we'll see you at the next video. In this video, we're going to talk about common networking components, and this is going to be a brief introduction to some of the more common networking components. Later in the course, we're going to go into great detail, and I'm going to have dedicated lectures on all the different major networking devices, so don't feel like this is all you're going to get out of this course. This is just a brief introduction to some of the more common ones, so as we move forward in the class, it's all going to make a lot more sense. So let's go ahead and let's get started with this lecture. So there's 3 different devices we're going to talk about on this slide. We're going to talk about routers, firewalls, and switches. And before we get into that, here's a basic network diagram at the bottom, and we have a router down here. And so let me go ahead and mark this. So we have a router here, and this whole area right here within the router, this is going to be our network. So let me go ahead and change colors on here so we can see the difference. So this right here is our network, and on the border of the network we always have a router, and that's really what's going to show the edge of our border, and on the other side is the internet that we're trying to connect to. So with that said, what does a router do? We know now that the router is on the edge of the network. Well, it's simple in what it does. It connects one local area network, so one LAN, or one network for short, to another one. And that's the whole point of a router, is that it routes traffic from one network to another. And in this example, we're using the internet down here. So it allows us to route traffic from our network across the internet to some other network. And if we think about it, remember when we talk about the internet, remember it's nothing more than multiple networks connected together. So we can call that an internetwork, or we can call it a wide area network. And remember, a wide area network, it is nothing more than multiple local area networks connected together. So let me just go ahead and type in WAN. And remember, the internet is nothing more than a wide area network. So that's what a router does. Now let's talk about the firewall, and let me go ahead and circle the firewall as well, and we'll use a different color. So here's our firewall, and you'll notice here is that we have our local area network, and right on the inner edge border of our network is the firewall. So what does it do? Well, as its name implies, it keeps fires out. And when we're talking from a networking perspective and a cybersecurity perspective, a fire is malicious data. So we're trying to keep hackers out, and we're trying to keep all their malicious hacking attempts out of our network. So if they're trying to send malware into our network, or if they're trying to gain access to our network, the whole point behind the firewall is to prevent that from happening. So it really, more than anything, keeps the bad stuff out of the network. And we're not going to go into detail into what all the different malware is and all this different malicious data trying to get into the network is and all these attacks are, because this is not an information security and cybersecurity class or penetration testing class. But I just want you to understand from a high level that a firewall protects our network from malicious data and malicious packets of information. And when we're talking about a packet, that is what we're talking about when information goes across the network. We call it a packet. So lastly, let's talk about a switch. And let me go ahead and circle the switch as well with a different color. So here's our switch. Once we move further into our network, So we go from one device to the next, and let me go ahead and use my arrow, and we'll go ahead and use this in red. So we have data coming in. Let's say we have data coming in to the network router. It goes into our network. It goes in the firewall. The firewall says, okay, this data is clean. It goes into our switch, and then our switch, what it does is it connects everything on our network together, and it switches traffic, so it determines where traffic goes on the network. And a really good analogy is, for example, remember a long time ago when they had operators in a phone station where they actually switched the phone calls from one switch to another to connect people? Well, that's really what a network does. If we know that the data needs to go up to our laptop, then that's what it's going to do. It's going to route it to the wireless access point that's going to send it to our laptop over here. So really think of it as the switch is really, it switches the data and determines where it needs to go on the network, connecting our network together. So that's how these three different devices work in combination together to get data where it needs to go on our network. We have our routers that route data across one network to the next. We have our firewalls that's going to protect our personal network, keeping the bad stuff out. And we have our switch connecting everything together on the network, making sure data, once it gets into our network, it goes where it needs to go. So now let's talk about servers. So we talked about servers in our previous lectures. We talked about the client-server architecture, but I want to just quickly discuss with you some of the more common types of servers, and this is going to be a quick discussion. So there are different types of common servers that you're going to see on a regular basis, and let's talk about them. So we have authentication servers. An authentication server, what it does is that it manages the access control to your network. So it manages who can get on and who can't get on. It manages the username and passwords. It manages what resources they have access to by having access control set in place. And it manages what time of the day and what days people can access the network. A file server, as its name implies, it manages and stores the files on the server. So it stores the files, and as people need them, it gives it to them. And when they're done, it stores them again. The mail server, well, it's like the post office. It's like the digital post office, because the mail server is what handles the emailing functionality of your network. So if you have Outlook set up and you need to send emails from other people on your network, that's what the mail server does. The print server, again, as the name implies, if you need to print something out to one of the printers on the network, well, that's what the printer server is there for. It's there to manage the print jobs on the network, and it's there to give different people and different resources higher priorities and different priorities on different printers on the network. Now, web server, that's if you have a public website set up, or if you have an internal intranet set up for your company, that's where you're going to host that so everybody has access to that. We can also have application servers. So if we have our own customized applications that we need to have set in place for our company, maybe we have, accounting software where we need to have an application server, or we have, some sort of other business function that requires a special application, then that's what we're going to have with our application servers on the network. And then data typically stored from applications usually go to database servers. So many applications store their data in a database, and a majority of the different systems out there are going to be doing that. So you're going to have database servers set up in place to store your data. And so there are simple rules just simply to manage the data in a database. So that's our common networking components. So we talked about our common networking devices, talked about the router, firewalls, and switches, and we talked about our common servers in, about 7 minutes worth of detail. So high level detail, enough to give you an overview. So later in the course, we'll be talking about a lot more of this stuff in detail, and I'll be talking to you about many more different networking components. But hopefully this will serve as a good primer moving forward in the class. So thanks for watching, and we'll see you at the next video. In today's video, we're going to be introducing the concept of physical network topologies, and we'll be talking about their importance. So what is a physical network topology? Well, it's all about how the devices in our network physically connect together. So we're talking about taking everything on the network. We're talking about our servers, our desktops, our laptops, our routers, our switches, our hubs, and all of our cabling, and determining how we should connect that together. And there's specific topologies in place that we can follow, and so that's what we're going to talk about. Now, before we talk about their importance, the first thing I want to say is that we're not going to cover all the topologies in this section of the course, simply because we don't need to cover them for the scope of this course. However, if you do decide to go and get one of your certifications in networking, such as Network Plus or the CCENT, you're going to need to know all the different physical network topologies, and we're not going to be covering the more antiquated ones. And so ones such as the bus and the ring, those different topologies that we're not going to cover in this course. So let's go ahead and let's talk about their importance. So why are physical network topologies important? Well, first of all, it's all about planning. And when we're planning and designing a network, we need to know what type of topology is going to work best for us and for our situation and in our scenario. And also in regards to all of our constraints. Maybe we have technological constraints, or we have monetary constraints, or we even have personnel resource constraints. So it all comes down to planning and designing the network and understanding what's going to work best for you. Another important thing is that it shows the network on a map. And so it's going to physically show where all the devices are on the network. And it's really going to show you how everything interacts with the cabling. And for somebody that's been in IT, if you've been in IT and you've been in desktop support or you've been in network support, you'll know how important this is. And when you don't have this in place, you know how difficult it can make your life. Because when you don't know how the network's connected and you're having network issues, then not having a physical map of the network is just going to be a huge hindrance for you trying to troubleshoot those issues. So, when we're talking about all that, it really comes down to when you know how everything's connected together on a physical map and how it's designed, you understand how data and information flows throughout the network. And so when we're troubleshooting, it's easier to identify what the potential problems are, and we can isolate them a lot easier. And so this is what it's all about. This is why it's important. We do it because we need to have a network map. Once the network is designed, we need to have one in place for when we design it. We need to understand all our constraints and our resources and understanding how we can properly plan and design the network and what should work for us. And then when we're troubleshooting after the fact, when we're giving the network off to the system administrators and the network support personnel and the desktop support, it's important for them to have this information so they can easily troubleshoot their issues. So in the next video, we're going to start talking about some of the physical topologies. So I'll see you there. In today's video, we're going to talk about some of the more popular, more prevalent physical network topologies being used in modern networks today. So we're going to kick off our conversation talking about the star topology. And the reason we're going to talk about this one first is because it's arguably one of the most popular physical topologies being used today, both in large and small networks across the world. So what is it and how is it designed? Well, we call it a star because everything is centrally connected. And I only have 4 devices on here, but if I put a 5th and I aligned them like a star and I drew lines out, it would look like a star. So everything is connected to a central device, and that central device is either a switch or a hub. And so for example, we have a switch here, and we have 4 different devices connected to it. We have a system here, one here, and one here. And they all have a separate network cable that goes directly into this switch or this hub. And the way that it's designed here is that it has built-in fault tolerance. So what do I mean by built-in fault tolerance? Well, what I mean by that is that if any one of these end devices go down, or if the network cable on any one of these end devices ends up having issues, then what happens is that it does not affect the rest of the network. And I know we haven't talked about how switches and hubs work yet, but we'll get into it. But I mean, if you think about it, let's say that this device crashed. Well, it's not going to affect how these 3 devices over here connect to the network. Now, let's say that one crashed and then somebody accidentally spliced the cable right here on this one. Again, it's not going to affect any of the other devices because they have their own cable that goes into the switch of the hub, which then connects to the network somewhere else. And so that's what we're talking about, fault tolerance. But there is one major downside. And that major downside is that we have one central point of failure. And what that is that's our switch or our hub right in the center. So what happens if we have a failure here? If this goes down, then the internet connectivity or network connectivity to all these devices, it all goes down. So let me clear this and let me redo this so it looks a little bit easier. So let me get my pen tool out. So let's say that our switch is going to go down. Let's say that it just fails, the hardware fails. Well, if this fails, then there's no connectivity to the internet or network here. There's none here, there's none here, and there's none here. And so it is a central point of failure for the entire network. However, Switches and hubs are very reliable, and I rarely have ever seen them fail. For the most part, they are going to last for a long time. But if they do fail, the upside is that they're very easy and very inexpensive to replace. So if you know that your switch fails, you don't have any power to it, you simply just go and unplug the cables, plug the new ones into the new switch, and plug it into the wall, and you're up and running. So it's not hard to troubleshoot, even though it is a single point of failure. So that's the star topology. Now let's talk about the mesh topology. And the mesh topology is very interesting in the fact that it's designed to have a very high level of redundancy. And so when we need to have a high level of redundancy in place where we need to make sure that our data is safe and secure and highly available all the time, then people tend to implement a mesh type of topology. And the one thing with the mesh topology is that you can have a full mesh or you can have a partial mesh. And here I have a full mesh. And what we're talking about when we say a full mesh, we're talking about every single device on here has a direct connection to all the other devices. So if any one of them has a failure, or if any one of the cables has a failure, there's always a link to get to the other device. And if we think about it, so I have 3 computers. I have 1, 2, and 3, and I have a switch down here. What you'll notice is that this system has a cable directly to this system, has a cable directly to this system, and has a cable directly to this system. And so do all of them. And this is considered a full mesh because they have a direct connection to every other device on the network. The downside to this is that this system here, every single system on here has to have 3 network cards, 1 to connect to each other device on here. And the switch has to have at least 3 ports, which is fine. But the expensive part is buying these multiple network interface cards to make sure that you have this fault tolerance and redundancy in place. So with that said, because we have to have so much hardware that we have to add onto our systems, this is a really expensive topology to implement. And you're typically not going to see it in a standard local area network, but you're going to more so see it in a wide area network where you need this fault tolerance put in place. Maybe you have a router and it has 2 ports just in case one of the lines goes down. It's always going to have a connection to the other network on the other side of the WAN. So let's go ahead and let's take a look at how this would actually work. So for example, let's go ahead and say that the switch died. So the switch dies, and you notice that all of a sudden this cable becomes useless because it connects through here. This cable becomes useless as well, and this cable becomes useless as well. However, these systems can still communicate amongst all 3 of themselves because they have other connections. So you still have a connection here, we have a connection here, so this guy can connect to both of them still. The same thing with this guy, he has a connection here and connection here. Again, check mark, he can connect as well. And then over here as well, we have a connection here and a connection here. So they can still connect. And that's a great thing about having a full mesh. Now, we didn't talk about a partial mesh, and let me go ahead and erase the screen so it's not going to be so garbled with information on there. So what's a partial mesh? Well, a partial mesh is where some of the connections in here aren't going to have a connection with every single device. So for example, with a partial mesh, we could say, maybe on this system, in this system, we don't need to have all those connections. Maybe we don't need to have a direct one here. We don't have to have that level of redundancy and fault tolerance on these 2 systems. So we can take this out and it'll save us some money. And maybe we say the same thing here because we have the switch. It's going to be reliable, so we don't need a full mesh between both of these. And we take this cable out here in the network cards. And so that would be a partial mesh where you determine where you don't need 100% redundancy and fault tolerance in place, and you're just going to take some of those out of there. Now, just leading to the final point again, I want to reiterate is that this is very expensive to install. So this is not something you're going to put in an everyday network because it's just going to be far too cost prohibitive. So that's the mesh topology. Let's go ahead and let's talk about our next topology. And that's the point-to-point topology. And this is really as simple as it gets. This gets back to our initial discussion where we talked about the most basic type of a network. 2 systems connected together by a cable. It's a one-to-one point-to-point connection from one device to another. And it can be any device. I have a computer to a computer, I have a router to a router, I have a switch to a switch. I could do a router to a switch. I could do a computer to a router. I could do a computer to a switch. It doesn't matter. It's just a one-to-one connection. And we typically don't see these in local area networks. We see them used in a wide area network instead. And it's usually in a point-to-point wide area network link, which is going to be something like this right here in the center. And I'll go ahead and circle it. So it's typically going to be in a point-to-point from one network to the other where it's going across a wide area network. And remember that routers sit on the edge of your network and they connect your network to another network. So that's why we have routers, and we're not talking about switches or computers. So when we do see it, we typically see it, for example, a really good example would be a university or a big corporation where they have a campus with multiple buildings. They need to connect those buildings where those buildings have their own specific separate local area networks, but they need to connect those together via a wide area link. Well, they're going to have something like this in place most of the time. And so you'll see connections like that between buildings. And one important note with this is that it does not provide redundancy. So we just looked at the mesh design. The mesh design provides redundancy. This one, if the network cable fails between these two devices, they can't communicate, and it kills the connection. And so that's the one thing to understand about a point-to-point, is that if it's going to be difficult for you to replace your cables, if it's underground or if it's in a tunnel, or if it's up in the ceiling, it might be more cost prohibitive for you to, sorry, not cost prohibitive, but it might be more efficient and more effective for you to implement two cables together and do a mesh instead of a point-to-point. However, on the flip side, if that's going to be cost prohibitive and it's easier for you to go ahead and replace the cable from time to time, or replace one of the routers, or replace one of the switches, then just go that route instead. So that's the point-to-point topology. Now let's talk about our last one. And this is really what we see in the networks. This is a hybrid topology. And so what's a hybrid topology? Well, this is pretty much what you're going to see in almost every network today. And it's a combination of a lot of the physical topologies combined. And so we're talking about implementing our mesh, our star topology, and our point-to-point topology, and other topologies all together into one. So, for example, I went ahead and just did a diagram over here, and this diagram includes a combination of a star topology, a mesh topology, a point-to-point topology, and they're all combined. And so let's go ahead and let's see if we can identify them. And we'll start with the star topology, and we'll use our arrow tools. So we'll make the star topologies green. So where is our star topology? Well, let me go ahead and put a box around here to identify star is going to be green. And we'll get our arrow out. Well, here's our star topology right here. Remember where we have our switch in the center and everything spreads out off of it? Well, this is our star topology where it connects to these devices here, and to the router, and to this other device here. So that's our star topology. And I'll go ahead and I'll just circle this like so. So where's our point-to-point topology? Well, there's a point-to-point topology as well. And there's actually, you could potentially say two, but really there only is one. And I'll mark this cyan. So here's our point-to-point. And where is our point-to-point network topology? Well, if you look hard enough, it's really, it's right here. Because it's a single point of failure between this part of the network and this part of the network. And so this is a point-to-point between both of these, even though this is still part of this star and this is still part of this star down here as well. But again, it's a point-to-point between both of these. Now let's talk about the mesh topology. And let me go ahead and pick a different color for the mesh. So we'll go ahead and use red for our mesh topology. Well, where's the mesh? Well, it should be easy to identify. And I'll go ahead and I'll use a box on this one as well. Here's our mesh. We have a full mesh here where everything is connected to each other device. This device is connected to here, it's connected there, it's connected to there, and so forth. Now we also have a partial mesh right here as well. So I'll go ahead and use an arrow to show you the partial mesh. So I'm going to go ahead and point right here. So if you notice the connections to our router here, we have a switch here, we have a switch here, and it can get out to the internet from here. It can get out to the internet from here as well. And so we have a partial mesh setup. Now you'll notice that I don't have, arrows going both ways to make this a full mesh, but it's only a partial mesh. So if this cable dies, the network can still come back around and use this to get back out to the internet. And if this cable dies, again, it can loop up through here and get out to the internet through here and go right on out this way to the internet. So this is our hybrid where we have a star, a mesh, and a point-to-point combination of physical topologies combined together to create one small network. And that's what you're going to see, and you're going to see that there's overlap. There's not going to be always a specific point where you're going to say, well, this is the point-to-point, and this is the mesh, and this is a star. You'll notice that this is a point-to-point, but again, it's part of this star. This is a mesh, but this is also part of a star as well, and this is a full mesh, and this is a mesh as well. And so that's why we call it a hybrid. But that's going to go ahead and conclude our introduction to physical network topologies. And before we end this video, I'm just going to recap. Remember, we talked about the star topology, which is the most popular one. We then talked about the mesh topology, which is good for high redundancy and fault tolerance. And then we talked about our point-to-point design, which we typically see in wide area networks. If you have any questions about this, please let me know. If it's still a bit confusing, I recommend going back through the video and watching it again, because it may not click the first time, and that's completely understandable. But if you do have questions after that, just go ahead and reach out to me and post a question on the discussion board, and I'll be happy to answer. And thanks for watching, and we'll see you at the next video. In this video, we're going to talk about physical network topology selection criteria, and we need to be thinking about this whenever we're designing a network. And it doesn't matter if you are working from home and you're setting up a home network, or you are studying to take the CCNA and you want to set up a network, or you work for a small organization or a big organization and you need to set up a network. Regardless, you need to think about what your criteria is, what your constraints are, and what resources you have available to you. So when we are looking to build out a network, we have to plan and design accordingly. And this is what this is all about. This is just a quick introduction to get you to think about your different constraints and your different criteria that you have to utilize. So let's go ahead and let's talk about it. So what's the first major criteria? Well, the first major one is it's a really important one. It is our cost. What's the cost of the network going to be? How much is it going to cost us? How much money do we have to spend? And what's going to fit within our budgetary constraints, and what's going to meet our requirements? So we always need to be thinking about the cost. We need to think about how much money we have, and we need to think about how we can get the best bang for our dollar, where we're going to get a positive return on our investment. Now, the second thing we need to consider is the ease of installation. And this, along with the ease of maintenance, I'm going to talk about them together. It all comes down to your level of expertise and the level of expertise of the IT and networking people that you're going to be working with. So you need to design a network that your personnel can effectively not only install, but they can maintain. The last thing you want to do is purchase equipment and hardware where your personnel can't set it up and you can't afford to have somebody set it up. And then even if you do get it set up, they can't maintain it because they don't have the knowledge. And the last thing we need to consider is fault tolerance. And so, if we're looking at a mesh versus a star versus a point-to-point, we need to consider what's our fault tolerance requirements. How much availability do we need to our systems and our network and our servers? And if the server goes down, how long can we be okay without having that server online? Do we need to have 100% availability? Or if we have outages, are we going to be fine if it takes us an hour or 30 minutes to get it back online? So you need to think about all these different things. And on the next slide, I really just came up with some very generalized questions that you can think of. And when we're thinking about this, the first step is to really evaluate your underlying requirements, like I talked about on the previous slide. And so these questions here are going to help guide you through that process. So for example, how many client computers will there be attached to the network? Because that's really going to determine the size of the network and how many switches and hubs you're going to need and what type of layout you're going to have. Again, how many servers are going to be attached to the network? That's going to have a huge impact again on how much cabling you need and how many different network devices you need to connect everything together. Another good question that we need to be thinking about is, what are the company's plans for future expansion? Is the company done expanding for quite some time? Did they just build out a new building and we are prepped for expansion? Or do we expect the company to continue to expand over the next coming years? Because if we do expect the company to expand, we need to build that into our network design. So maybe we buy bigger switches that have open ports that are available for expansion. Versus if we know that the company is already done expanding in this building, they can't expand anymore, maybe we just buy the switches that are the most cost effective and they're going to get the work done that we need. The next thing to consider is what type of applications are going to be running on your network. So that gets down to the speed, and we haven't talked about the different cablings and the different speed aspects of that, but that's something we need to consider. Are we just going to be sending Word documents and PowerPoint files and Excel spreadsheets across the network? Or are we going to be streaming media across our network? Are we a multimedia company? Or are we somebody such as like YouTube out there, or somebody that's going to have huge bandwidth requirements? Because in regards to the design and the equipment that we use, specifically the cabling, it's going to have a huge impact on that. The next question is, are we going to need a peer-to-peer, or should we do a client server? Again, we talked about what's involved in that, and there's pros and cons to setting up a peer-to-peer network versus a client server, and we need to choose which one's best for us in our scenario. The next one is, how much fault tolerance do we need to have in place? And we talked about that a bit earlier. So we need to determine how much availability and uptime we need, and if we're okay with downtime, and if we're not, then how much fault tolerance do we need to build into our network to make sure it's up per the availability needs that we need. And then the second to last question gets back to our budgetary constraints. So how much money do we have available? What's our budget? And what can we afford to build out? Because we can spec out a design, but if we can't afford it, then what's the point? And then lastly, what are the security considerations? So there's security devices that we can put on our network. We can have firewalls, we can have internet intrusion detection systems, intrusion prevention systems, and spam filters, and all sorts of different things. But do we need them? And if we need them, how much are they going to cost? So, these are just some of the general questions, and before you start designing and building out your network, you need to just go ahead and think about questions like these and start filling it out to give you a better idea of your requirements and your scope of your design. So that's my quick little introduction to thinking about your topology selection in terms of your requirements, your criteria, your constraints, and really using that to drive how you're going to design it. In the next few videos, we're going to be doing some follow along in class exercises where I have some scenarios that I created, and we're going to use those scenarios to create some virtual network designs. And now, since this isn't a real class where we have access to a lab and a bunch of networking equipment, we're going to have to do this on the screen. And so I'm going to be using software similar to Visio, and it's a web-based software. It's called Glyphy, and I'll be designing the network on there. And so my recommendation for you is that you can follow along either by using something similar to that, like Visio, or just get a pad of paper and a pen or a pencil and follow along that way as well. The whole goal is to really just start getting some repetition in regards to designing networks. So once we get further along in the class, it's going to be a lot easier for you. So let's go ahead and let's get started on the next video. Okay, so let's get started with our network design scenario number 1. You have been hired by a small company to set up a network in their new office, and they've given you a router, a firewall, a switch, and 3 different computers to set up. And your job is to design the network and to label the topologies that you use. So let's go ahead and let's get started with this. Okay, so I have my Glyphy software up and running. I'm going to go ahead and start pulling over the different hardware they're giving us. So here's our firewall. We'll go ahead and label that firewall. And they've given us a switch and a router. So here we go. We can use this as a switch. And let me scroll down to the routers. And here's a router we can use. And they've given us 3 computers. So let me scroll back up and we'll do a couple desktops and we'll do a laptop. And these we don't have to label. So I'm going to resize these a little smaller so they fit on the screen a little easier. Now let's figure out how are we going to design this. And this really gets back to our previous lecture where I introduced the 3 basic type of devices, where I introduced the router, the switch and hubs, and firewalls. And I talked about your basic design. So they've given us a router, a firewall, switch, and 3 devices, and we need to hook them up. So let's get back to the basics. Remember that the router always goes on the edge of your network, and the router you use to connect to wide area networks and other networks. So the router is going to be on the edge of your network, and this is going to lead out to, and we'll just put this here, we'll put the cloud, and we'll call that the internet. So let's just call this the internet. So your router is going to connect to the internet, and then the first thing that you want to have on the inside of your network is your firewall, because you want to protect all the data that's coming in or going out. So you want to keep the bad stuff out, and you want to make sure that you don't let out information that you don't want to let out. And so we'll go ahead and just connect these together. So firewall connected to a router, router connected to the internet, and then we have our switch. And let me get rid of this and get back to my arrow. So the switch is going to come in here, and remember we need to connect our devices. So our devices are going to connect to the switch. And so I'll just do this for a quick design, and we'll connect each device to our switch. And then we'll connect our switch to our firewall. And there you go. There's our basic design. So we have our 3 computers on the inside connected to our central switch, which then connects to our firewall, and our firewall connects to the router, which connects us to the internet. So we have our design in place. Now we need to list the topologies. Well, let's think about the first topology. Is this a peer-to-peer, or is this a client-server? Well, they didn't tell us, so we don't know. We don't know if any of these are server or not, but we're going to assume if they just said computers, it's probably a peer-to-peer design. So we'll just say peer-to-peer. We'll go make this a little bigger so it's easier for you to read. So we're using a peer-to-peer design, and now let's think about the actual topology. So let's go ahead and start marking this up, and let's go ahead and circle. I'm going to go ahead and circle this portion here. So off the top of your head, what type of topology is this? Well, we have a switch in the center, and we have these devices here. What is that? Well, this is going to be our star topology. And remember, the star topology always has a switch in the center. It's a central device, and everything connects on the outside. So star topology. And we'll go ahead and we'll bold this, and we'll make it a bit bigger so it's easier to read. I'll even make it bigger than the last one. So this is our star topology right here. There we go. And so if this is a star topology right here, well, what is this and what is this? Well, both of these are, you just have a single point to point here, and it's just a one-to-one link. So both of these must be a point to point. And that's exactly what they are. They are just single point to point. And so we'll just go ahead and put this in point to point. Again, we'll bold this and we'll make it a little larger. And we'll just do this. So we have 2 point to points. We have one here, one here. And we'll go ahead and bring this down over here as well, so it's easier to read. Now, one interesting thing here as well is that, well, what about this connection here? This is actually a point to point as well. Even though it's part of the star topology here with the switch, it's also a point to point for data coming in and data coming out, because nothing can get to the router unless this is connected. So we have a point to point in 3 different spots. So we'll just bring this up here, and I'm going to use my nice little arrow tool. So we have a point to point here, we have a point to point here, and we have a point to point here. So it's not just having a point to point here and here. This is really a part of the point to point, even though it's part of the star topology. So that's going to go ahead and conclude our first simple scenario number 1. And if you remember, this is going to look just like our first design that we went through, and I explained what a router was and a firewall and a switch was in a previous lecture. And if I pull up my PowerPoint deck, let me show you what we should have. And let's jump to the next slide. And there you go. So this looks similar to what we just created. We have our three systems. We have our switch, we have a firewall, we have our network router, we have our star topology here, we have a point-to-point here, a point-to-point here, and a point-to-point here. So if you have any questions about this, please let me know. If not, thanks for watching, and we'll see you at the next video. Okay, so here's design scenario number 2. An investment firm is headquartered in Los Angeles, and it's in the process of opening up another office in San Francisco. And it wants to be able to securely communicate between both offices. So what type of physical topology are we going to recommend? So they didn't give us all the information, but let's assume if this company wants to do secure communications and its network is going to be spanning from Los Angeles to San Francisco, we must assume that they have some money and it's a fairly large corporation. And we really have a couple of different options. And so our first option is going to be a simple point-to-point, where we have a single line coming from the first router all the way to the other router where it is a secure leased line. However, there's an issue with just doing a single line. Remember that we're going to have a single point of failure if we do that. And we don't want to have a single point of failure. In fact, we want to probably have some sort of redundancy built into place, because if we have our headquarters in Los Angeles and we have a satellite office in San Francisco, we're going to assume that they're probably going to communicate back and forth on a daily basis and on a regular basis. And if we have any sort of downtime, it's going to hinder the business. So we could do point-to-point, but it's going to make a lot more sense if we do a mesh where we have two redundant lines. So if one of the lines goes down, at least the other one is up and running and they can still communicate. So we're going to have a secure leased line. We're not going to be using a public line. We're going to go to an internet service provider and say, hey, look, I need to get a secure line from one firm location to the other one, and I'm located in Los Angeles, and I need this one to go to San Francisco, so what can you offer me? And they're going to say, well, we can do a point-to-point or we can do a mesh. What do you want? And, you know, if we want it to be secure, if we want to have redundancy, if we want to have fault tolerance, and if we don't want to have downtime, then we're going to want to go with not the point-to-point, we're going to want to do a mesh between these two different lines. And we're going to pay a little bit of extra money, but for that extra money, you know what, we're going to have a lot more availability and uptime than if we only had one line and it went down. So, simple scenario here, two different options, just got to pick the one that best fits. Okay, so on to our final network design scenario, scenario number 3. So in this scenario, we have a university professor named Dr. Smith, and he currently has a lab set up in the university, and in that lab he has 3 desktops that are connected to a network switch, and it looks like this. He purchased 3 new laptops and he wants to connect those to his network. However, he doesn't have the equipment to do so, and he needs your help, and you're one of the IT staff members. And so he came and talked to you and he said, okay, well, I have a switch and I have a wireless access point that you can use, and I can help you set that up. And he says, okay, great. Well, I still need to be able to connect to other networks on the network here in the university, and I need to get out to the internet as well. So he's asking you to design a network for him, and so our goal here and our job here is to design a network solution for him. So what are we going to do? Well, let me go ahead and pull up Glyphy again, and we can go ahead and design him a network. Okay, so I have Glyphy up and loaded, and in Glyphy I have the standard design in place. So we have his current lab setup, his 3 computers, and they're connected to a 4-port switch. So that means we have one more port on here that we can use. And this is all the new items that he has. 3 new laptops, another switch, and a wireless access point. So what should we do? Well, first thing we need to do is we need to connect to the current network. And so what we're going to do is we're going to take the new switch, we're going to go ahead and we're just going to connect it to the old switch. And that way, that can communicate with the rest of the network. And now the next thing we can do is we can go ahead and we can scroll down and we can take our wireless access point over here, and we can use this to connect to our laptops wirelessly. because all these new laptops are going to have wireless connectivity built in with Wi-Fi. And so we don't have to use cable space, and because they are Wi-Fi capable, then you can freely move around in the lab and still be connected to the network. And so what we're going to do is we're going to connect our wireless access point to our switch here, and then that'll be able to communicate out to all these devices Wi-Fi wise. So unfortunately in this software I don't have symbols to signify the airwaves. So what I'm going to do is I'm simply just going to go ahead and draw some lines that are getting bigger as they get closer to them, and that's going to signify the Wi-Fi signals. And so what this does is just going to sound the signals and they can communicate back and forth. So we have a majority of the network in place. We have our 3 laptops now be able to connect, and they can communicate with these systems over here. We used up all the 4 ports here on this switch. We have this other switch over here. We've only used 2 ports, so we have more available ports. So he also stated that he needs to connect with the rest of the campus network and the internet. Well, simply what we're going to do is we're going to use this to signify that this is campus network and internet. And since we can assume that the campus network is just one large network, we don't need a router, and we're not going to tell him that he needs a purchase router. We're simply going to say, okay, well, we can just connect here from the switch out to our network, and it's going to do everything else that we need to do. And so there we go. Here's our design. It's set in place. This is pretty much the only design that we're going to be capable of doing when we have this setup, where we have our wireless access point here. And I'm going to signify this as just WAP for wireless access point. And then we'll call this switch as well. And there we go. And the reason for that is typically with the wireless access point, it's just going to have one port on the back, and it's going to extend the signal out. And the way that this works, this is not a point-to-point, but it's a point-to-many. So this is not really a star design. This is a one-to-many type of relationship. So this connects out, and there's only one signal. But if this signal goes down, then they're all going to lose connectivity. It's not like having a separate cable where if the signal goes down, then one of them is going to be able to communicate and the other ones aren't. If whatever's going out here and releasing out this signal, if there's a mechanical or electrical issue that goes wrong in there, then the wireless access point is going to stop working altogether. So that's how the wireless access point works. And we have our other switch here, and this goes out to the campus network and internet, and we are good to go. So we can say, here you go, Dr. Smith, your new lab is set up. We have everything connected. Here's how you're going to connect your laptops. You're going to connect them via Wi-Fi, via this wireless access point, and you're going to be able to communicate with your 3 remaining computers that are already on the network, and everything can get out to our campus network, and then from our campus network, you can get to the internet. So if you have any questions about this, let me know. If not, thanks for watching, and we'll see you at the next lecture. Now that you've made some pretty good progress in this course, if you like this course, I'd very much appreciate it if you could leave a nice review of the course. And if you don't like the course, I'd appreciate it if you could send me a message on Udemy and tell me what you don't like about the course so I can improve it over time. The reason that I'm asking for this is that number 1, reviews help me as your instructor, and number 2, I'm always looking to improve my courses. So any sort of feedback that I get, whether it's good or bad, as constructive criticism is going to be beneficial to me as your instructor. So I really hope that you're enjoying the course. Thanks for watching this video, and let's continue with the course. We're going to kick off our discussion talking about network devices by revisiting the network interface card. And I know that we've already talked about this, but I think there's merit in revisiting it. So we're going to spend a couple of minutes just to solidify your knowledge of a network interface card. So the first point is that the network interface card is what's installed on your computer. It's either built into the motherboard, or it's going to be an expansion card like this one right here, where it plugs into the motherboard right here. And its main role is you simply use it to plug in the network cables into the ports and allows you to communicate on the network. And what happens? Well, we have electrical signals that go in and out of this port, and that's our data that goes out onto the network and the data that comes back to us. Now, in regards to its acronym, the acronym NIC is going to be used a lot in the IT world and networking world. So if you hear NIC, just remember that stands for Network Interface Card. Now, in regards to how it looks, it can come in all sorts of different shapes and sizes, and it can look like a USB thumb drive. It can look like a standard one. It can have a Wi-Fi connector. I mean, they really have all sorts of designs. And in fact, I even have one now where it's literally the size of this right here, where there's just a little tiny piece coming out the end where you can pull it out. It looks like the ones for your wireless mouses where you plug them into your laptop, and literally that's all it is. Now, this is going to be your standard one where it's an expansion. This is going to be a standard one where it's an expansion as well, where this is cabled and this is Wi-Fi. However, when you get into the server world, you are going to need a higher level of redundancy, and you're going to see network interface cards where they have 2 ports, so it has redundancy built in. So if one of the ports go down, or if the cable breaks or there's an issue, then the second one will take effect. And we're talking about things like file servers and web servers where you want a high level of redundancy and uptime. So, just don't think of a network interface card as something like this, where it has a port or something like this. It can be a little tiny USB thumb drive where it plugs in, or it can have multiple ports. So that's our quick refresher on network interface cards. In this video, we're going to talk about hubs. And before we get into all the details of what a hub is and how it works, the first thing I want to tell you is that we don't use hubs anymore, and we replace them by switches. However, we have to understand why we don't use hubs. And for those of you that go and you decide to work in the IT world, if you go and you are desktop support, or if you're a network support, you may encounter hubs in use, or you may encounter them just sitting in storage. And if you don't know the difference, if you don't look at the details, a hub looks just like a switch, and you may end up accidentally putting a hub in use when you shouldn't be using a hub. So with that said, let's go ahead and let's talk about hubs. So like I said, we don't use hubs anymore. We used to use them a long time ago. They were used in early networks, but we now replace them with switches, and we'll talk about that in the next lecture. So we don't use them because they're inefficient, and they are what we consider a multi-port repeater. So what do I mean by multi-port repeater? Well, when traffic goes into one port, one physical port on this hub, it is repeated, meaning it's sent out on every other single port. So for example, if we have computer 1 here and it wants to communicate with computer 2, if it tries to send data out its port and it wants to get it to computer 2, the hub is what we call a dumb network device. It doesn't try to memorize anything at all. It doesn't know where that data is supposed to go. Instead, it really doesn't care. What it does is instead, anywhere where there's a network cable plugged in, it sends that data out onto every single port. And so computer 3 over here is going to get that data, and computer 4 is going to get that data as well. And what that ends up doing is that it makes the network very congested, so you can have lots of packets of data going across. So if you imagine computer 1 needs to communicate with computer 2, computer 2 at the same time is trying to communicate with computer 3, and computer 3 is trying to communicate with computer 4. Every time each device is trying to send data out their port, this hub is taking that data and it's sending out every other single port. And so what we have is that we have data just going everywhere onto every single port. And in the networking world, we call this one big collision domain, because when we have this happening, we have to have safeguards in place to prevent data from hitting each other while they're on the wire. And so we have packets of information going back and forth. The last thing we want is for them to collide and have a collision where that data is lost. And so it makes it very inefficient. It makes it very slow. And there's also a security concern. If computer 1 has information that it only wants going to here, where potentially it has sensitive information, well, if you have a hacker listening on the network over here, maybe tapped into this network wire, when this data comes out here, then the hacker can get it. And so with all that said, the big takeaway is that a hub is much less efficient than a switch, and we'll talk about why that's so. And just be aware that you are going to encounter these from time to time if you ever work in the IT world. So that's what a hub is. That's our quick introduction. In the next lecture, we're going to take a look at switches, and after that, we're going to compare hubs to switches, and you'll really get an idea of why switches are so much better than hubs. So we talked about hubs in our previous lecture. Now let's talk about switches and why they're so much better than a hub. So first thing we need to look at is we look at the image here. This is a switch. The previous lecture had an image of a hub, and my question to you is, can you tell the difference? Do they look any different? Well, for the most part, no. They look almost exactly the same. And so that's why we need to know the difference between a switch and a hub, and we need to be able to identify if it's a switch or a hub. So you're going to have to look on the actual switch itself and look at the model number and pull it up to determine if it's a switch or a hub. Because if you don't, you can accidentally use a hub, and we don't want to do that. So let's talk about the differences. Well, the big resounding difference is that a switch is what we call an intelligent network device. So remember in our previous lecture, I said that hubs are nothing more than dumb network device, and they're multi-port repeaters. So any data that comes in on any single port goes out all the other ports. However, a switch doesn't do that. A switch memorizes MAC addresses. And I'm going to highlight this. So for each single device on the network, remember that network interface card has a MAC address built in. And remember that I said before in the course that we use MAC addresses for communication within our local network. Well, that's where switches come into play, because switches use MAC addresses to communicate. They don't use IP addresses, they use the MAC address. And let me go ahead and write this in so this makes sense. So I'm just going to type in MAC address, and let me get this into a better color. So I'm going to just type in MAC. So when we're talking about switches, we use our MAC address to communicate. However, when we're talking about routers, we use our IP address, and we'll get into that later in the course. So getting back to this, these switches are going to memorize the MAC address of each device, and what they do is that they put that into the MAC address table. So if you just think about a simple Excel spreadsheet with two different columns, one for the computer number or the port number on the switch, and another one for the MAC address, well, it's simply just going to fill in that table, and it's going to have a table of MAC address information that's assigned to each port on the switch. And really, that's how it works. And so we have our MAC address table, and what it does is that it pays attention to both the source and the destination MAC addresses of any communication on it that's going on in the network. And I'll do a quick example once I get done with this. Now, the really great thing about this is, since it doesn't flood all the ports because it knows the MAC addresses, it only sends data to the assigned port. And so it breaks up these collision domains that we talked about that happen with hubs, where data, because it's going everywhere, we have potential collisions going on all over the place because our traffic is congested all across our network. However, with switches, data only goes to where it's supposed to go, and we don't flood all the ports. So it's much more efficient, and it breaks up these collision domains, and it's also much more secure. So let's do a quick example. So let's say we have computer 1, computer 2, computer 3, and computer 4. So let's say we just turned on our switch. It's brand new out of the box. It doesn't know anything. And let's say computer 1 wants to send a file to computer 2. Well, what happens? Well, the very first time that it boots up, this doesn't know. So it sends a request. It says, hey, it sends a request to all the computers on the network, and it says, hey, are you this computer? Are you this destination with this MAC address? And then this computer is going to respond, and then it's going to record it into its MAC address table. And as they all communicate, it's going to do that process, and only the computer that is the proper destination address is going to respond and says, yeah, that's me here. I'm on this port. And so over time, and literally in a matter of seconds, it's going to fill in this MAC address table. And so within maybe a minute of it booting up, or even less, that's how quick this happens, it's going to have this MAC address table populated. And so as you start communicating out on the network, and for example, if you want to send some data from computer 1 to computer 2, it's not going to flood all the ports. So it's going to go into that port, and it's going to come out of this one, and it's only going to go to number 2. So we're not going to be flooding everything else and causing all these collision domains. So that's the great thing about a switch. And I'm going to revisit this, and I'm going to talk about this process in detail as well, about how it works. But I really wanted to introduce this to you and let you know how a switch works and why it's so much better than using a hub, and really understand why it's our standard. It really is our standard in our network infrastructure today. Everybody uses switches because of how they work. So if you have any questions about this, let me know. But before you ask questions about switches, just continue to watch the next couple of lectures, because I'm going to talk about how this works in detail in a couple of lectures. So thanks for watching, and we'll see you at the next lecture. In this video, we're going to spend a few minutes to just recap on hubs and switches and to look at the differences, because I really want you to understand the differences side by side now that we've talked about hubs and switches separately. So let's start off talking about the hub. So remember, the hub is a dumb device because it floods all the ports. It doesn't know where data is supposed to go. It doesn't care. So anything that comes in any of its physical ports on the hub is going to go out every other single one where there's a cable connected. And we call this a layer 1 device for the OSI model. And layer 1 is really the lowest level, and the reason why we call it a layer 1 is because at this level we're dealing with nothing but the actual electrical signals, and since a hub doesn't care where data goes and it's not intelligent, it just floods everything with electrical signals. So for that reason, it's a layer 1 device. Now because it does all this, it's very inefficient, and we get a lot of collisions on our network, and because we get a lot of collisions on our network, we have decreased speeds. And also we have security issues because data is going out to every single port, so it's easier for somebody to be eavesdropping, and for somebody such as a hacker that got onto our network, it's easier for them to get that data from us than if we're using a switch. Now let's look at the flip side. So now let's look at our switches. So in comparison, a switch is an intelligent device because it's not flooding the ports. It learns the ports by MAC addresses and records them in a MAC address table. And once it has that data in the MAC address table, which is very quickly, it only sends the data to where it's supposed to go. So it knows what MAC address is on which port, and so when a data packet comes in and it says, look, this needs to go to MAC address XYZ on port 2, it'll send it there. And it is a layer 2 device. And so why is it a layer 2 device? We haven't talked about this yet. Well, it's a layer 2 device because layer 2 is all about our MAC addresses. And since it deals with MAC addresses, it is a layer 2 device. It is efficient because of all this that it does up here. It doesn't flood the ports, it's efficient. That leads to higher speeds on the network. We have less collisions, and we're more secure against hackers and eavesdroppers. So that's the difference between hubs and switches in a nutshell. In the next lecture, I'm going to revisit switches, and we're going to go into detail and talk about how switches learn MAC addresses. In this video, we're going to go ahead and we're going to revisit switches. However, we are going to be focusing on how switches learn MAC addresses. And I'm going to be giving you a broad overview of how this works. Now, I'm not going to go into all the detailed steps, so we are going to leave some things out, but I'm going to cover all the basics so you have a good idea of how switches work. So let's go ahead and let's get started. The first thing we need to know is that switches learn MAC addresses by a source MAC address. And this will make more sense as we go through this. Another thing that you need to know is that whenever you send a packet of information out on a network, it's going to include two key things. It's going to include a source MAC address, and it's going to include a destination MAC address. And the easiest way to explain why we're doing this is if we just think about emails. Whenever you send somebody an email, you're going to include who it came from, that would be the source address. And when you send your email to the email server, you're going to include the destination email address where you want it to go to. And so when we're talking about any sort of information going on a network, it has to have the source MAC address so the switch knows where it came from, and it has to have the destination MAC address so the switch knows where you want to send this information. So now let's get into the process of how it works. So let's say that this switch here is a brand new switch, and we just plugged it in, and we plugged our 3 computers into it on the network, and its MAC address table is completely empty. There's nothing in there. And what we want to do is that we are on computer A and we want to send a packet of information to computer C down here. And so our goal is to get our information down here to computer C. So let's go ahead and let's walk through this process. So when the switch receives the packet of information from computer A, what it's going to do, it's going to look in its MAC address table and it's going to see if it has anything recorded for computer C. So it's going to look in here and it's going to say, well, is computer C with the MAC address of CCC, is that on port switch 1, 2, or 3? And because it's empty, it doesn't know. Now it does know, however, because computer A sent it a request that on port 1, because this request came from port 1, it now knows that the computer on port 1 is going to be computer A with the MAC address of AAA. And so it's going to go ahead and record that in this table here. And this is a simplified table to show you how this works. And also, these are not real MAC addresses. Remember in the previous lecture, a MAC address is hexadecimal, and it looks nothing like this. I'm just using these very simple ones just for the sake of space on the screen and for the sake of the explanation to make it much more simplified. So getting back to that, so now it knows that this computer is on port 1 and it's going to record that in the MAC address table. However, it doesn't know where computer C is. So what it's going to do is that it's going to flood all the ports. So it's going to send a request out to port 3 and port 2, and it's going to say, hey, I have a packet of information for destination address, MAC address CCC. If you are this computer, respond and let me know. Well, computer B on port 2 is going to say, well, I am not that computer. My MAC address is BBB, so I don't need to respond. So it's just going to go ahead and disregard that packet of information. It's not going to respond to the switch. Now, when computer C gets it on port 3, it's going to say, okay, well, wait, that matches my MAC address, so I'm going to go ahead and respond, and it's going to respond to the switch and say, yeah, that's me. I am on port 3. And what will happen is, if we jump to the next slide, what will happen now is that since C acknowledges that request, the switch is going to say, okay, well, now that I know CCC is on port 3, I have that information, and now we have that information, and whenever computer A wants to communicate with computer C, if a data request comes in, we're just going to send it out to this port only, and we're not going to send it out into any other ports. And same thing, if we have a request coming from computer C up to computer A, again, it's just going to come up, and it's only going to go out to port 1. And that's how the process works. I did skip some of the detailed steps, but that's just really how it works in a nutshell. So if the switch doesn't know, first off, where it is, it's going to go ahead and send a request out to all the ports, and only the correct computer is going to respond, and it's going to go ahead and populate this MAC address table, and then from that point on, communication is only going to happen where it should happen. And so the same process is going to happen for computer B, and if we have more computers on here, again, the same process is going to continue to happen to the point where this MAC address table is completely filled out. And when it is completely filled out, any sort of data request going from one computer to the other is only going to be going out the correct port. It's not going to be going out to other ports. So for example, if computer B was eventually memorized and it's trying to send data down to computer A, again, it's only going to go out to port 1. It's not going to go down to port 3, and it's not going to flood it. And so that's why a switch is an intelligent device, because it learns where the MAC addresses are and it assigns them to the proper port. And instead of flooding information out to every single port, it only sends information where it's supposed to go. So that's our quick introduction to how switches learn MAC addresses and how they work in a nutshell. If you want to find out all the specific details, I highly recommend that you just go out to YouTube and you do a search for this, because there's some really great videos on here, especially for some of our networking exams like the Network Plus and the CCNA, where they go into great depth and they tell you how this works. But this is more than good enough for this course. And again, if you have any questions, as always, let me know. If not, thanks for watching, and we'll see you at the next video. We are going to talk about wireless access points in this video, and the first point I want to make is that it's not a wireless router. So this image here may look like your wireless router in your house, but a wireless access point is not a wireless router, and it does not work like a wireless router. So let's go ahead and let's talk about it. So what do I mean? If it doesn't work like a wireless router, how does it work? Well, we can think of it as a bridge. So what do you mean by bridge? Well, if we think about how a bridge works, it allows you to communicate from one side to the other by creating a bridge. And that's how this works. It allows us to extend a wired network onto a wireless network. So if you think about our previous in-class scenario that we did earlier in the course, where we set up a lab and we hooked up a wireless access point to give access to 3 different laptops, we hooked that up to the switch and we extended out our wired network into a wireless network. And you're not going to see wireless access points in home environments typically, but you are going to see them in enterprise environments. So I've worked with them before. When I worked at a university, we've set them up in basements where our facilities management didn't want to bring a lot of cabling down simply because it was difficult, because it was pure concrete. And we set them up in different student areas where we wanted to provide additional Wi-Fi access to certain rooms. And so you are going to see it in a business environment. Now, you can think of it as a wireless switch. However, it's going to have security safeguards. So it's going to be secure just like your wireless router at home. It follows what we call the IEEE 802.11 standards, and this talks about the encryption standards that we have when we set up our wireless routers at home. So it follows those same encryption standards. And so think about it as a wireless secured switch that extends a certain subportion of a network. But it doesn't have all the features that you have at home when you have your all-in-one wireless router. So that's what a wireless access point is. We're not going to be covering wireless networking in this course in detail, but if you do want to find out more about wireless access points, I do recommend that you go out and you do some research on your own. In this video, we're going to talk about basic routers, and we're going to start discussing the concept of what routing is. So what's the purpose of a router, and what do we talk about when we're saying we're routing information? Well, the main purpose of a router is that it routes traffic from one network to the next. So it's designed to connect different networks together. And so we connect different networks together with routers. And if you remember in some of the previous lectures, I talked about how the router goes on the edge of the network and how we use it to connect to a wide area network. Well, when we're connecting to a wide area network, we're connecting to different networks. Now, another thing about routers is that they don't use MAC addresses. They don't care about MAC addresses. They only operate based upon IP addresses. So our switches within our local networks, they use MAC addresses for communication. However, once data goes to the router and we try to get information or we try to communicate across a wide area network like the internet with another network, we have to use IP addresses for both our source and our destination. And we're not going to talk into a high level of detail about how this works in this course because it's beyond the scope of this course. We're not going to talk about how all these different routing protocols work, but just understand that routers use what we call intelligent decisions. And when we're talking about intelligent decisions, we are talking about using different routing protocols. So there's a number of different routing protocols in place that routers can use, and based upon the scenario and how the network administrator feels is the best way to set up their network, they will choose a specific type of routing protocol. And what the routing protocol is going to do, in a nutshell, it's going to find the best way to get this packet of information from one network to the other. And there's different metrics that they can use, and it's going to look at those metrics based upon what protocols are in place, and it's going to say, okay, this is the best way to get here, this is how I'm going to get here, and this is how I'm going to deliver this information. Now, a router communicates on the OSI layer 3, and so we'll take a look at that right now. And so, for example, I have layer 1, layer 2, and layer 3 side by side. And so let's go ahead and let's talk about these again. So remember, let's start at the bottom. So our hubs are our dumb devices, remember that? And remember, they don't use any sort of intelligent type of decisions whatsoever. They just send out electrical signals. So we're just going to do electrical signals here. So they just send out the electrical signals and nothing else. A switch, on the other hand, they communicate with MAC addresses. And so that's layer 2. And then layer 3, they communicate with IP addresses. And so that's the difference. By the time that we get up to layer 3, routers are going to communicate with IP addresses. On layer 2, once we get a little lower, switches are going to communicate with MAC addresses. And hubs on layer 1, it's just electrical signals going out. So that's what a basic router is, that's what it does, and that's how it works. We're going to talk a bit more about how we send packets and how they get forwarded from one network to another in this section. However, we're not going to go into details, and we're not going to talk about the different types of routing protocols, because simply that's beyond the scope of this class. So thanks for watching, and we'll see you at the next video. In this video, we're going to do a brief introduction to how the packet routing process works. So I know that this is an introductory course to computer networking, and I'm not going to go into details on how routers work and how different routing protocols work, but I didn't want to leave you without really knowing how the process worked from a high level perspective. So that's what we're going to do in this lecture. We're going to do just a short introduction so you have a good idea of how routers work. So let's go ahead and get started with our example. So in this example, we have computer A and we have computer C, and you'll notice is that they're on separate networks across the internet. Well, let's say that computer A wants to communicate with computer C. How does the process work? Well, let's go ahead from the very beginning. If we look at computer A, let's say computer A wants to send a packet of information to computer C. Remember, the first thing that we need to understand is that it's going to include the source address and the destination address. When computer A looks at the destination address, it knows by looking at it that it's not on the same network. It knows that computer C is not on the 192.168.1.55 network. Instead, it knows that it's on the 205.115.15.25 network. So instead of sending it to the switch to send to a local device on the network off the switch with its MAC address, it's going to send it to the router. And we call that sending it to the default gateway. And so why do we call it the default gateway? Well, we call it the default gateway because our router is our gateway to get out to other networks. It's our gateway to get out to the internet. In this example, it's our gateway to get out to wide area networks. In other examples, and we just need to understand that it's our gateway out of our network onto other networks. And so that's why we call it the default gateway. And whenever a computer wants to send information out of its network, it puts in the packet information. It says, hey, you know what? I need to send this packet to our default gateway. I'm not sending it to a device on the local network. So the switch knows to send it to here instead of some other device on the local network. So once the router gets that packet of information, it looks at that destination address. It looks at it and says, okay, this needs to go to 205.115.15.25. And it's going to use routing protocols to determine the best way to get it there. And there are different routing protocols, and there's different routing protocol metrics set in place. And it's going to use either one specific metric or a combination of metrics to determine the best way to get it there. And when I'm talking about metrics, I'm talking about things like the fastest route there. Maybe we're talking about the actual distance, or we're talking about the speed of the link, or we're talking about the status of the link, meaning how congested it is or not. And so there's just a wide array of different routing protocols, and we're not going to talk about them, but I just want you to understand that it's going to use routing protocol metrics that it's configured to use to determine what it thinks is the best way to get that information there. So when we say the best way, we're talking about the most reliable and the most fastest way. And so what happens from a high level perspective is you see once it goes from this router, it goes out to the internet, you notice that it goes from router to router to router to multiple different routers until it reaches its destination. Well, what we call that when it goes from one router to the next, we call that a hop, and I have this down here and I'll go ahead and I'll underline it. So every time we go from one router to another router on the internet, that packet of information is going from one hop to the next. So whenever you hear a hop, it means it's going from one router to another router. And the way that it works is that once router 1 finds the best way for it to get there, it finds the best way for it to get to the next router to get it there. And so once it takes that information, it's going to do this hop. And let me go ahead and change my pen color so this makes a bit more sense. So you don't, again, not going to see red on all of them, but it's going to go from here and it's going to go to this one. And now it's the duty of this next router to determine the best way to get that there. Once it gets to that router is going to look at it and it's going to say, well, is this for my network? If it is, I'm going to go ahead and send it to a switch to my network and we're going to deliver it. If not, I'm going to figure out the best way to get it to its destination. And so every time it goes from one to the next, this entire process restarts itself. And each router is going to determine the best way to get it there. And it's just going to continue doing hops until it gets there. And you'll notice in here we have multiple different hops. So we have one hop here, a second one here, a third one here, we have a fourth one here, a fifth one here, and finally a sixth hop here until it gets to the destination router. And this router is going to look at it and say, oh, hey, this packet of information, this is designed to go onto my network. This is designed to go to 205.115.15.25. That's my network, so I'm not going to send it off to another router. I'm going to send it to my switch, and we're going to deliver it to computer C here, and computer C is going to get that packet of information. And so when computer C wants to communicate back to computer A, if computer C does, it's going to do the exact process, but it's going to go backwards. And so that's just a high-level perspective of how this entire process works. Again, I didn't go into tons of details talking about how this works. We just did a high-level overview because I want you to have an idea of how it works. If you want to have a really good understanding of how this works, then my recommendation is to do further study outside this course. There's some great networking books that I can recommend to you if you let me know, or you can simply go out to YouTube because there's tons of great resources out there as well. So thanks for watching, and we'll see you at the next video. In this video, we're going to revisit the role of the firewall. And so we talked about what a firewall was in a previous video, but we're going to go ahead and revisit it again. So what is a firewall? Well, it has one major role. It wants to keep malicious data out of our network. And that's its main goal, is really we don't want malicious data to get into our network, and it's going to do whatever it can to keep it out. So it protects our local area network against malicious data, mainly from the internet. And why am I saying mainly from the internet? Yes, malicious data can be within our network already, but when we think about it, our internal network is considered a trusted network. However, everything out here on the internet, we don't know anything about, so we consider that untrusted, and we don't trust anything that comes in. Everything has to be inspected as if it was bad and malicious data. So that's why we're really concerned with the internet, because for the most part, if we trust our people within our network, then it should be a trusted network. However, we cannot trust anybody out here on the internet at all. So it prevents unwanted network traffic on different networks on the internet from accessing our network, and vice versa. It essentially controls the flow of information in and out of our network. And so if you think about it, that is 100% true. So we have information coming in, we have information going out. However, we have rules set in place on our firewall that's going to allow only a certain subset of information to come in or to go out. And so we could have certain rules that disallow certain types of packets to come into our network or certain types of packets to go out of our network. And how that works is that you simply set up network access rules. And those are set up on our firewall, and we use those to maintain how the firewall is going to behave and how it's going to protect our network. Now, we're not going to go into detail, and we're not going to talk about the different types of firewalls, but I am going to say that a firewall can be a standalone network device, or it can be software on your computer system. So if you're on a Windows machine, you should know that you have a built-in firewall software built into your Windows operating system. Every single one does. And so we can have client-based firewalls on our network as a level of defense, and we can also have our network firewall as well as a level of defense. So that's our quick introduction to a firewall. If you have any questions, let me know. If not, thanks for watching, and we'll see you at the next video. So I keep referring to your home router and your all-in-one router and your wireless router throughout this section, and now we're going to talk about that. So remember, in our first few lectures in the course, I talked about SOHO devices, your small office, home office device. Well, you know what? That's what you have at home, and now that you know about everything that we talked about in this section, now that you know what a router is, a firewall is, a switch is, a wireless access point is, and a DHCP server is, now you know what a SOHO device is, because a typical SOHO device has all this functionality built in. It is a router, it is a firewall, it is a switch, it is a wireless access point, and it's a DHCP server all in one. And it may even have additional functionality built in. So these devices are really smart. A SOHO device has all this functionality, and if you ever want to take a look at its configuration settings, all you need to do is go to the administration console for it. And you can look up its firewall settings. You can look up how it manages its IP addresses. You can set your security settings for the wireless access point, and also you can set the name for it. You can look at some of the switching settings, and potentially you may even be able to look at the MAC address table. And you may even be able to look at how it's routing information. So I just wanted to go back and revisit this because I've been talking about this throughout this section, and I mentioned the SOHO device earlier in the course. Now you know what it is. And so if you think about it, you can go down to Fry's, you can go to Best Buy, you can go to Amazon.com, or you can go to Newegg.com, and for $40 to maybe $100, you can go buy a really great SOHO device for your home or for your office, and you're going to get all this functionality within one. And so if you think about it, if we go back to our discussion on setting up a small office network with a peer-to-peer network, you see why having something like this makes it so powerful, because you have your all-in-one device there, and it makes setting up a network super easy and super efficient. So that's going to go ahead and conclude this lecture and this section. Thanks for watching. If you have any questions at all on any of these devices we talked about, let me know. If not, thanks for watching, and we'll see you at the next lecture. This section is all about network cabling, and so it only makes sense to kick off our discussion talking about the importance of network cabling. And I want to spend a couple of minutes to talk about this because when a lot of people think about networks, they don't focus on the cabling, but instead they focus on the hardware. They focus on the routers, the switches, the firewalls, and all the devices that connect to the network. And in fact, in this class so far, we really haven't talked about network cabling at all. We focused on all the other aspects, but we haven't focused on this yet. So we're going to spend a couple of minutes and we're going to talk about why network cabling is important. So why is it important? Well, first of all, it's important because it's the backbone of your network. And you need your cabling to be set up properly. You need to choose right cabling, and you need to make sure that it's functioning properly for your network to operate. And if the cable doesn't work, meaning it doesn't operate properly, it doesn't meet your requirements, or maybe it's just broken, then your network's not going to work either. And then lastly, we've moved to wireless networks, and a lot of people have wireless networks set up in their organizations, in public spaces like Starbucks, and in their homes. But we need to remember that a wireless network also uses cables too. And so at some point in that network, there's a physical cable that plugs into that wireless device. And if that cable isn't working, or if it doesn't meet the right requirements, then that wireless network is not going to work either. So for all these reasons, that's why network cabling is important, and that's why we're going to spend time in this section and we're going to be talking about network cabling. So let's go ahead and get started with that in the next lecture. In this video, we're going to do a quick introduction to the different types of networking cabling that you're going to see out in the networking world. And the first one is coax cable. So coax cable is not a very common networking cable. In fact, it was used quite widely in early networks, but you rarely see it in use today. And in fact, the only place that I've ever seen it used is where I get my TV through a cable service provider and my internet is through them as well. And so I get both my cable service through them, and also my cable modem hooks up through a coax cable. But from then on out, my network does not use that. So that's the only place I've seen it used. You may see it from time to time being used in other instances, but it's highly unlikely. So that is coax, and we're not going to be talking about coax in detail in this course because simply we don't use it and it's not a prevalent type of networking cable. Now the second one is twisted pair. And twisted pair is going to be quite familiar to everybody because this is the most popular type of networking cable being used today in modern networks, both for home networks and for enterprise and business networks. So if you go ahead and you go to Best Buy or you go to some other store and you buy a new cable modem or cable router for your house, it's usually going to be packaged with this type of a cable. Or if you're in the office and you had to hook up your laptop, you're going to see this type of cabling. So this is the most popular type and the most common one that we're going to be familiar with. Now the third one is a newer type of networking cabling, and it's not that new, but for people that aren't in the networking world, you probably have not heard of this either. This is fiber optic. And fiber optic is a newer type of cabling. It's a lot more expensive. However, it's a lot faster and it spans much wider distances than any of the other cabling types. And so this is becoming more prevalent, and you're going to see it both in home networks and also in enterprise networks. So those are the three different types of cables. We have coax, twisted pair, and fiber optic. And we're going to be talking about in detail, we're going to be talking about twisted pair and fiber optic in future lectures in this section. So let's go ahead and get into it. In this video, we're going to talk about twisted pair copper cabling in detail. And so let's go ahead and let's get into it. So what is twisted pair networking cabling? Well, it is a cable that is coated with 4 different pairs of twisted cabling in it. And you'll notice that we have 1, 2, 3, and 4 different pairs. And what you'll notice is that they are color coded differently, and one of them has stripes and one doesn't have stripes. So why is that? Well, with each pair, there's going to be a positive and negative electronic signal, and so they balance each other out and they complete a circuit. And so that's why there's a positive and negative for each one. Now, a bigger question is, why are they twisted together? Because you could easily just create this network cabling and bundle it together and not twist them. But there is a specific reason why they are twisted together, and that's to help reduce interference. And we're talking about electromagnetic interference and crosstalk. So there are 2 types of interference, is electromagnetic interference, and the second one is crosstalk. So let's start with electromagnetic interference. What is that? Well, that's when electronic signals emanate outside of the coating here that's covering this copper cabling, and it can potentially interfere with the other cables. not only with the cables within this one single strand, but potentially other cables that are near it. So maybe there is another type of cabling next to it, such as a phone cable, or maybe just an electrical line. And electromagnetic interference can cause issues with our data lines because it can cause signal degradation, and it can cause us to have corrupted data if there is too much EMI. Now, the second one with these twists is that they help prevent crosstalk. And crosstalk is a type of EMI where the EMI is going from one cable to the next. And here's a good example down here. So for example, we have a signal here on our orange strand, and it's jumping down to all the other cables, and it's causing signal degradation. So that's why we have it. Now, there's a security concern with this type of cabling, and that has to do with the EMI. And so when you have this type of cable, it can emanate electronic signals outside of this cabling, and that's what causes EMI. Well, when that happens, when you have hackers, if they're good enough, they can actually pick up on that EMI and those signal emanations and try to pull data off of it. So there are security concerns when you use this type of cabling in a networking environment. Now, in regards to this type of cabling in general, it does have a maximum distance before you have to hook it up to some sort of repeater, whether that's a router or a switch or a hub, and that is 100 meters. So one strand of this cabling can only go for 100 meters before you have to go ahead and hook it up to a switch or router where it repeats that signal and it strengthens up that signal. Because what happens over time as it goes down this 100 meters is that the signal gets weaker and weaker and weaker, and what they've determined is that 100 meters is the maximum distance that we can go before the signal gets too weak for it to be useful. So let's go ahead and jump to the next slide. And let's talk about two specific types of the cabling. And there's two specific types. One is shielded and one is unshielded. And the shielding that we're talking about is right here. You'll notice that there's this metal shielding here and there's none here. And again, there's a specific reason for this. And so we talked about our security concerns with our signal emanations in EMI. Well, when we have this shielding in place, it goes ahead and it reduces the signal emanations and it reduces the EMI. And so it protects against electric interference, not only from electric signals that are going out from here, it prevents them, but it also prevents ones from coming in. So it'll block other cables as well from interfering as well. And so it acts as a shield, like a metal shield, just like it is. Now the other one is unshielded twisted pair, where there's no shielding, and this is the most common. So the reason why this is more common because it's cheaper and it's more inexpensive, and that way it makes it much more affordable for wide use across multiple industries. Typically you're going to see this in network cabling runs out from cubicle to cubicle, or where there's no other electrical cabling around it. Typically where you're going to see shielded twisted pair is where you have cable runs close to other electrical equipment or electrical cables. So for example, if they're running cables from some sort of electrical closet up into the ceiling along the same lines as the other electrical lines, you're going to have shielded twisted pair, but by the time it gets out to the cubicles where there's not that many electrical signals around, then they're going to use unshielded twisted pair. So let's go ahead and let's talk about the different types, because there are different categories of these, and the categories determine how fast these type of cablings can be, meaning what type of bandwidth that they support. So there's category 5, category 5E, and category 6. And here's an image of them three. So we have Cat 5 here, we have Cat 5E here, and we have Cat 6 here. Now, I do have this image as a full screen on the next slide, but if we take a look, the cabling here is the exact same. However, the only difference is the number of twists per cable. And so the more twists you have, the faster speed it supports, the less signal emanation it has, the less EMI it has, the less crosstalk it has. And so the speeds that it supports are much higher. So for category 5, it's 3 to 4 twists per an inch of cable, which is right here. And that'll support up to 100 megabit per second Ethernet. And Ethernet is simply when we're talking about the networking. Category 5E has more twists than Cat 5, and what you'll notice here is that you can see more twists, and it supports 1 gigabit per second network speed. And then Cat 6 is the fastest out of these three. And again, this one has many more twists. So if we look at here from here, you're going to see a huge drastic difference in twists per an inch. And this will support up to 10 gigabit per second. So we're going from 100 megabit to 10 gigabit per second just from going from here to here. And the cabling itself is the same. The only difference is the number of twists per inch. So let's go ahead and let's jump to the next screen so you can see a bigger picture. And there you go. So if we look at here, you'll notice for each inch, from here to here, we only have a minimal amount of twists, but when we get up here, we have numerous twists. And so those twists allow higher bandwidth speeds because of all the benefits that it gets in regards to reducing EMI, reducing crosstalk, and reducing signal emanation. So that's going to go ahead and conclude this lecture. If you have any questions about twisted pair coupled cabling, please wait until the end of this section because we're going to talk about it a bit more after we talk about fiber optic cabling as well. But by the end of the question, if you still have questions about twisted pair cabling, please let me know as usual. And if not, thanks for watching and we'll see you at the next video. In this video, we're going to talk about fiber optic network cabling. So let's go ahead and get started. So the first thing that you need to know is that fiber optic network cabling has a glass or plastic fiber core that carries light. And this is what it looks like right here. So this is the glass or the plastic fiber core. And what happens is that we have light pulses. So our network interface card that's set up for these, it pulses light signals and it goes down through there. So it's not like our standard network cabling where we have a copper core with our twisted cables. Instead, this is moving light instead of electromagnetic signals. So it's entirely different. And so I think that's pretty cool. And so I'm going to go ahead and I'm going to go over here and I'm going to underline this so you can see this. And let me go ahead and get my pen tool out here. So it carries light. And this makes for some significant differences in terms of its bandwidth. So remember when we were looking at our twisted pair, the highest bandwidth that we saw was 10 gigabit per second. Well, if you look at fiber optic, up to 100 gigabit per second. So a 10 times increased possibility in speed. And when we're talking about 10 gigabit per second, that's really fast. Once we get up to 100 gigabit per second, that's lightning quick. Now, another benefit is that it can span much longer distances. So with our electrical signals, the signal is going to attenuate out of the cable and we're going to have EMI, we're going to have crosstalk, and so the signal is going to have signal degradation over time. Well, with light, we don't have that as much, and so it can go much longer distances. And while I'm talking about it, we'll go ahead and we'll point at it. So multi-mode fiber will go up to 6 miles and single mode fiber will go up to 40 miles. And so if you remember from our previous lecture when we were talking about twisted pair, we can only go 100 meters. And so we're looking at 100 meters and now we're comparing it to 6 miles or 40 miles. I mean, that's a drastic difference. Now, another huge benefit, and this is kind of a plus benefit in two factors. So the other benefit is that it's immune to EMI. And it doesn't emanate signals because we're not dealing with electrical signals anymore. So when there's no EMI, there's no crosstalk, there's no signal degradation like there is with our twisted pair. And also, because we don't have EMI or crosstalk, it doesn't emanate any sort of the networking signal out of the wire. And so we don't have to worry about our security concerns like we do with the twisted pair. So that's another benefit of that. Now, there are two main types, and they are multi-mode fiber and single mode fiber, and we'll talk about those more on the next slide. So in terms of how they're used, multi-mode is typically used for shorter distances, so for local area networks and from building to building. Single mode fiber on the other side is more expensive than multi-mode, and it's used for longer distances, typically wide area networks. And you can see this will span 40 miles and this only spans 6 miles. And now I'm saying it only spans 6 miles, but if you think about it, this is probably more than good enough for a campus network if you want to set it up on a wide area network, because you're typically not going to have 6 miles between buildings. And now, if we compare this to our old type of cabling, our coaxial and our twisted pair, this will go much longer distances. So let's go ahead and let's see what the actual difference is between multi-mode and single mode. So with multi-mode, we have multi-bursts of light signals going back and forth, and they bounce off the core off the edges, which we see here. And so you're getting more than one burst of light and signals going at a time. Single mode is just one burst going straight down, and so one burst at a time, and that's the difference. Now, I don't know all the detailed differences of how it actually works and how these fiber optic networking cables work and how that works with this on a high level of detail. But from our perspective and what we need to know from a beginning perspective and just understanding how it works, this is how we need to know how it works. We don't need to know any more than this. So let's talk about why we would use fiber, and I already talked about it. The downside is that it's a lot more expensive than twisted pair. And so because it's a lot more expensive, we need to be able to justify why we would use it over twisted pair. And so the first one is the distance. Now, if you're in an office network where, you're in a small office or medium-sized office and you don't need to span that large of a distance, twisted pair is going to be fine. But what if you need to span multiple miles? Well, that's where this comes into play. Or what if you need to set up a wide area network? That's where fiber comes into play. So that's one of the reasons. You would use fiber if you need to span long distances. And you would use twisted pair if you need it for short distances. Now, another benefit is that we have decreased costs on our other networking equipment. So if we think about our switches and our routers, because these can span such longer distances, we don't need as many of those devices. So while we increase our costs on our fiber cable and the specific devices required to use it, we do cut down costs on our switches and routers because we can span longer distances. So that's another benefit. However, that may not offset the cost, but if you think about it from that perspective, you can offset some of the costs. So that's one of the other benefits. And then if we're thinking about security concerns and you're thinking about signal degradation, you're thinking about signal emanations and EMI and crosstalk and needing your networking to be highly reliable, well, because fiber is immune to all of those, that's another reason why we'd want to use it. We don't have to worry about EMI, we don't have to worry about signal emanations, we don't have to worry about our loss of signal over short distances, because it's going to span multiple miles if we need it to. And so all this leads it to being much more reliable and much more secure. So those are other benefits. And then lastly, another benefit is that even though fiber is new, it's been around for quite some time, but it's still relatively new. And whenever you come out with a new technology, the prices are going to be higher at the beginning because there's going to be costs associated with manufacturing it. But once we get those economies of scales in place and we have many different companies and manufacturers building it, those costs are going to decrease. And so as costs decrease, you're going to see more people adopting fiber. And so those are the different reasons. So now let's go ahead and, just for fun, I decided to put a picture in of all the different types of connectors for fiber optic. And you'll notice that there's a ton of them. And I don't know what the difference is between them, but I just wanted to show you. One of the reasons why people use twisted pairs is one, it's inexpensive, and two, there's a standard in place. You'll only see that RJ45 in use, which you'll see when we talk about it more. But when you're talking about fiber optic, we have all sorts of different cables and connectors on the end. And so it's going to take time for it to be standardized, and once it does, and they pick one different type of connector or another, then the prices are going to decrease. But as of right now, there's lots of different connectors. So that's going to go ahead and conclude our introductory lecture on fiber optic cabling. If you have any questions, please let me know. If not, thanks for watching, and we'll see you at the next video. We're going to jump back and we're going to talk about our twisted pair copper network cabling again. And we're going to talk about the wiring standards. And the reason why we're going to talk about this because number one, it is the most popular and most prevalent type of network cabling out there in the networking world today. And number two, for those of you that decide to go in the networking world or pursue a certification, you need to be familiar with these wiring standards because these are how the cables are going to be connected at the end with their plugs, specifically the RJ45 plug. And so we need to understand what these standards are, and all it is, it's the order of how the cables are put into these plugs, and it's nothing more. So all the cables go in here and they go in a specific order, and that's how we identify them as standards. So let's first talk about why we need to have standards, because you could set up your own standard, and so long as the wires are correct on each side, then it's going to work on your network. But there's a specific reason why we have standards in place. And the first one is to have interoperability, that if you go from one network to the next, that it's going to be the same. Or if you have one personnel quit and somebody else comes in, they know exactly how you wired the network and how the cables are set up. So with that said, let's talk about the two standards. So there's two specific standards. There's a 568A and there's a 568B. And between them, they actually work the same on the network. The only difference is how the cables are ordered on them. And 568B is a newer order and a newer standard than 568A. And it is the recommended standard. Now, I don't know why they chose to go with the 568B over 568A, because they work exactly the same, and you could wire your network with this standard, and it would work just fine. But for some reason, people recommend 568B as the standard. And I think it's just choosing one or the other over the other so we all follow that same standard. So let's go ahead and look at the differences. So for the 568A, we have our green-white wire followed by our green wire. Then we have our orange-white followed by our blue. We have our blue-white followed by our orange. And we have our brown-white followed by our brown. Now on the flip side, it's just a little bit different. We have an orange-white followed by an orange, a green-white followed by a blue-white followed by a green, a brown-white followed by a brown. So you're going to see some of those wires flipped around. And all you have to remember when you are doing network cabling, if you do go into the networking world, you're going to have to learn how to do this, and it's just, trial by error. It takes you about maybe a couple hours to get the hang of it. That's how long it took me. But all you have to do is memorize the order of these, and it's a specific order that it goes into the RJ45 plug on the end of the cable. And so you just line them up, you make sure that they're nice and straight at the end by snipping off the end, and then you just put them in here, and then you snip it on together. So that's all you do, and you do that on each side of the cable, and then that's considered one of these standards. And since we're going with the 568B in our industry standard, then you would follow that. So that's what the wiring standards are, and it all just comes down to how you plug these plugs onto the end of these cables. Because in the networking world, we don't buy cable pre-plugged together. So if you go to Best Buy, or if you go to Fry's Electronics, or you go to some other electronics store, you can buy a network cable and it's already completed for you. It's already created. It always has the RJ45 plug on the end, and it's ready to go and you can plug it in. But for a lot of companies, they buy big spools of the cable by itself, and they buy a whole bunch of these plugs, and we buy tools to put together. And the IT people and the networking people, in our spare time, we make cables. And the whole reason for that is that it cuts our costs. It's a lot cheaper than having them pre-made by somebody else. You can just do it in-house, and you can test them to make sure they work with some testers. And so that's why we need to know this. And just getting back to why they're important again, if we've just all followed the same one, we all know what everybody's using. So number one, it lowers costs because there's no questions on how the cable is going to be set up and how it's going to work. We know that it's going to work on any network. Number two, it increases our interoperability because we know it's going to work on each network. And number three, it decreases our maintenance time, again, because when somebody new walks in, they know how to wire those networks. So if a network cable is broken, they can just plug a new one in, or they can cut it and put a new plug on the end and so forth, and it's going to work. So that's our introduction to copper wiring standards. Now, if you want to know how to put these together, I recommend going to YouTube and just searching for 568B or 568A network wiring standards, or how to put a network wire together. It's very simple. You need some specialized tools, a crimper, some wire snips, and so forth, and you can do it. Unfortunately, I don't have a type of high definition camera where I can show you here in this course, just because there's a fine level of detail, and you have to see how every wire is put together, and you have to be able to see the different colors on them. So that's going to go ahead and conclude this video. If you have any questions, let me know. If not, see you at the next video. We talked about cable selection criteria a little bit in previous videos, but I want to make sure that I dedicate an entire video to it. So that's what this video is going to be all about, because I want to make sure I talk about all the specific points you need to consider. So let's go ahead and get into it. So what's the first criteria? Well, the first criteria is always going to be your budget. What can you afford? So, ideally there's certain types of network cabling that we want, but what fits best within our budgets? What can we afford? And what do our resources allow us to purchase? Now, the second one is going to be your speed requirements. So what type of bandwidth do we need to support both now and in the future? So we just can't think about now because we want our network to support growth over time. So we need to consider what do we need now and what will it support in the future. And what you have to do is you have to figure out what's going to fit best within that. So you need to figure, okay, what's going to support us now plus the future. And it may not be fiber, which may be what you ideally want, but maybe it's going to be something like Cat 6 or Cat 5e, where it's 1 gigabit per second or 10 gigabit per second. Now, the third one is going to be your distance requirements. So again, we're thinking about both currently and in the future. So everything we need to think about is, does it support us now and does it support our future growth in the future? So, we really only have two different options. We have twisted pair and we have fiber. So we need to determine, how big is our network going to be and where do we need to put one type and where do we need to put another. So don't always think that when you're looking at the cable that you have to just go with twisted pair and you have to go with fiber. You can do a combination of both. So you need to determine in what areas will twisted pair work because it's more affordable and more economical, and what areas is going to require your fiber network. And if you can get away with just twisted pair altogether, then that may be fine as well. And then lastly, your third concern is going to be noise and interference immunity. So we have to think about our concerns with our crosstalk, our EMI, our signal emanation, and our signal degradation. And we need to determine what type of factors our environment deals with that, how it affects it, and also our security concerns. So we need to consider all those different aspects. And when we're talking about interference, I'm talking about power cables, microwaves, cell phones, and even motors, like if you have a generator. So we need to think about all that for crosstalk and EMI. But then we also have to think about the security of our data. So what if we're on a network that we have potentially classified information, if we're a government network, or we have sensitive but unclassified information, or if we're a corporate network and we have our own proprietary information that we don't want leaked out and we don't want somebody to be doing corporate espionage against us and trying to hack it, we need to consider what's going to work best for us. And if we're worried about the security concerns, then of course, fiber is going to be the best choice. And if we're not so worried, then twisted's going to be fine. So those are the high-level criteria that we need to think about. First of all, again, we'll recap. We need to think about our budget and our budgetary constraints. We need to think about our transmission speed requirements both for now and in the future. We need to think about our network distance requirements both now and in the future. And then lastly, we need to think about our noise and interference immunity and also our security concerns. So that's going to go ahead and conclude this video. If you have any questions, let me know. If not, thanks for watching, and we'll see you at the next video. So we're going to go ahead and we're going to revisit our twisted pair networking cabling again, and we're going to be talking about two important types of network cables that are commonly used in our twisted pair network cabling environments, and that is our straight through cable and our crossover cable. So we need to talk about these because they're highly used throughout networks and they're commonly used, and you're going to see them a lot. So let's talk about the specifics. And the difference between them is how the cables are ordered when we put the RJ45 jack on the end. And in the next slide, I will show you the difference. So first, let's talk about how these work and what type of devices they're used to connect. So a straight through cable is used to connect non-similar devices. So what do I mean by non-similar devices? Well, I mean devices that are not the same. And let's go ahead and let's take a look. So for example, what I mean by non-similar, an example would be a router connected to a switch because they're different types of devices. Another example would be a computer to a switch, again, because they're two different types of devices. And a third one would be a switch connected to a wireless access point because, again, they are separate types of devices. Now, on the flip side, a crossover is the exact opposite. It's used to connect similar devices. And so what I mean by similar devices, well, a good example, a computer to a computer, a switch to a switch, and then a router directly connected to a computer. So this one gets a lot of people. So why a router connected to a computer? Well, because a router acts like a computer. It's a very smart device with its own operating system. So we really consider it a smart device similar to a computer. So we use a crossover cable to connect a router directly to a computer. So let's jump to the next slide and let's look at the cabling difference. And this should be fairly similar to what you saw before. And we're going to be looking at our two standards, our 568A and our 568B. So when we want to connect computers and make them a straight through cable, we are going to be making them the same on both sides. So if we're doing the 568B here, and let me get my highlighter tool out so I can go ahead and highlight this a little bit to make it a little easier to read. So if we're going to use our 568B or 568A, this would be one side of the cable over here, and this would be another side over here. So the cable is going to look the same on both sides. And that would be a straight through cable. However, if we wanted to do a crossover, and you'll notice here it says crossed wiring, so if our organization was doing 568A and we wanted to make a crossover cable, you'll notice that this side is going to meet this and be equal to what this looks like. However, there's going to be some switches over here. And so you just need to look at this diagram and determine the right order on the other side, because some of the cables are crossed. And same thing for the 568B. And so that's the difference. When we're looking at these pin numbers here on this RJ45 jack, we need to make sure that the proper numbers align on each side. And you'll notice that we have cables that are crossed over here in multiple different areas, and that's why we call it a crossover cable versus a straight to cable. And that's the difference. So now let's do some more examples talking about our crossover and our straight through cables. And we talked about it in a previous video, so here's some examples. So we have a straight through cable. Remember, this is for non-similar devices. So what do we have here? Well, the first one, we have a switch connected to a router. The second one, we have a switch to a computer. These are non-similar devices, so we would use a straight through cable. Over here we have a crossover, and remember, we use a crossover for a similar type of device. So we have a router to a router, we have a router to a computer, again because a router is a smart device and it has its own operating system, so we really consider it like a computer. And then we have a computer to a computer and a switch to a switch. Make sense? If not, just pause the video and just go back to the first slide and start the video from the beginning and watch through again, and it'll help make sense. Because on the next slide, what we're going to do is I have a diagram, and let me pull that up, and now I want us to identify what type of cable that we're going to use. So from here to here, we have a switch to a wireless access point. What type of a cable would we use here? Well, it's non-similar, so I am going to go ahead and write ST for straight through. And so that would go both here, right? Because we have non-similar devices there from a switch to a wireless access point. And then also over here, we have a switch to a computer, again, non-similar. So right here, we would also have a straight through. We would not use a crossover. Now, what about from here to here? We have a switch to a switch. These are similar devices, so we are going to use a crossover. And I'm just going to say CO for crossover. Now if we go over a little further, again we have a switch to a computer. So from here to here, non-similar, this is going to be straight through. And again, we have a switch to a router, non-similar devices, so we would use a straight through cable here as well. And then down here, we have a router connected to a computer. So remember, we said that a router is like a computer. It's a smart device, it has its own operating system, so that would be a crossover cable that we would use to connect these devices together. And then we have one more to look at. We have a laptop up to a laptop, so that's a computer to a computer. Similar devices, so again we're going to use a crossover cable to connect these together. So it's as simple as that. All you need to do when you're diagramming out and designing your network and determining what type of cable to use is you need to look at it and say, is this a similar device or a non-similar device? And for similar devices, we're going to be using a crossover cable, and for non-similar, we're going to be using a straight through cable. So that's going to go ahead and conclude this video. Again, if you have any questions about this, please let me know. If not, thanks for watching, and we'll see you at the next video. This section of the course is completely dedicated to the OSI model, and so what we're going to do in this video is we're going to do a bit of a review on the OSI model, and then what we'll be doing is we'll be dedicating a lecture to each layer of the OSI model. So let's go ahead and get started. So remember that the OSI model stands for the Open Systems Interconnection Reference Model, and it's a conceptual framework that shows us how data moves throughout a network. So why was it developed? Well, remember, it was developed to give us a guide to see how networks operate and to see how data moves throughout a network. And remember that there are unique protocols at each layer. And one of the most important things with this we have to remember is that this is only a reference model. Remember, this was not implemented. It's only a reference model. And in the real world, remember, TCP/IP was implemented instead. So remember that the OSI model is a stack of different layers, and within those layers there's a total of 7, and we have upper layers and we have lower layers. And so if you remember with the upper layers, we will call those the host layers, meaning these are the activities that happen on the computer itself. So we're talking about the activities that happen on the host computer, such as formatting the data, encrypting the data, and managing the network connection, so setting up sessions and tearing them down. Now the lower layers are the layers that we call the media layers, and these are network specific layers. So these are the activities that happen on the network, such as the routing, the MAC addressing, and the flow control of the data going across the network. Now let's go ahead and let's do a review of what the stack looks like. Remember, we have 7 different layers. We have our host layers on the top, and we have our media layers on the bottom, meaning our network layers. And remember, we have this nice little phrase to help us remember what these different layers are called. And it is, please do not throw sausage pizza away. And remember that everything links together. So let me get my little arrow tool together, and we'll go ahead and I'll show you what I mean by this. And let me get this in an easy color. So the first letter on each one is going to align with the first letter over here as well. And you'll notice that when we say it, we start with the bottom, we go to the top. So please do not throw sausage pizza away. And the first letter is going to align with the first letter here. So for those of you that are studying to take the Network Plus or the CCENT or the CCNA, having something like this to memorize this is something that's going to be really good for you. Now in terms of how this is laid out, remember we have our host layers up here, and so we have our host layers at the top. So the top 4 layers here are the host layers, meaning that's the activities that happen on the computer, and then the bottom 3 layers happen on the network. Now I'm not going to go into detail, and I'm not going to talk about this specifically because we're going to talk about this in detail in the upcoming lectures, so we don't need to talk about the actual roles of the layers right now. And just one more slide as a reference guide. Remember the process. We talked about how this works. Remember that everything starts up here at the top, and you're in there and you're inputting stuff on your computer. And remember, this goes down from here and down the stack until it's formatted so the data can be sent off in packets of information across the network wire. And then it goes across the network wire, and then it goes up the stack, so it goes the exact opposite way until it gets back up to the other computer. So that's how it works. It goes down the stack on one side, and I'll draw an arrow this way. So we have a computer here and we have a computer here. It goes down the stack on one side, starting with the application layer, and it ends at the physical layer, and then it goes across the network, and then once it gets to the computer that needs to receive the data, it goes up the stack. And so we're taking this data and rebuilding it so the person can see it. So that's our quick recap on the OSI model and our quick introduction for those of you that didn't watch the introductory video. What we're going to do now is we're going to go ahead and jump into videos. We're going to talk about each specific layer on its own. So let's go ahead and get into that. We're going to start our discussion talking about the OSI model, starting with layer 7, which is the application layer. So we're starting at the very top layer at the host layers, and we're going to work our way down all the way down to the physical layer, which is the very bottom layer where the data is going to be moving across the network. So why are we starting at the top? Well, we're starting at the top because this is where you, as a user, you use computer programs and applications to communicate with the network. And that's why we call it the application layer, because this is where you are interacting with applications, and then these application programs are going to interface with the network. And so we have application programs such as the Internet Explorer or Outlook, and these programs are going to interact with application layer protocols. So for example, Internet Explorer needs to interact with specific protocols to access the internet, and that specific protocol is HTTP or HTTPS. Outlook is the same thing. It's going to use email protocols such as POP3 or IMAP to interact with the network to allow you to send and receive emails. So one thing that's important to note with this layer is that the applications themselves don't reside in this actual layer, but instead they interface with application layer protocols. So it's the actual application layer protocols that reside in this layer 7 up here. And I'll go ahead and circle one. So for example, HTTP is one of them. Another one that I said was IMAP, and another one that I said was POP3. Those are both for email. So just to recap, remember when we are talking about layer 7, the application layer, the very top layer, this is where you and applications on your program are going to be interacting with application layer protocols that interface with the network. So for example, Internet Explorer is going to interface with the protocol HTTP to get out to the internet. Outlook, the application, is going to be interacting with an application layer protocol, IMAP, to get out to a network to receive and send emails. It is not the actual application that's in this layer, but instead, again, it is these application layer protocols that's in here. So that's what layer 7 is, and so that's the very top layer of the OSI model where we're talking about how applications interact with the network. And you'll notice over here it says network processes to applications. So again, network processes or network protocols interacting with an application, allowing this application to communicate with the network. That is the very top layer of the OSI conceptual model. So in the next lecture, we're going to talk about layer 6, the presentation layer. So we started with layer 7, now we're going to move down to layer 6 of the OSI model, and that is the presentation layer. So we've gone down one layer. So what does the presentation layer do? Well, in a nutshell, it deals with data representation and encryption. So what do I mean by data representation and data encryption? Well, that's exactly what it does. It needs to make sure that data, when it goes from one computer to another on the network, that the data is represented properly so they can understand what it is, and if it needs to be encrypted, that is encrypted properly. So number one, it ensures that the data that's being transferred from one system's application layer can be read on the application layer on the other computer. So if it's going across the network, it doesn't do the other computer any good if it doesn't understand what the data is. So we use standard formats such as the IASCII format for HTML when we're sending HTTP requests across the network from one system to another. It uses that standard format so it can encode it in the standard format so all the computers that receive it understand what it is. And when we're doing this character encoding, we can output it in whatever language we need it to be in, so we understand what it means and what the data is. Now, another very important feature is that it also deals with data encryption. And you'll see my example down here, is that we can encrypt data going across, and then also, once we get to the other side, we can also decrypt, so it comes back in the proper format. So that's what the presentation layer is all about in a nutshell. Number one, it's all about data representation, where we're talking about encoding the data on one side with a standard format such as ASCII, and then also dealing with encryption. So when it gets to the other side, if it's encrypted, it knows how to decrypt it, or if it's encoded with a standard format, it knows how to go ahead and decode it as well. So that's what the presentation layer is all about. It only deals with this. And in the next video, we're going to talk about layer 5, the session layer. So now we're down to layer 5, the session layer, and we've gone down 3 layers. We've interacted with the computer, and so we've interacted with the program, and now we're on the network. We have prepared data to send it across the network, so it's going to make sense when it gets to the other side. So what is the session layer all about? Well, this layer does one important job. It's responsible for setting up, managing, and then also tearing down network connections and sessions between presentation layer entities. So what do we mean when we say presentation layer entities? Well, we're talking about you interacting on one side and needing to communicate with the presentation layer on some other side, whether it be a server or it be somebody else. Maybe you're doing an instant chatting session, or maybe you are logging into your bank via Internet Explorer or Firefox. So that's all that layer 5 does. It's all about starting, stopping, and restarting your sessions from one side to the other on the network. Now, this is just this process in a nutshell. We're going to talk about how this works when we talk about the TCP/IP protocol stack, because there are specific protocols we can talk about. But from a very high perspective, that's all you need to understand with this. Once we get down to the session, it's all about managing the communication from one side to the other by setting up, managing, and tearing down network sessions. So let's go ahead and let's jump to the transport layer in the next video. So now we've reached the halfway point. We're down to layer 4, the transport layer, and this is the very bottom layer of the host layers. So what is this all about? Well, let's go ahead and let's talk about it. Well, this layer is all about end-to-end connections and reliability. And I like to call this the post office layer, because this is all about ensuring that data arrives safely from the source to the destination. And there's two different protocols that are commonly used. And let me go ahead and get my tool ready. So I want to go ahead and circle this. And I actually do a little square to cover it. So this is using the TCP or the UDP protocols. And these are two very important protocols. And we're actually going to spend a little bit of time talking about these later in the course when we talk about TCP/IP. But the goal with TCP, the Transmission Control Protocol, or UDP, the User Datagram Protocol, is that we use these two different protocols, we select one or the other to determine how we're going to send data across the network. It's either going to use TCP or it's going to use UDP. And this determines how data is going to be sent across and how we're going to set up sessions and how reliable it's going to be. So when we're talking about this layer 4, we're talking about us being the post office, us being the mail person, delivering these actual packets of information and ensuring they get there and determining what sort of controls we have in place. So from a very high level perspective, without going into details before we get into our next section, we're actually going to talk about TCP and UDP. What you need to know is that this ensures that data arrives safely from the source to the destination. So there's different control measures in place when we're talking about TCP and we're talking about UDP to ensure that data gets there properly and safe. Now, another portion of this is that it breaks this up. It breaks the data up into segments. So the data is going to be broken up into segments, and as you can see down here is that we have it broken up into segments, and it's coming across in bits and pieces. And then when it gets from one end to the other, it reassembles the data into a data stream that can be read by the presentation layer and the application layer. So that's what layer 4 is, the transportation layer, all in a nutshell. It's all about ensuring that data arrives safely from one side to the other, and that we break it up and segment it into pieces, and then we reassemble it when it gets to the other side. And we're using TCP or UDP when we're doing this. So now let's go ahead and let's start with our top layer of the media layers. We're going to talk about the network layer in our next video. So now we're down to layer 3, the network layer. And this is the very top layer of our media layer. So meaning this is the very top of the layers that's dealing with the network portion of the OSI model. So we're no longer dealing with what's happening on the computer. Now we're dealing with what's actually happening on our network. And so what is this layer all about? Well, this layer is all about routing. And when we talk about routing, we deal with routers and IP addresses and routing protocols. So again, what are the two main focuses of this? IP addressing, number 1, and number 2, routers and routing protocols. And let me go ahead and get my highlighting tool, and I want to highlight this. So our IP addresses and our routing and routing protocols. And we're talking explicitly about dealing with IP addresses to communicate across wide area networks. So remember from previous lectures, when you're dealing with routers deal with IP addresses, and those are our logical addresses that's assigned to us by our network. This is not the MAC address, this is our logical IP address. And so you'll see down here in these two examples, computer 1 over here and computer 2 over here, is that we have their IP addresses listed underneath them. And we have the internet here being a wide area network. And what do we use to connect networks together? We use routers to connect networks together and communicate across a wide area network. So this layer is all about IP addressing, routing, and routing protocols. And remember, just to recap on the IP protocol, it's a primary networking protocol that's used across the internet. We've talked about IP version 4, and that's what these are down here. And I'll draw an arrow. So these addresses down here, IP version 4, we haven't talked about IPv6, but it also deals with IPv6 as well, and we'll talk about that for a little bit, but we're not going to go into details on it in this course. So that's what layer 3 is all about. Now we're going to jump down to layer 2, the data link layer, and we're going to talk about physical addressing. So just to give you a preface on that, layer 3 deals with our IP addresses, our logical addresses, and layer 2 deals with our MAC addresses, our physical addresses. So these two layers, once we get down to the media layer, these two layers are all about our addresses on our system. Remember, we have two addresses on our system. We have an IP address that's assigned by the network, and we have that physical MAC address that's burned into our network interface card on our computer. So let's go ahead and let's talk about the data link layer in our next video. Okay, so now we're down to layer 2, the second to the last layer. We started with the application layer, and now we're all the way down to the data link layer. So let's go ahead and let's take a look at what this represents. And in the previous video, I talked about this briefly. This deals with MAC addresses. So this deals with our physical addresses on our systems, and let me go ahead and highlight them since I have them down here. And remember, when we're talking about MAC addresses, we're talking about interacting with switches, because switches deal with MAC addresses, and that's how they send information back and forth with their MAC address table. So the main point to take away from this is that this is all about communication on a local area network and making sure packets of information going across the network are received on one device to another. And we're dealing with our MAC addresses, which is our media access control address. Now, one thing to understand is that when we're dealing with a network, we're dealing with routers, and we're talking about communication across wide area networks. When we're dealing with the data link layer, we're talking about MAC addresses, and we're talking about sending data across our actual local network. So this is important to understand because we have two different layers, and one layer deals with one aspect of network communication, another layer deals with another aspect of network communication. And as we move down the stack, we are going to talk about our very last layer, the physical layer. And so this is important because once we get down to here, the data link layer, the next layer down is our physical layer, and this is where this is going to interact to send data across the wire. Now, one last thing that I'm going to say about this is that we usually call the data link layer the switching layer. And so this makes complete sense because when we're talking about switching, we're talking about interacting with switches to send data across the local area network with MAC addresses. So now that we know what the network layer does and the data link layer does on our media access layers, let's go ahead and talk about the physical layer, our very last layer in the OSI model. So now we've gone from layer 7 all the way down to layer 1. So we started with us interacting with the network application, such as Internet Explorer, where we're interacting with Internet Explorer to communicate with the network. And now we've gone all the way down to our physical layer, where we're talking about the actual bits and bytes of information going across the network. So when we're talking about the physical layer, we're talking about the physical portion of the network. We're talking about our cables. We're talking about our punch downs. If we're punching into a punch down box, we're talking about our network interface cards, we're talking about our Wi-Fi cards, and we're talking about our wireless signals. So it's all about the cabling and the Wi-Fi at this point and the physical aspects of it. There's no protocols that we deal with down here. It's all about just sending this information across the network, whether it's wireless and we have radio waves, or it's wired and we have electrical bursts that are going through our twisted pair cabling, or it's light bursts that are going through our fiber optic cabling. So that's what this is all about. By the time it gets down to here, that's what we're dealing with. And so that's what the physical layer is all about. So now that we've talked about all the different layers in the OSI model, we need to conceptually understand what happens to data when it moves down and up the OSI model stack. So we're going to talk about that in this lecture. So what happens is a specific thing called data encapsulation and data decapsulation. So what do I mean when I'm talking about those? Well, when we're talking about encapsulation, we're talking about when we add chunks of information to our data. So what am I talking about when we add chunks of information? Well, this occurs when we start at the very top of the OSI model and we're interacting with our computer. and we're trying to send data across the network. Well, when that data goes down the OSI stack, we're adding on additional information such as our source and our destination IP and MAC addresses, any encryption, any encoding, and setting up those sessions and all that sort of information. So what happens is that we add chunks of information and we call this encapsulation. So this occurs when we send data from our computer. Now the exact opposite occurs when it goes up the stack and data is being received at the other end. So when data is being received at the other end, we call that data decapsulation. And the exact opposite happens. We remove these chunks of information that we added on. So the MAC addresses, the IP addresses, and everything else. So by the time that it gets up to the very top of the other end, where the user receives that data and information on their computer, all the receiving is the information that needs to be outputted, and none of that extra chunks of information such as our IP addresses, our MAC addresses, and our encryption and all that other stuff. So now that we've introduced encapsulation and decapsulation, let's go ahead and let's visualize it, because this may not make that much sense, but I guarantee once we jump to this next screen, it's going to make a whole lot more sense. So here's a visualization of it. And here we are starting at the very top, and let me go ahead and show you what we're talking about. So when we're starting at the very top, it's just the data. But as we go down this application layer, we're adding on additional information. And so you'll notice we add on a bit of information here for the application layer. So there's the application layer protocol such as HTTP. For the presentation, determining how we're going to encode the data. The session, determining how we're going to manage the session. The transport, determining how we're going to reliably send that information and how we're going to break it up and get it there. The network portion, where we're going to be adding on our IP addresses. The data link portion, where we're going to be adding on our MAC addresses. And the physical portion, where we're going to be breaking this up into actual bits and bytes of electrical signals or light bursts. And as you notice, when we go down, we're encapsulating data. So we start with the bare data, and by the time we get to the bottom, we have all sorts of information on the bottom added to it. And then when we go back and we go over to the other computer on the other side of the network, we decapsulate it. So we take off that information that we don't need. And by the time we get back up to here, it's nothing but the raw data. And that's how this process works in a nutshell from a conceptual point of view. Now let's go ahead to the next slide and let's visualize this again. So now I want to just give you an idea of some of this information that we're adding on. Now I'm not talking about every aspect of what we're adding on, but I want to talk about some of the important aspects. And remember, when you're sending information across a network, we are sending IP packets and Ethernet packets. Well, we have to send a source and a destination IP address, so that needs to be added on. And when we're sending our MAC address information to communicate on the LAN, we need to have a source and a destination MAC address as well, so that's our Ethernet address. And so I just wanted to highlight those two important things, because from a beginner's perspective, we need to understand that there's going to be a source and destination IP and MAC address in addition to all this other stuff that we added on as well. So we can just assume that this is all that other sorts of information that we're adding on as well. And what we call, so here's the actual data, what we call these headers of information added on. And so we start at the top and we just add on more and more information. And that is the OSI model, data encapsulation and data decapsulation in a nutshell. So, in this section we started off talking about the OSI model by itself and the layers, and then we reached to the point where we talked about all of them and we could bring it together and I could show you how it worked visually from a conceptual model where data is encapsulated with information to send it across the network. And once it gets to its destination, that data is stripped off, that extra information is stripped off to the point where the only thing that is delivered on the other end is the actual application data itself. So if you have any questions about this, please let me know. If not, thanks for watching and we'll see you at the next lecture. This section of the course is all about planning a network before we build it out. So why do we plan before we build? Well, I think that's a fairly simple question and there's a fairly simple answer. Number one, we need it to do what we need it to do. And from a business perspective, that means it needs to meet our business requirements and it also needs to meet our technical requirements. Now, what happens if we don't properly plan a network and we just build it out? Well, we're going to have all sorts of issues, and we're going to have all sorts of risks. And we're going to end up having an ad hoc network design. An ad hoc network design meaning that it's not going to meet our specifications, and it was inadequately designed. And when we have an inadequately designed network that was built out, well, we're going to have all sorts of issues, and I have them all listed here. And when we have all sorts of issues, we're constantly putting out fires, trying to keep it up and running, and we have a very reactive approach to keeping the network up and running. So whenever anything breaks, we have to fix it, and we end up having a break-fix mentality, which is not what we want. Now, this is an issue that we commonly see with small and medium businesses. I'm going to go ahead and circle this. And so why do we commonly see this with small and medium businesses, and most likely small businesses? Well, it's because this is all around resource constraints. And when you have resource constraints, you can't afford to do what you ideally want to do. So you may have monetary constraints, and you may have personnel constraints. You may not have the expertise that you need to build out this network. And so that's why it's primarily around small and medium businesses, and typically not with larger businesses. So now let's talk about the issues that we're going to have. Well, if we have an ad hoc, inadequate network, and we're following a break-fix mentality, well, we're going to have troubleshooting issues, because if it wasn't properly designed, then we're going to have issues when we're troubleshooting, because maybe we don't have a network map, maybe we don't have a network design to go off of when we're troubleshooting issues, or if it wasn't designed in the first place, we're going to have a hard time just keeping it up and running. Now, again, if it wasn't designed properly, it's not going to scale per our needs. So we're going to have scalability issues either now or in the future with the network. And then, of course, if it's not running properly, we're going to have reliability issues as well. So the network's not going to have the availability that we need. And then again, if we have somebody design our network that doesn't know what they're doing, if they don't secure it properly, we're going to have network security issues. So our network isn't going to be as secure as we want it to be. And this is a huge one. And this will lead to all this combined: troubleshooting issues, scalability issues, reliability issues, and security issues. This all leads to these two bottom points that I'm going to go ahead and circle: data loss issues and costly repairs. So we're going to lose data a fair amount of the time, and typically this is something that we want to prevent. We may lose it due to reliability issues. We may lose it to network security issues. And this all leads to costly repairs and us spending more money in the future than we should have spent in the first place. So now let's talk about some more issues that we can face. Well, number one, business downtime is something that may end up being a huge problem for us. And a lot of people really don't think about this. You know, we do have business downtime, but what's the impact? Well, when we have business downtime, we have decreased revenues, we have decreased profitability, we have a tarnished reputation, and that all leads to one important thing that we don't want, and that is a loss of our customers. And so, you know, you don't really think about this unless you are on the business side of the house. When the network goes down, you don't understand how decreased revenues are going to harm your business. You don't understand how that leads to decreased profitability of your business and a tarnished reputation, which is something you want to do your very best to prevent, all leading to this one last thing, which is a loss of customers. And if we have a loss of customers, that's really going to doom our business in the long run. So we want to prevent all this information and all of this from happening here. Now, when we are planning a network, what's the benefits? Well, the benefits is that it keeps the process focused and organized. And I'm going to go ahead and highlight these. And so when we're focused and we're organized, when we're planning, then when we go to the designing process, we know our business requirements and we know the technical requirements as well as our resource constraints. And good plans are going to produce the best results. So if we plan well, we're going to have good results. On the flip side, if we plan poorly or if we don't plan at all, when we go to design, we don't know the technical requirements, we don't know the business requirements, we don't know our resource constraints. And so when we design and build, we're going to have the worst results. And then lastly, this is a very, very important point, is that if we are doing this from a consulting perspective, or if we're doing this from an employee perspective, both our clients and employers expect us to properly plan before we build out a network. So that's why we plan before we do anything else. In this video, we're going to talk about the overall process of planning, designing, and building a network. Now, this is a fairly simple process, but I wanted to take a couple of minutes and walk you through it so you understand everything we're doing. And this really evolves around a project management perspective, because we really are starting at the very beginning of a project where we want to build a network, and at the end result is having a network that's up and running. So let's go ahead and let's get into this process. So what's the first step? Well, the first step is we plan. And we talked about this earlier, is that initially we want to plan, and when we're planning, we are looking at the business requirements, we're looking at the technical requirements, we're figuring out what our constraints are on all of our resources, and that allows us to effectively plan. Now, once we plan, we take all this information that we gathered in the planning phase, and we take that and we start designing our network. And so at this point, we're going to design our network based upon these constraints that we have, based upon our needs as well. And so we take all that, we build out a plan, and we design our network based upon that. And then once we get our network designed, and our client, our employers, or whoever is going to be improving that design, once they approve it, we go to the next step, which is building out that network, and that's implementing it. So we're going to take that design that we utilize from our plans, and we're going to implement a network. And so we're actually going to build it out. We're going to purchase all the hardware, and we're going to physically build the network. Now, once we're done building the network, we're not done yet. You may think that you're done, but you're not. Once it's up and running, you need to make sure that it's working properly, and you need to maintain it. So there's going to be this process of continual maintenance on the network. So you're going to have somebody in place, a network administrator, a network support personnel that's going to be maintaining the network for any issues that may be happening. And they're going to just make sure that the network is running as smoothly as it can. So once we get to that point, the network is up and running. At some point in the future, we need to tune the network and we need to upgrade the network. And if you think about it, with all computing equipment, it's going to have an end of life cycle. So it may be 2 years, it may be 5 years, it may be 10 years. At some point in time, you're going to want to upgrade that equipment. You're going to want to fine tune. And this comes to the process of continual improvement. And so we're going to go ahead and we're going to determine what we're going to go ahead and what we want to upgrade. And so we want to look at tuning it. But before we do that, we have to jump back right to plan. So we need to plan before we do all this. This is just kicking off this phase, and what this does is that it kicks off the planning phase and we start all over again, and it's just always cyclical, and we just go around in a cyclical process. So that's the overall process, and this is not only centric to only networks, but this deals with anything. This can deal with any project in general. It can deal with any IT project in general, but this worked very well for network design as well. So that's our overall process for building out a network. So when we're planning and we are going out and we're gathering information on the business, the first thing that we need to do is, number one, whether we're a consultant or for an employee and they want us to build out a network, well, we need to understand the business first before we go anywhere else. And so if you're thinking about understanding the business, we are talking about what the business does. So we need to understand, what does a business do? What is their services? What are their products? What problems are they solving? So when we're talking about this, we're talking about their core and strategic competencies. So this is what the business is all about. So you need to understand this first, and I'm also just going to point an arrow at it because I think it's highly important that you understand this point. It doesn't matter if you're a consultant, it doesn't matter if you're an employee. Before you build out that network, you need to understand what the business does, because you're going to need this to determine the business requirements. So let's go ahead and let's determine how we can do this. How can we determine understanding the business and understanding what it does? Well, there's some key processes that you're going to want to do. And these is that you want to perform the following. You want to perform a business process analysis, a business impact analysis, and key stakeholder interviews. So why are we doing all this? So why are we doing a business process analysis? Well, we need to understand what the business processes are, and this gets down to understanding what the business does. So when you analyze the processes of the business, for example, maybe you're a manufacturing business. Well, you need to go in, you need to interview people, you need to go ahead and look at the business, and you need to determine what are their key processes. So we need to understand what these processes are. And then we also need to do a business impact analysis. So we need to determine what's more important and what's the least important. So once we understand what these business processes are, we're going to look at them and we're going to prioritize them from the most important to the least important. So for example, for a manufacturing business, one of the most important processes is going to be the actual manufacturing. Well, what's one of the least important processes? Well, maybe that is something to do with their HR processes, or maybe it is a marketing process, or maybe it's something as simple as a purchasing process. Now, it's not to say that these aren't important, but we have to rank them from most important to least important. And so we're going to determine what they are, and then we're going to do a business impact analysis to rank them and to find out which ones are the most important. And so how are we going to do this? Well, it's very simple. We have to interview employees. We have to interview key stakeholders in the business and organization throughout the different departments to determine what the key business processes are and determine which ones are the most important. So that's the process of understanding the business, and we need to understand what we need to do to determine what the business core strategic competencies are and their key business processes are when we're doing this initial planning process. In this video, we're going to talk about the concept of establishing a business need. So what is establishing a business need? Well, it's all about justifying why you need to do something. And when we're talking about building a network or responding to a request for a proposal, if we're a consultant where somebody wants us to propose a network design to them, they're going to want us to establish the business need and tell them why our proposal is better than our competitors. Or if we're a network administrator and we need to upgrade our network and we're going to ask our managers for money, we need to justify how that's going to help the business. So people just aren't going to give us money left and right to build networks for them or upgrade networks for them. We need to establish a business need, and that's all about justifying how our network design or our network upgrade is going to help the business. And so what do I mean by helping the business? Well, we can talk about that in terms of these examples down here. One example is that we can use our network design or network upgrade to increase operational efficiencies via business process improvements. So for example, maybe we upgrade our network so now it can support higher bandwidth. So we can then purchase a server where we can do business intelligence, and that's going to take a lot of our manual processes and reporting and roll them up into an automated process. And that's going to increase our operational efficiencies, and it's also going to lead to business process improvement. Now, another example is maybe we take our network, we have an older network, and we build and spec out a smaller, more efficient network that's going to use a lot less electricity. It's going to be a lot more green, and it's going to be a lot more environmentally friendly. Well, maybe that leads to decreased IT costs and decreased operational costs. Now, another example of this would be properly designing a network where the network is going to be working properly versus having one in place that you currently have that was set up with an inadequate design. If we're going to upgrade and we switch it to a properly designed network, again, we're going to have decreased IT costs. It's because we're going to have less troubleshooting costs, and that's going to lead to decreased operational costs as well. And the goal is, and this always isn't going to be the case, is that if we use our network as a strategic driver for the business to enable us to do what we do as our core business processes, well, the goal is to have this to increase the profitability of the company and increase our bottom line. So it's all about a positive ROI. Now, in certain instances, it's not going to be the case. But for example, let's say that you are a security network administrator and you determine that you need to purchase a bunch of security devices on your network. Maybe you need to upgrade all your firewalls, or you need to purchase some intrusion prevention systems or intrusion detection systems. And this is going to cost the company a lot of money, and they're not going to see a positive ROI in terms of increased profitability, but they may see a positive ROI in regards to having a lower risk factor and reducing the likelihood that the company is going to be hacked into and the data is going to be lost and it's going to hurt the reputation of the company. So you need to look at that from that perspective as well. You're not always going to give the company more money. It's not always going to improve the processes and make the business more profitable, but it's going to support the business in other ways, especially when we're talking about cybersecurity and network security. But that's going to go ahead and conclude our video on establishing a business need. And I just want you to understand that when you are planning out a network design or a network upgrade, is that you always have to justify why you need it. Not only from a technical standpoint, but if it's for a business, always from a business standpoint, and you need to establish that business need and get that buy-in. So if you have any questions about this, let me know. If not, thanks for watching, and we'll see you at the next video. So when we're building out our business case and establishing our business need, we really need to think about specific areas that we can improve within the organization. Because when we are justifying our need, we need to give concrete examples. And that's what this video is all about. So when you are looking at an organization, whether you are a consultant or an employee, and you're either building out a new network for them or you're upgrading a network for them, you need to look for areas within the organization that you can improve with your design. And so let's go through some of those right now. So what are some of the things that we can do? Well, we can improve communications and data sharing with the network. We can automate business processes as well. And we can do many other things. So what can we do? What are we talking about when we're saying improving communications and data sharing? Well, when we're talking about improving communications, maybe we can set up an inter-office chat system where people can do phone calls over their laptop or their desktop, or they can do a video conferencing. Maybe they can do instant chatting with other employees. Well, maybe we set up a more reliable email system so people can communicate more effectively on the network. And for data sharing, maybe we set up a wiki software service for people to share information and data within the organization on their intranet. So what about automating business processes? Well, the simplest example is taking very archaic and very manual paper-based processes and converting them into digital processes where we can automate them and we can make them much more efficient in a much more quicker manner than if you're doing them on a manual-based process. And also we can look at reporting. So lots of organizations will have manual type reporting. It may be semi-automated, it may be digital, but it may be very labor intensive. Well, with a proper network design and a proper IT structure set up with servers and clients, is that we can look to automate those processes and those reports as well. Now, some other things that we can do, well, we can implement a business intelligence solution, such as business objects. We can implement a data backup system. So maybe in the past you didn't have something as simple as an effective and efficient data backup system. So when we're doing that, we are ensuring that our data is backed up properly and that it's restorable. And then lastly, we can enhance our information and network security. And this is really a big one. And this is something that you're going to see that's improperly designed and set up in a lot of small and medium businesses. And so if you're a consultant, this is something that you can pitch. Because in this day and age, with everything going on in the media, with the hacks of the IRS, with the hacks of OMB, with the hacks of Target, Sony, and all these large corporations, is that we need to look to better enhance our information security. So if you can pitch that you're doing that, if you can pitch that you're going to better protect that company's information, and you can stand behind what you're saying, then that is a really good way to define specific areas of improvement. So when you're planning your design and you're building out your proposal and you're building out your business case and you're defining those specific areas that you're going to improve within the organization, well, to move forward and to start designing and building this network, we need to get a formal buy-in and approval. And so that's what we're going to discuss right now, is that I want you to understand that when you're building this business case, you're really building up a proposal. And so once you have everything in order, once you have your proposal set up, you need to go forward to either your management or to your customer if you are a consultant, and you need to seek both approval and buy-in from them. And so the whole point is that we want to get that approval and that buy-in, because that leads us to getting the resources that we need to move forward. And that's our ultimate goal here in this phase. Our goal is that by doing this proper planning effort, and where we're planning how we're going to design this network by analyzing the business and telling the business how we can improve it, is that we want them to say, okay, good, that looks good. I see how you justified this plan. Let's go ahead and let's move forward. I'm going to go ahead and improve this. I'm going to give you funding that you need. I'm going to give you the IT personnel that you need, and I'm going to give you the time that you need to move forward with this and to go on to the design phase and go on to the building phase. So remember, you have to get the formal buy-in and you have to get the formal approval, and we want to get these resources, and this is what we need to move forward with building our network. So when you are planning and designing a network, or if you're planning or designing anything that's going to alter the way that people work, we end up having things that we call hidden costs. And so what am I talking about? What am I talking about when I'm saying hidden costs? What is a hidden cost? Well, let's go ahead and let's talk about it in this slide. So when we're talking about planning and designing a network, well, it's more than just actually designing the physical and logical network. It's more than planning the equipment purchases. It's more than selecting the proper and necessary software, all based upon the business and technical requirements. It's much more than that. We also need to understand how it changes the way that people work. We need to understand how it affects their jobs and how they're going to react to that. So you need to think outside of the box. You need to understand it from a personnel perspective. You need to understand that networks change the way that people work. And when we're thinking about this, really, it's all about process improvement and change management. So when we are putting a network in place, and for example, if we're putting in a place where business has a lot of paper processes, or we're taking a lot of manual processes and we're automating them, or we're fully automating them, it really does change the way that people work. And so we need to be cognizant that setting up and designing and upgrading networks does change the way that people work. And there's going to be issues that you face. There's going to be lots of issues that you face that you need to combat. And this may cost you time and money and resources. So what are these issues that you're going to face? Well, the first one is resistance to change. So you're going to face people that are resistant to change. They like doing things their way and they don't want to change, even though the business is changing it and it's moving in a modern era. Now, the other thing that you're going to face is training costs. So whenever you upgrade any sort of IT process or IT business process or IT equipment or even a business process, which designing a network will do, is that you have to not only train your end users, but you have to train the IT administrators that are going to be managing as well. Now, whenever you're doing any sort of a network design or IT build-up or network build-out, you need to factor in the cost of your documentation and also ongoing support. So you need to have people there to support it over time. You need to have your desktop support, need to have your network support, and this is going to be long-term costs that people tend to forget. They tend to forget all these little things. They tend to forget resistance to change. They tend to forget training costs. They tend to forget documentation and ongoing support costs. And they also tend to forget transition planning. So what do I mean by transition planning? Well, maybe you consult with somebody to build out your network, but your in-house personnel people are going to be supporting it. So there needs to be transition planning where one group of people take over administrating the network from another group of people. So we need to understand the costs associated with all of these different items down here. We need to understand what it's going to cost us to combat resistance to change and what are the proper business processes that we need to put in place to minimize that. We need to understand what the training costs are going to be. We need to understand what the initial training costs are going to be for administrators and also what the ongoing costs are going to be to train end users as they come into the organization. We need to understand what the documentation costs are going to be when we document the network design, and we need to understand what the ongoing support costs are going to be as well. And then lastly, we need to understand what transition management planning costs are going to be if we transition and we hand over control of the network from one group to the other. So when you're planning and you're designing out your network, you need to consider all of these costs down here. And these are just simple examples. These are really just a few of the simple examples of the different hidden costs that you're going to find. And just remember that it's more than just designing and building that network. We need to include everything that we talked about above as well. So in this video, we're going to talk about some considerations you need to think about when you're planning your network. So let's go ahead and let's talk about some considerations. Well, one of the first things that you need to consider is you need to look at the available technologies that are out there to you. So if you are upgrading your network, if you're an IT administrator or you're a network administrator, you may not be up to date on the latest technology trends. And so one of the things that you need to do is you need to determine what are the latest trends. So for example, maybe you aren't virtualizing your servers. Maybe you can't set up a virtualized server infrastructure. So maybe that's a new trend you can go to. Or maybe you can utilize cloud computing. Maybe you can utilize Amazon's AWS or EC2 infrastructure to decrease your costs as well. So you need to look at all these new available trends and the latest trends to see what fits your needs. And we really need to look at and we need to see what best fits your needs. And when we're talking about what best fits your needs, we're talking about what fits within your financial budget, of course, but we're also talking about what fits best within the business needs. So what meets the business requirements and the business's technical requirements as well. So some basic considerations to consider. Now let's talk about a few more. So some additional considerations that you need to consider when you're doing your initial planning is you need to look at your bandwidth requirements. So what are your bandwidth requirements? What type of speed are you going to need on this network? Is this just a basic office setup where you're just going to be sending a few files back and forth? Or are you a company that's going to be sending large media files back and forth over the network, and it's going to need a lot more bandwidth? So we need to determine, what do we need? Is 10 megabit per second okay? Or do we need gigabit speeds? We need to think about our current business infrastructure and its current size, and also how the business is going to grow in the future as well. So when we're talking about that, we're really talking about scalability with a network. So when we're planning our network, we need to make sure if we need to scale for the future because the business is going to grow, well, we need to make sure that the network is going to be able to scale with it. So we need to plan not only for now, but we need to plan for future growth, and we need to plan for the future as well. So we need to make sure that our network equipment is going to handle that growth. Another thing we need to talk about is our security needs. So we need to determine how we're going to adequately secure our network. And when we're talking about that, we're not only talking based upon what we think we need, but we need to look at the laws and the regulations as well. We need to make sure that we meet those requirements. We need to look at things such as encryption, physical security, and logical security. And a good example of that is to look at your network cabling. A very simple example. Can we get away with using twisted pair, or are we going to have a security concern if we have data emanation and instead we need to go to fiber optic? And then lastly, we need to look at what are any sort of specialized software requirements. So we need to understand what they are. We need to make sure that our network supports them. And a perfect example would be a dentist's office where they have specialized server and client software set up to manage their system, to manage their patients' records, and even do things such as digital x-rays. So we need to make sure that our network supports that as well. So those are just some basic considerations that we need to consider during our initial planning process. So during the planning process, we do need to ask specific questions that revolve around how we're going to design the network. And so when we're interviewing people, when we're surveying how the business operates, we need to think about some specific questions. And they're designed around these items right here. So what are they? Well, the first one is we need to ask questions and we need to determine what type of network do they need. Are they going to need a peer-to-peer design, or are they going to need a client-server architecture? Now, we also need to think about the network cabling that they're going to need. Are they going to be okay with our standard twisted pair cabling, or are we going to have to implement fiber optic? Well, what about wireless? Maybe they need to move around freely within certain areas. Maybe, for example, one department is the design department, and they all have tablets that they design on, and they're all set up on Wi-Fi. So you need to look at the cabling needs as well, and that's based upon the bandwidth that they need, their security concerns, and also the mobility concerns of their devices that are going to be connected to the network. We also need to look at their printer requirements. We need to determine if they're going to need centralized printing, where they have a print server set up, or they have network capable printers that are dispersed throughout the office, or if we can just hook up printers to computers individually. We also need to look at their email requirements. Are we going to set up our own internal email server, or are they going to use an external host that's going to be providing them email services themselves? We also need to look at their data requirements. What type of file server requirements are we going to have? Because that's going to dictate our design as well, and it's going to dictate our bandwidth, and it's also going to dictate just our general design in terms of cabling and everything else. And then lastly, we need to consider our network security requirements. And so when you're talking to the business, we need to determine what type of network security requirements are in place. What type of data is going to be on that network? If it's a corporation, do they have information that's proprietary that they want to keep secure from all their competitors? or if it's a governmental organization, or if it is a medical office building, or a dental office, or a lawyer, is there's going to be private information that they need to secure where they don't want people to have access to them. So for example, if it is governmental, there's certain requirements that you have to follow. Again, if it's medical, there's the HIPAA Act in the US that you have to follow. And then of course, if there's legal information, there's information you have to follow as well. So I also, when you are going through this whole planning process and you're thinking about business process improvement, you're building your business case, well, you also need to think about all these different aspects as well when you're talking to people throughout the organization. You need to think about the network type that they need, the network cabling, their printer requirements, their email requirements, their data requirements, their network security requirements, and many other requirements that's going to affect the network design. Okay, so we're done gathering our information during the planning process, and we put a plan together and we have everything that we think that we need to move forward. So what's the next step? Well, remember when we talked about the overall process? After we plan, we design, and then after we design, we're going to build out and implement that network. So we're going to take everything that we gathered in the planning process, and we're going to take information such as our business needs and our technical requirements, and we're going to take that and we're going to start designing the network. And so what is the designing process from a very high level perspective? Let's go ahead and let's do a quick introduction. And before I get into that, I just want to mention that we are going to spend a section on this designing process. So this is nothing more than just a quick introduction to how it works, because I want you to understand what we'll be discussing later in the course. So what's within this design process? Well, when we're talking about the network design process, the first thing we're going to do is we're going to transform our plans into design. And when I mean a design, I'm talking about a network design. We're going to do a physical topology design. So we're going to determine how we physically lay out the network. And remember, when we went over physical topologies earlier in the course, well, during the design process, this is when you're going to start implementing that. You're going to take that design and do a physical layout. And so you're going to base your design based upon the layout of the actual building itself. And then in addition to that, we're going to do a logical design and a logical layout as well. And this is all about our IP addressing. So in this, we're going to determine our IP addressing schema. And then we're also going to define some design specifications. So for example, maybe we need email servers, maybe we need file servers, maybe we need streaming media servers, maybe we need all sorts of different technical requirements that we need to build into this design. So we're going to take all that and we're going to start designing out the network. We're going to put everything in place, and then we'll take that design and we'll take it to our stakeholders and we'll get their approval to build that network. In this video, we're going to do a recap of the TCP/IP protocol suite, which we introduced earlier in the course, but now we're going to do a deep dive into it in this section. So what is it? Well, it's a suite of protocols that we use to communicate across networks. And we call this the Internet Protocol, and we call this the Internet Protocol because it's a suite that the Internet was built upon. So we use this as one of the primary protocol suites to communicate across the Internet today. And remember, there's two different portions to this. There's the TCP portion and there's the IP portion. Hence, that's why we call it the TCP/IP model. Now remember, this is very similar to the OSI model, which was that conceptual model that we talked about in detail earlier in the course, but this is a simpler model. Remember, there are less layers, so we have 5 versus 7 layers here, and the OSI model was conceptual and the TCP/IP model was actually implemented. And here's our layers. We have the application layer, the transport layer, the network layer, the data link layer, and the physical/network access layer. So let's go ahead and let's start talking about the TCP/IP in detail in the upcoming video. The purpose of this video is to provide you just a quick snapshot of everything that we're going to be covering in this section of the course. So you'll notice that I have all the layers listed out for the TCP/IP protocol suite, and you'll notice is that I have various protocols associated with them. Well, you know what? These aren't even all the different protocols. These are just some of the more common ones, and that's what we're going to be covering in this course. And in addition to talking about them as they're associated to different layers, we're going to talk to them in regards to the type of job or role that they do on the network, whether if it's for diagnostics, communication, management, emailing, and so forth. So we're going to talk to them in regards to the roles as well. So stay tuned. We're going to get into this just on our next video. So see you at the next video. We're going to kick off our discussion talking about network layer protocols, and we're going to talk about these 4 specific protocols that we have on the screen. So we're going to talk about the Address Resolution Protocol, better known as ARP, and then we're going to talk about the Internet Protocol, specifically the Internet Protocol version 4, better known as IPv4, and the Internet Protocol version 6, better known as IPv6. And then lastly, we're going to talk about the Internet Control Messaging Protocol, better known as ICMP. So let's go ahead and get into it on the next video. In this video, we're going to talk about the Address Resolution Protocol, better known as ARP. So what's the purpose of ARP? Well, it resolves IP addresses to MAC addresses. And remember, when we are talking about a computer, it has 2 addresses. It has its logical address assigned by the network, and that's its IP address. For example, 192.168.1.1. And then a MAC address, which is the actual physical address that's burned into the network interface card. So remember, we talked about switches, and switches build a table where they are identifying what port has what MAC address. Well, computers do a similar thing. They have a table within their system where they are aligning the different IP addresses that they know, and they're associating MAC addresses with them. And so, for example, if a computer knows an IP address of a computer that it wants to communicate on the local area network, but it doesn't know the MAC address, it can send out an ARP request. Or if it knows the MAC address and it doesn't know the IP address, it can send out a reverse ARP request. And so the whole point of this is to use this protocol to identify the MAC address or the IP address of a system where it doesn't know one or the other and only knows one. And so without this protocol, we really can't communicate across the network, because the first thing you do when you plug a computer in and put it onto a network is that it doesn't know anybody's IP addresses. It doesn't know anybody's MAC addresses, but over time it's going to learn them, and it has to use the ARP request protocol to do so. So let's go ahead and see what it looks like. And so, for example, if I wanted to look at my ARP table, I could go to my command line prompt and type in ARP space -A, and it's going to show me here's the IP addresses and here's the associated MAC addresses. And let me pause the video for 1 second, and I'll pull up my command line and I'll do this actual request. So I'll be back in 1 second. Okay, so I went ahead and I pulled up my command prompt, and I had to run this as administrator. So if you are on a Windows machine, a Windows 7 or greater, you have to right click and tell it to run as administrator. Otherwise, this command won't work. Now, the command itself is very simple. So it's ARP space -A and enter. And now it's going to show me the ARP table in my physical computer, and it's going to show me the IP addresses here and the associated MAC addresses. Now, for example, if it knew this IP address here, but it didn't know the associated MAC address, it would send out an ARP request on the network, and I'll show exactly how this works from a high-level point of view on the next slide. But it'll send out a request, and it'll say, hey, who is the MAC address of 192.168.0.100 on this network? And the computer that has that IP address is going to say, okay, that's my IP address. Let me tell you what my MAC address is. And we can do a reverse ARP request if we know the MAC address and we don't know the IP address. We can say, you know, what's the IP address of this MAC address here? And the computer on the network will go ahead and respond. So that's that. Let me go ahead and pull up the next slide, and let's talk about how this process works from a very high level perspective. Now, this is not all the nitty-gritty details that actually happens on a network, but this just gives you, as somebody that's being introduced to networks, a high level overview of how this works. So for example, we have 2 computers on our network, and we have this guy, it's 192.168.1.110, and then we have 192.168.1.115. And so this guy over here wants to communicate with him, but he doesn't know his MAC address. So he sends out an ARP request saying, I need the MAC address of this IP address, this 192.168.1.115. It goes out and it goes across the network, and it does what we call is an ARP broadcast. So it goes to the switch and it tells the switch, I need to do an ARP broadcast. Send this request out on all the ports where there's a cable connected, and the switch will say, okay, I'm going to send this out on all the cables that are connected. And then it's going to go to every single computer, and they're going to get that ARP request. They're going to look at that IP address and see if it matches theirs. And if it does, they'll respond. And this guy says, oh, okay, well, I'm this guy. I am 192.168.115. Here's my MAC address. And so he'll go ahead and he'll respond to his MAC address request to this computer. And now this computer is going to have the associated MAC address. And that's how this works in a nutshell from a high-level perspective. So that's our introduction to ARP. If If you have any further questions about it, please let me know. If not, thanks for watching, and we'll see you at the next video. In this video, we're going to do a quick introduction to the Internet Protocol version 4, and then in the next video, we're going to do the same thing for the Internet Protocol version 6. Now, I'm not going to talk a lot about how they work because I have a later section in the course detailed solely to IP addressing, so this is just going to be an overview of how they work and why we use them. So what is IP? Well, IP stands for the Internet Protocol, like I just said, and it's really the primary protocol for moving data across the internet from one network to the next. So when we're talking about moving data over wide area networks, that's what this is all about. And we call this the moving truck of the internet because this is all about moving data from one network to the next across wide area networks. And so, for example, if I wanted to send a packet of information from my computer in the United States to China, I would use IP addressing, and I would use my router to send it out across wide area networks. And if we think about this, a good example would be a moving truck analogy. So let's say I was going to pack up and I was going to move across country, let's say to Washington, D.C. I would have to pack up all of my boxes and I'd load them into that moving truck, and I'd drive that moving truck across the country on the different highways, and eventually I would get to Washington, D.C. So that's what this is all about. It's all about getting that information, getting that stuff from point A to point B. And its primary job is simply just to get that data there, and that's what it focuses on, and that's what it does really well. So it is exceptionally well, and it does a really great job with moving data back and forth throughout the internet via routing. And remember, we talked about routing in a previous lecture. We talked about how it works and how routers use routing protocols to send packets of information from one router to the next, and they determine the best route to get it there. Well, that's what IP addressing is all about. So what it does is that, like we said when we talked about our previous lecture, we did the introduction to routing, it looks at the destination IP address and it looks at its routing table, and it uses its routing protocols, and it determines what's the best way to get it onto the next router to get it to its destination. Now, one unique thing about IP addressing is that it's a connectionless protocol. So it fires off this packet to the next router and it forgets, and it's done. It says, my job is done here. I've taken this packet, I've determined the best method to get it to the next router to get us to its destination. I'm going to fire it off and then I'm done. So it doesn't have any sort of method to check to make sure it got there. That's what other protocols are all about. IP doesn't do any of this, and we have to talk about other protocols for that. So just remember, IP just fires it off and it forgets. Now, let's do a quick introduction to the formatting. Remember, the formatting again is the dotted decimal notation, the 192.168.1.1. And if you break this up, we can break this up into smaller bits into binary. And when we break it up into binary, what it is that it's a 32-bit address. And when we talk about a 32-bit, there's 4 bytes. And so we have a byte here, we have a byte here, we have a byte here, and a byte here. And if you do the math, of adding up these 32 bits and we do our binary math, this gives us a total of possible of this many addresses. So 4.2 billion addresses potentially usable with IP version 4. Now, the crazy thing is that we're actually running out of IPv4 addresses because it's not that efficient, and so we're starting to make the move to IPv6. And that's what the next lecture is all about. So let's go ahead and let's get into that, and let's talk about IPv6 on our next video. In our previous video, we talked about IP version 4 and we did an introduction to it. And remember, I talked about how we're running out of IP version 4 addresses, how there's only 4.3 billion addresses. And if you think about that, that's a lot of addresses. But if you think about the world population and how many different devices we have that connects to the internet, well, now you can see why we're running out of addresses. And so we're running out of addresses, and so we created IP version 6, and that's what we're going to talk about in this video. We're going to do a quick introduction to IPv6. So IPv6 was created to mitigate the issue of us running out of IP addresses so we can continue to connect devices to networks and the internet. Now, if you look at the difference, when we talked about IP version 4, it's a 32-bit address, and IPv6 is a 128-bit address. Now, when you determine the math to determine how many addresses it is, it's 2 to the power of how many bits. So for IPv4, it was 2 to the power of 32, which equal to roughly 4.3 billion addresses. Well, 2 to the power of 128 addresses is 340 trillion addresses. And there's the actual amount on the screen. And if you take that and you divide it by our world population, you'll see that we're never going to run out of addresses with IPv6, just because there's so many potential combinations of addresses. Now, I did not put the format on here because it's a very complex hexadecimal format and you don't need to understand it to really see why we went to IPv6. And also some other reasons why we went to IPv6 is that number one, it improves routing, so it makes the routing process more efficient. Number two, it includes some cybersecurity, and I actually should say network security features within it to make it more secure. And so overall, by having more addresses, by improving its routing functionality and improving its network security functionality, it's just much more efficient overall. And that's going to conclude our quick introductory lecture to IPv6. We'll be talking about IP addressing much more in our dedicated section on IP addressing later in this course. In this video, we're going to talk about the Internet Control Message Protocol, better known as ICMP or simply ping. Now, the way that this works is that we use this commonly in the networking world and in the IT support world for troubleshooting network connectivity issues. And the way that it works is that you open up your command prompt and you type in ping and whatever device you want to communicate with, whether you know the IP address or you know the domain name, and you're going to send them a ping. And your computer is going to ping them, and if it can communicate with them, that device is going to ping you back and say, okay, I heard you okay. And we call this an echo request and an echo reply. So you're going to be sending the echo request, and if they can communicate back, they're going to send an echo reply. If for some reason they can't communicate back, they're going to send a destination unreachable. And so we use this very commonly in the network support and desktop support realm, where if we're on the system and that system can't get out to the network, we can simply use a ping command to see if we can communicate with one of our servers or one of the other desktop systems. And if we can't communicate, then we know that we have some sort of an issue where we have to troubleshoot that. So here's a quick example here on the screen, and I am going to do a live demonstration, but here's a quick example of me pinging google.com. And it shows that I type in ping space google.com, that's the command. And it says here pinging google.com, and here's Google's IP address with 32 bytes of information. And then google.com replies, and it sends 4 replies saying, I was able to get your ping. Here's my response. I'm responding again with this 32 bits of information. And it took 21 milliseconds for the first one and approximately 20 milliseconds for the other one. And then we can also look down here to see if we had any packets lost, and which shows that we sent 4 packets, we received 4 replies, and we didn't have any lost packets, so we're able to communicate just fine with them. Now let me go ahead and let me pull up my command prompt because I want to show you how this works. So rather than just showing you on the screen, we can go ahead and just to show you that this is a quite complex tool. There are different switches, so there's different options on here if we wanted to provide other information. So I'll do a ping space dash space question mark, and you'll notice that, and let me scroll this down to see if I can get this any bigger. You'll notice that there's a lot of different options, so you can tell it to do all sorts of different things here. But for us, we're just going to use the very basic ping functionality here. So I'm going to scroll to right here, and let's just ping yahoo.com. And here we go. So it says I pinged yahoo.com, and here's its IP address, and it shows the response, tells me how long it took, tells me how many packets of information I sent, how many were received, how many were lost. So we have 0% loss, so we're not having any connectivity issues. Now I am going to go ahead and ping my router. So let me show you, you can use this for an IP address as well. So let me get my IP config, and let me do this command. So I'm going to do an IP config -all, and I am going to get the IP address of my gateway, which is my router on my network. And so let's go ahead and find out what that is. So my default gateway is 192.168.0.1. So let me ping my router. So I'm pinging my router, and you'll notice that I'm able to communicate just fine. Now what I'm going to do is I'm going to pause the video in a second. I'm going to go downstairs, I'm going to unplug my router, and then I'm going to try to ping it again, and then we'll see what happens when it can't reach a device. So I'm going to go ahead and pause the video. I'll be back in 1 second. Okay, so I went ahead and I turned off my router, and I put the command in here, ping 192.168.0.1, and type enter, and look what it's going to say. Pinging that IP address, but destination host is unreachable. So if you are having connectivity issues, you're going to get something like this, and if it's intermittent, maybe some of them are going to go through and other ones are going to be unreachable. So that's our quick introduction to ICMP or ping in a nutshell. And I do recommend that you play around with this. If you want to find out more about it, simply do the ping dash question mark. And you can look at all the different options here, and you can go ahead and look at the syntax. And you can play around with this, and you can ping different websites and different network devices just to get an idea of how it works. Now, one thing to remember is that certain network devices are going to be set up to not respond to pings. So for example, certain web servers, certain different network devices on different networks. So if you're doing it at work and it's not responding, then it's set up not to respond. And they do that for bandwidth concerns. They don't want different devices responding to pings. And it's also a network security concern because it can be used for a denial of service attack. So you don't want your devices, certain devices on the network, to respond to pings in regards to that request. Anyways, if you do have any questions about this, go ahead and just Google it, or you can reach out to me with any questions. Thanks for watching, and we'll see you at the next video. In this section, we're going to talk about two vitally important transport layer protocols: the Transmission Control Protocol, better known as TCP, and the User Datagram Protocol, better known as UDP. So why are they so vitally important? Well, remember when we talked about our IP addressing, where it uses routing and it just sends and forgets? It doesn't have any sort of error checking, or it doesn't determine if something was received or not. Well, that's where TCP and UDP come in. They are the two protocols that we use to determine how we want to send our data and how reliable we want that data to be when we send it. So let's go ahead and let's get into it, and let's kick off our conversation talking about TCP. In this video, we're going to talk about the Transmission Control Protocol, better known as TCP. So when we're talking about our transport layer protocols, we have TCP and we have UDP. Now, one of them is connection oriented and the other one is not connection oriented. And this will make a lot more sense as we go through this lecture. So TCP is connection oriented, and before it sends any data to any other device, it does what we call is a three-way handshake. And so what is this three-way handshake? Well, the device that wants to communicate with the other device on the network, before it starts to communicate, so for example, you down here, let's say that you want to communicate with Gmail to check your emails. Before you start transmitting data back and forth, the first thing you're going to say is that, hey, Gmail, I want to communicate with you, and this is called the SYN portion of it. So number one, you send a SYN request to Gmail. And then if Gmail is able to communicate, they will acknowledge your request, which is what we call the SYN ACK. And right here we have our SYN ACK from Gmail. So Gmail's going to receive that request, and then it's going to respond. And then lastly, you're going to acknowledge that you received Gmail's acknowledgement that it's ready to communicate, and that's called our final ACK. So that's our ACK, and that's why it's a three-way handshake. So let's go over it one more time. Number one, first you go to Gmail and you say, I want to communicate. That's number one. Number two, Gmail is going to confirm that it can communicate. So that's the second part. And thirdly, you're going to confirm with Gmail that you are ready to communicate. And once you complete all three steps, 1, 2, and 3, then you're able to send data back and forth reliably. And so this is why it's reliable, because it sets up this connection. And so we have this session set up between both you and Gmail before any data is ever sent. And so TCP is considered a reliable delivery method because of this three-way handshake and this virtual connection between both you and Gmail. And the reason why this is reliable is because it ensures that the data is delivered to Gmail that you send to it, or that the data that Gmail is sending to you is delivered to you through what we call is error checking. So what it does is that it does this data sequencing where the packets have a specific number assigned to them, and it's in order, let's say for example 1 to 10. And if for some reason you don't receive one of them and you don't respond to Gmail saying I received it, Gmail is going to go ahead and resend it. And so that's why TCP is a reliable connection oriented method of sending data. So let's go ahead and let's flip to the second slide. And this is a screenshot of Wireshark. Wireshark is a different type of software that we in the IT world can use to listen to information or visualize information as it goes through a network. So anything that comes to your system, you can have Network Shark or Wireshark set on a mode where it's listening and it's outputting all that information. And here, right here, is a simple example of setting up that three-way handshake. So we have a device here, a source device and a destination device. The source sets up a request saying, I want to communicate with you. The other device says, okay, I got it with the send ACK. I'm going to respond to you that I'm ready to communicate. And then the device that did the initial request says, okay, I received your acknowledgement. I'm going to acknowledge that. Let's go ahead and let's start sending data. So we have our three-way handshake, part 1, part 2, and part 3. And so that's our quick introduction to TCP. Now on the next slide, let's go ahead and let's start looking at UDP in our next lecture. In this video, we're going to talk about the user datagram protocol, better known as UDP. So remember, we talked about TCP in the previous video, and we said that it's connection oriented and it's very reliable, and it has retransmissions of data when data isn't received. Well, on the flip side, UDP does not do any of that. UDP is a scaled down economic version of TCP, because when you add all this extra functionality onto a protocol like TCP, well, it requires a lot of resources, and you'll see this in the next video. Now on the flip side, TCP is reliable, but UDP is not at all. It's connectionless and it's unreliable. And it doesn't do any sort of data retransmission. So it just pretty much sends data and it says, I'm done with it. I did my best effort. I sent the data. Hopefully it gets there. If it doesn't, oh well, there's nothing I can do about it. And you may be thinking, well, what's the purpose of using something like UDP? Don't you want all of your information that's sent across the network to be reliable and to make sure that that data is actually sent? Well, in certain instances, yes, but in others, no, you don't need it at all. In fact, there are specific reasons why you're going to want to use a protocol like UDP where you don't retransmit data, you don't care if a connection is set up or not, and you don't care if it's reliable or not. So let's think about some examples, and I put some on the screen. So for example, some real live time data that's streaming. For example, a phone call, if you're doing a voice over IP. You're going to have some data loss. You might have some of that connection where the audio doesn't come through, but you're still able to understand what the person's saying. And so it makes it a lot more economical for both you in regards to how much data you need to transmit back and forth and how much you need to pay your internet service provider, but it also makes it more economical for them in regards to how much they need to scale up their network to support VoIP. Another example would be video streaming. So for example, live video streaming. We're not talking about YouTube, we're talking about actual maybe connecting to a live video stream. For example, if you're able to find a live video stream of a sporting game or a sporting match, then it's okay if you have a couple of bits of information or a couple of packets of information here and there that don't get through, because for the most part, your system is going to be able to decode what that is. And you may have a little bit of jarbled information here and there, but you're going to be able to watch that live streaming video. And then same thing for audio streams. If you're doing something like listening to a radio station or a podcast that's live over the internet, again, it's okay if we have a little bit of data loss here and there. But in other instances, you want to make sure that data gets there. For example, where you're connecting securely and you're doing some online banking, well, you want to make sure that your data gets there, and if it doesn't, then they respond and they retransmit. So there's other instances where we want it to be secure, we want to have that retransmission, we want it to be reliable, but in instances like this where we're talking about, for example, real-time data, where we're talking about, for example, VoIP, real-time video streams, real-time audio streams, we don't care, and there really is no reason to have retransmission of data because it's live. It is not data that you're going to wait and pause to watch it. If it's live, then the data is already gone and it really doesn't matter. So that is UDP, and those are the instances and why we would use it. Now in the next video, I'm going to do a bit comparison to show you the difference between UDP and TCP, and just to show you how many more resources are required to send TCP over UDP. In this video, we're going to do a comparison between TCP and UDP, and on this first slide, I have a graphic representation of the bits of information required to send a TCP versus a UDP packet. And so here on the left, this is a TCP packet. And here on the right is a UDP packet. And now everywhere where you see the 16 bits or 16 over here or 32, this is the amount of bits of information that we have to add on. And because TCP is very robust, it has a lot of extra information on here. And so for example, our sequence number for our packets to make sure they get there, 32 bits right there. Another 32 bits of information for our acknowledgement number to acknowledge that we received the information. And then it also has some additional information in here as well to make sure that it gets there. So if you add all this up, there's a lot of extra information that we need to send across the network. Now let's look at UDP. We just have our source and destination information are linked and a very simple checksum to make sure that the data is not corrupt. And so if we look at this, we have a total of 64 bits of information added on. Over here, just adding these two together, that's 64, not adding on any of this other information. So you can see why people want to use UDP when they can, because it's a lot more efficient than TCP in regards to bandwidth cost. So when we want reliability and we want assurance to make sure our data gets there, there's a cost associated with it. There's a monetary cost in regards to making sure that our network scales up with it, but there's also a bandwidth cost as well. So it's going to take up bandwidth in regards to using TCP over UDP. Now, we already talked about this, but we're going to go ahead and do a bit of a recap. So, you only want to use TCP when you need to have data sent reliably and you want to make sure it gets there. And so, for example, maybe file transfers online or online baking sessions online. In other instances, if you don't need it to be reliable, if you just want it to be fast and economical, then you're going to want to use UDP. And a good example that we did in our previous video was our voice over IP phone call, where it's going to get the job done. We don't need TCP, and UDP is going to be working just fine. So, just to sum up, in certain instances, we want reliability, we want that retransmission of data, we want our session set up before we do any sort of communicating, we want to use TCP. But on other instances, for example, live streaming data, where we're not worried about all that, and something like UDP is going to get the job done, then we're going to go ahead and we want to choose UDP. So that's going to go ahead and conclude this lecture. If you have any questions about TCP and UDP, please let me know. If not, thanks for watching, and we'll see you at the next lecture. In this section of the course, we're going to talk about our TCP/IP application layer protocols. And as you see on the screen, there's quite a bit that we're going to cover. So I broke them down into subcategories, and we're going to talk to them in regards to the different categories that they're in. So we're going to talk about management related protocols, and we're not talking about business management, I'm talking about network management. We're going to talk about remote authentication protocols, protocols that allow you to remote authenticate into other systems. Then we're going to talk about mail application protocols, so the different protocols that allow you to send emails back and forth across the internet. And then we're going to talk about browser protocols after that. And so those are the different protocols that allow you to get on your internet browser and use the internet to browse and surf the internet. And then lastly, we're going to talk about voice over IP protocols, the protocols that allow you to do phone calls over your computer, over the internet, or over a network. So let's go ahead and let's talk about our management protocols in the next video. In this video, we're going to talk about our application layer management protocols. And the first protocol we're going to talk about is called DNS, or Domain Name Services. So what does DNS do? Well, DNS converts a domain name such as google.com into its associated IP address such as 74.125.224.52. So why is this important? Well, for example, if you're on your work's network and you want to go out to a website, for example, my website, microgrinder.com, and if your network doesn't know how to get there, it can use its DNS server to look that up and determine what the IP address is for that domain name, and then it can log it. And so we can have a DNS server set up to manage all of those records and to allow you to be able to communicate by using a domain name rather than an IP address. Now, a really easy way to do an example of this on your computer is you can do an NSLOOKUP. And let me go ahead and show you how that works right now. So again, we're going to use our command prompt just about every time for everything that we want to do. So let me go ahead and type up my command prompt and pull it over. And I'll slide it over here so it's not in the way. So you're going to type in NSLOOKUP. And then you can just type in a domain name. So for example, we'll do yahoo.com. And we'll press enter. And what it's going to do, it's going to go ahead and take a look, and it's going to tell us the associated IP addresses. And for example, with yahoo.com, it has more than one IP address because they're such a big website that they're going to need more than one IP address associated with them. So if we look at this, now we know that the IP addresses associated with DNS for google.com are these ones right here. Now, the next protocol that we want to look at is called the network time protocol. And this is what syncs up your system with the clocks on the internet. And for example, we can have it to sync automatically. So for example, I have a system set up to sync to nist.gov. They have a time server set up over there, an NTP server. And what it does is that it keeps your system up to date with what's on the network. So why is this important? Well, for example, if you have an authentication server, you want to make sure that the times are synced up with your different desktops where people are going to be logging in, because you can set up day and time restrictions. And if you have a big discrepancy between the dates and the times on the desktop systems that are the client machines and the server, then you're going to have issues with your authentication. So it's important to have an NTP server either set up on your local network or to have your systems get their time information from one of the bigger ones such as nist.gov. Now, the last management protocol that we want to look at is called the Simple Network Management Protocol. And there's been multiple versions. There's a version 1, version 2, and version 3. And what this allows us to do is allows us to go out to our network devices such as our routers, our firewalls, and our switches to collect data information on them based upon what's going on the network. And so we can use SMTP to go ahead and connect to those devices and get information on them, and also in certain instances to update and manipulate that network information. So it's great for network management, especially if you're a network administrator, and also for maintenance. Now you'll notice that there's V1 and V3. Typically you're going to see V3, but I did include V1 on here because originally all the information was in clear text format. But now we know that we want to encrypt and protect everything with everything that's going on in the news, with all of our breaches and all of our attacks from all these different hackers out there in the world. Well, now we know we don't want to have data in clear text, because if we do that, then we leave it wide open and available for people to take from us. So now with V3, it's now encrypted. So those are the 3 different protocols that we wanted to look at that are our management protocols for the application layer. And so we talked about, again, our DNS, which is converting domain names into IP addresses, our NTP, which allows us to get our clock information from a central server to synchronize our client machines with our servers, and then lastly our SMTP, which we use to pull data off of our network devices to manage them. In this video, we're going to talk about our application layer remote communication protocols, and there's 2 that we want to talk about. We want to talk about Telnet and SSH. So what is Telnet? Well, Telnet stands for Telecommunication Network, and SSH stands for Secure Shell. Now, they both do the exact same thing. They both are designed to allow you to use a protocol that interacts with an application so you can remotely log into a device on the network, whether that's a router, a switch, or a server. And the goal with having these is that you can log in remotely and you can do remote administration on those devices without having to physically be in front of them. So that's why we use Telnet, and that's why we use SSH. Now, we don't use Telnet anymore because it's antiquated and it sends everything across the network in plain text. It doesn't encrypt anything, so everything's unencrypted. And so that's a cybersecurity and network security concern. So Telnet is an antiquated protocol. It's not used anymore. And if it is, it shouldn't be used by people that are using it. Instead, everybody is using SSH or Secure Shell. And it looks a lot like Telnet, it acts a lot like Telnet, however, its communication is encrypted. And there's a very popular free client that a lot of people use called PuTTY SSH. So these are the 2 protocols, and I just want to show you a couple screenshots. But before I get to that, one thing I want to highlight is that they both use TCP. So if you notice on the slide, both Telnet and SSH use TCP because they have to set up that 3-way handshake when they're setting up their session. Now let's go ahead and let's take a look. With Telnet being an older protocol, a lot of people use a console or a command prompt to simply access the device. So you would simply go to your command prompt, or you would go to your console and you would type in Telnet, the IP address, and the port number you want to communicate on. And localhost is the same thing as saying 127.0.0.1, meaning that you're trying to connect to your actual device. And here is a screenshot of PuTTY. PuTTY is an actual application that you would use. You would use this instead of using your console. So a lot of people use an actual software suite like PuTTY instead of console when they're using SSH. And so here's just a quick snapshot. If anybody is interested, you can simply go out to the internet and you can do a quick Google search for PuTTY, SSH, or simply PuTTY, and this should come up, and you can play around with this if you want, if you have a device where you can try SSHing into it. So that's going to go ahead and conclude our quick introduction lecture to our remote communication protocols in the TCP/IP protocol suite, SSH, and Telnet. In this video, we're going to talk about the file transfer application protocols in the application layer of the TCP/IP protocol suite. So there's two different protocols that we can use. The first one is file transfer protocol, commonly referred to as FTP. And the second one is trivial file transfer protocol, which is refers to as TFTP as the acronym. Now you'll notice that one uses TCP and the other one uses UDP. So file transfer protocol uses TCP and trivial file transfer protocol uses UDP. So we're not going to set up a session with TFTP, but with FTP we're going to set up a session with a three-way handshake. And that's going to make a lot more sense when I go through the features between the two. So what's the main goal with FTP and TFTP? Well, the goal is to be able to transfer files back and forth over a network with these protocols, and that's what they do. So their main goal in life is to be able to transfer files between systems, whether it be your laptop and a server or a network device with another network device. Now with file transfer protocol, FTP, it authenticates with the username and password. So to be able to use FTP, for example, if I wanted to upload files onto my website and I wanted to use FTP, I would have to have a username and password set up. And if I don't supply them with my username and password, it's going to reject me and it's not going to set up that session with TCP. And with FTP, it's full featured. So what I mean by it's full featured? Well, it can do all sorts of functionality. It can list all the files on the remote system you're connecting to. You can add files, you can add folders, you can delete them off, you can upload files, and you can download files. So if you think about your interface on your system where you have a folder and you can add, remove, and everything, it's very similar to that. Now on the flip side, we have TFTP, our Trivial File Transfer Protocol. This is a very simple version of FTP. So think about a no-frills type of version of FTP. It can only send and receive files. It's not going to be able to browse a directory. It's not going to tell you what's on that directory. So for example, if you connect, it's not going to show you what's on there. You can only send something, you can only receive something, and there's no authentication. So now let's talk about, well, why would you ever want to use TFTP over FTP? Well, a good example would be a company that's a software company. For example, FileZilla. FileZilla is a company that creates an application for file transfer protocols. They have a simple software application that you can use to do FTP. Now, people only want to be able to download that from their site. They don't need to browse a directory. The company doesn't want people to browse a directory, so they can set it up where people can download their software with TFTP, where they go to their site and there's a link to an FTP page where there's no authentication to get in, where people can't browse a directory and they can only download that software suite. So that's an example where you'd want to use TFTP because it's very lightweight. Remember when we looked at TCP versus UDP, UDP is very lightweight, so you can set it up for that reason. Now on the flip side, why would we want to use FTP? Well, for example, like me with my website, I don't want just anybody having access to my files. I only want people that I give access to my files to have access, and they can have the list of functionality that I want them to have. And so that's where we'd want to use FTP. Now let me go ahead and show you what it looks like. I do have an example of FTP FileZilla software here listed on this slide. And this is what it looks like. This is an older version of a screenshot. This is me connecting to one of my older websites, amiibo.net. And you'll notice that I'm logged in with my account, aeharden@amiibo.net. So I set that as my username, and I had to put a password in as well to connect. And it shows me connecting to this, and it shows me getting access to it. Now here's my local system, and here is the directory of the web server. And what I can do is I can drag and drop files back and forth. I can edit the directories. I can do pretty much anything that I would be able to do on my local system because I have full control over this. So FTP softwares, and specifically FileZilla, it is a very common software client that you're going to see in a lot of places. And if you're ever interested in checking it out, all you have to do is go to the internet and you just simply go to FileZilla. And let me go ahead and scroll that in over here. You go to FileZilla and you just Google that, filezilla-project.org, and you can download it for free. So if I go to the home page, you can download it right here. And that's it. So that's our quick introduction to using FTP and TFTP and our different protocols that we use for file transfer over the internet or a network. In this video, we're going to talk about the email application protocols that we use on a daily basis that are in the application layer of the TCP/IP protocol suite. So what are they? Well, there's SMTP, which stands for Simple Mail Transfer Protocol, POP3, which stands for Post Office Protocol, and IMAP4, which stands for Internet Message Access Protocol. So how are they the same, and how do they differ, and how do we use all three of them? Well, regardless if you're using a web-based or if you're using Outlook, you are using one of these protocols or a combination of them. Now, SMTP and POP3 have been around for quite some time, and IMAP4 is a newer version. So let's start with SMTP. SMTP is a protocol that we use for sending emails. So it allows you to transfer emails between different mail servers. So for example, if you're on Gmail or if you are on Outlook and you're typing up an email and you send it to your mail server to send it off, you're going to use SMTP to send that email from your browser with Gmail or your Outlook client off to that mail server for it to be sent off to another email server. Now, what about if you want to receive emails? Because we all want to receive emails. We're not just sending them. Well, if we want to receive emails, we have to use POP3. So there's a different protocol for sending and receiving of emails. So if you go to Outlook and you hit the send and receive all and you want to download all your emails, or if you log into Gmail and you want to see the emails, well, it's going to use POP3. So POP3 is what's going to be used to deliver those emails from the mail server to your client machine. And you'll notice here that I said it's designed for intermittent connectivity. What does that mean? Well, it means that it's only going to query and send a request to the mail server whenever you ask it to. So for example, if you have Outlook, you set it to check for new mail every 5 minutes or every 10 minutes. Well, that's what we're going to do. It's set up to be used intermittently, and it's going to connect on a regular basis to download those new emails. So really, if you want to connect to an email server and you want to send and receive emails, all you need is SMTP and POP3. However, you can also use IMAP4. So IMAP4 is a bit different in the way that it works. And let's go ahead and let's read this. So it allows users to access emails on the email server and either read them on the server or download them to your machine. So for example, with my iPhone, I have it set up for IMAP, and I can either set it up to have me just read what's on the email server itself and have it stay on there, or I can have it download it to my iPhone and delete it off the server. And it's based upon your preference on what you want to do. Now, the reason why we have IMAP is that, for example, if you have multiple different machines that you want to access your emails on, for example, if you have an iPhone like me, and then I have my main desktop machine where I have Outlook on there. Well, I wanted to store all my emails in Outlook, but before I get to that point, I still want to be able to access them on the go, but I still want them to be available so I can download them onto my Outlook as well. So I'll set up IMAP on my iPhone so I can access them and read all the emails on the server, but not download them. So I'm simply looking at my emails on the server itself. However, when I get home and I open my Outlook, I'm going to use SMTP and POP3, and I'm going to use POP3 to get all my emails off the server, and then when they're off the server, it's going to delete them. So that's why you would use IMAP4 over POP3 or SMTP. Now, you're always going to use SMTP to send, but to receive them, you can either use POP3 or IMAP, or you can use a combination of both if you have multiple devices. And that's really all there is to it when we're talking about email application protocols in the TCP/IP protocol suite. In this video, we're going to talk about the internet browser application protocols that we use to browse the internet on a regular basis. And there's three that we want to talk about. So the first one is one that we're very common with. It's our HTTP or Hypertext Transfer Protocol. And this is the main protocol that we all use to browse the internet. So whenever you go to a website domain name such as google.com or Yahoo or Facebook, the main protocol that was set up a long time ago is HTTP. Now, in addition to HTTP, there's HTTPS. This is Hypertext Transfer Protocol Secure. So what's the difference? Well, this provides access to the internet in a secure fashion, meaning it encrypts the website. So for example, if you go to Gmail, it's going to be HTTPS, or if you go to your banking website, it's going to be HTTPS, and it's going to encrypt all your data so that communication that you have back and forth with that web server, it's going to be secure. Now you'll notice that all of these operate on TCP because they set up that three-way handshake. So HTTP, HTTPS, and the encryption methodologies that they use all use TCP. So none of them are using UDP. Now, what do we talk about when we're saying that HTTP encrypts our data? Well, it uses TLS/SSL. So there's two different types of protocols for securing our HTTP communication, and one is called transport layer security, and the other one is called secure socket layers. So you've probably heard of SSL, and the newer one is TSL. And what these are cryptographic protocols that takes all the information that you're going to communicate with and it encrypts it with some sort of an algorithm where it's going to be secure to the naked eye. So if somebody is doing a man-in-the-middle attack and they're pulling your data, or they're eavesdropping on your network and they have Wireshark and they're listening in and they're pulling the data off your network, if it's plain text, they're going to see everything that you're sending. But if it's encrypted with TLS or SSL, it's just going to be a bunch of jarbled characters where they're not going to be able to make it out unless they break that encryption. So SSL has been around for quite some time, and some people still use it. So when I mean some people still use it, certain web hosting companies still use it. But TLS is a newer encryption algorithm technology and protocol that's replacing SSL. And so you're going to see more often TLS over SSL. Now, from a consumer point of view, if you go to the internet, you're not going to know if it's SSL or TLS simply by seeing HTTPS. But if you are in the IT industry and you know how to identify it, you're going to be able to understand one is going to be TLS and the other one is going to be SSL. Just understand that when you're on the internet and if you're typing in a name, if it has HTTPS in front of the domain name, that means it's secure. If it has HTTP or there's nothing, that means that it's all in plain text. And let's just do a quick example. So here's my website, microgrinder.com. You'll notice that there's no HTTPS, and then when I hover over here, you'll see that it's just HTTP:// and my domain name. So that means that anybody that visits my website, if they're communicating back and forth with my website where they're browsing videos or whatnot, all that data coming back and forth is going to be in plain text. Now, if I go to, for example, let's go to Chase, and this is a bank, and you'll notice that everything is in HTTPS. So anything that you do on Chase's website is going to be encrypted by default. And that's the big difference. And you know, even a lot of the bigger websites, for example, Facebook now, in the past, it used to be HTTP. So I remember when I taught this class about 3 years ago in a classroom at a university, and at that point in time, Facebook was by default HTTP. So they weren't encrypting this information by default when you were logging in. Now by default, it is HTTPS. And you'll also see this lock symbol too. And this means that their security certificate is confirmed and verified by a third-party person that says this is secure. And so you're always looking for this lock symbol as well. And you'll notice there's no lock symbol over here. We just have this basic information, and we know that this is not secure. So that's going to go ahead and conclude our introductory lecture to HTTP, HTTPS, and TLS and SSL. In this video, we're going to talk about voice over IP protocols in the application layer of the TCP/IP protocol suite. So remember I talked about using UDP for things such as real-time information, such as phone calls and video calls. Well, this is where this comes into play. But the interesting thing with voice over IP is that it uses a combination of two different protocols, and one is TCP and the other is UDP. So let's go ahead and let's talk about them so this all makes sense. So the first protocol we want to talk about is the Session Initiation Protocol, referred to as SIP. Now this uses TCP to set up and tear down voice and video calls over the internet. So to set up that initial session communication, it uses that three-way handshake, and it uses TCP for voice over IP phone calls. So for example, for me to log into Skype and for me to send a request to call somebody, it's going to use SIP and it's going to use TCP IP. But however, once that phone call starts, to transfer that audio and video data back and forth for Skype, it's going to use the real-time transfer protocol, better known as RTP. And this is going to be using that UDP connectionless protocol, where it's just going to be sending data back and forth without resending and retransmitting data and making sure that it got there. So it uses TCP to set up that phone call, but for the actual phone call itself, voice over IP uses RTP, which is UDP. And so this is going to be fairly common, whether it's Skype or it's something else where you're using voice over IP on the internet to communicate back and forth. It's going to use that TCP to set up the communication, then it's going to use that lightweight connectionless UDP method to send it back and forth. And sometimes it works great, and other times it's terrible. And I'll give you an example. I'm a poker coach as well, and I use Skype to do my coaching sessions with my students. And we use a combination of a Skype phone call, and sometimes we'll do screen sharing if I'm watching them play and I'm providing commentary or feedback, or if I am providing them, strategy and theory sessions where I am sharing my screen and providing them information. Well, last night I had a student, he's over on the East Coast, and I'm in California on the West Coast of the United States. Well, what happened was he was having connectivity issues with his internet, and because Skype uses VoIP, it uses RTP for the actual transferring of the audio and video. Well, we were having lots of major lag in the video where it would stop, and then all of a sudden it would pick up slowly, and then it would be fine. And then the audio was just very sketchy where it was coming in and out. So RTP is not a great protocol to be using when you're having connectivity issues on your internet or your network connection. However, when you have a stable connection, it works fine. So you're going to find that, you're going to have issues with UDP. It's not going to be perfect all the time when you're using it for protocols like RTP and especially VoIP. And for those of you that have never done a VoIP call, if you do a VoIP call and you hear some skipping or some voicing that go in and out, or your jarbled information, that's just simply those UDP packets did not get from the source to the destination, meaning from the other person on the line to you. Somewhere in between, those packets got lost somewhere out on the internet. And it's fairly common, but for the most part, voice over IP worked very well. And that's going to go ahead and conclude our lecture. So just remember, summing up, we use our SIP, our Session Initiation Protocol, using TCP to set up and tear down our actual session communication where we're making that call. And then for the actual delivering back and forth of the audio and video, we're going to use RTP instead, which is connectionless with UDP. In this section of the course, we're going to talk about computer ports. And no, I'm not talking about those physical ports such as your USB ports, your HDMI ports, and your FireWire ports on your computer. I'm not talking about any of those physical ports. I'm talking about logical ports that are assigned to the operating system by the computer to manage network connections. So let's go ahead and get into it. So why do we need these logical networking ports? Well, computers require networking ports because network applications are abound on operating systems. So for example, you could be on your system, you could have Outlook open, you could have Internet Explorer open, and you could have FTP open. Well, they all want to communicate with your IP address across the network to another device. But you only have one IP address, so how does your computer identify what application that it's communicating with and what protocols it's communicating with? Well, it uses ports to associate packets of information with TCP/IP protocols such as HTTP, POP3, SMTP, and so forth. And so what happens is that we have our networking services. They're assigned with a specific port number. So for example, DNS has a specific port number that it's assigned to. HTTP has a different port number that it's assigned to. SMTP, the same thing, and so on and so on. So that's why we need ports. And if we didn't have ports, then there would be no way for you to be multitasking, because you only have one IP address and you only have one MAC address on your computer. And so we need these ports to differentiate what network protocols and services we're communicating with. And so for example, if you wanted to browse the internet, you would use HTTP TCP port 80. If you wanted to send and receive emails, you would use SMTP TCP port 25 and POP3 TCP port 110. Now, another thing to really concern yourself with is that firewalls, when we're talking about our network security, is that, remember, if we are differentiating what we're doing by port numbers, firewalls filter network traffic by port numbers. So for example, let's say that you didn't want people to browse the internet outside of your network. You could block TCP port 80 on your firewall and nobody could access the internet to do any browsing. Or same thing for emails. If you didn't want your company sending any emails in or out of the network, maybe you are a secure network and you have proprietary information, well, you could block TCP port 25 and TCP port 110 to block SMTP and POP3 on your firewall. So that's one thing, just a quick introduction to firewalls. Now, when we're talking about ports, there's a lot of ports available. For TCP IP, there's a total of over 65,000 ports, and there's some well-defined ports. So let's talk about those right now. So there's approximately 65,000 ports available. However, for these protocols that we talked about in the previous section of the course, all these different TCP IP protocols that we talked about, well, for all of those, there are assigned port numbers, and what we do is we call these well-known port numbers. So we have ports reserved for those, and anything under the number of 1024, it's going to be pre-assigned. Now let's go ahead and let's take a look at these actual port numbers. So here's a table of our well-known ports, and these are the protocols that we talked about. We have a majority of all of them in here. We have our file transfer protocol, we have our secure shell protocol, our telnet, our simple mail transfer protocol, our domain name system protocol, our trivial file transfer protocol, our HTTP protocol, our POP3 protocol, our IMAP4 protocol, and lastly our HTTPS protocol. So you'll notice that for these protocols, there's the protocol name, there's a port number assigned to them, and then the port's going to be TCP or UDP. So a port can either be UDP or it can be TCP. And so if something is port number 20 on TCP, that's going to be different than port number 20 on UDP. And so what I want you to get out of this is you don't have to memorize these because this is just an introductory course. But for those of you that do want to do a certification future on in your career, then you're going to have to memorize these well-known ports. And it's important to understand that, for example, DNS operates on port 53 for UDP, and HTTP operates on port 80 for TCP, and Telnet operates on port 23 for TCP, and so forth. So you're going to get quizzed on those when you take those certification exams. So I know this may be a bit foreign to you, but hopefully this next slide is going to help it make a bit more sense. What we're going to do here is we're going to go over ports in action. So I'm going to go through the process of how this works. So how does this work? Well, let's assume this is you and you're on your laptop and you just have a random IP address assigned to you of 192.168.1.112, and let's say you want to browse the internet. Let's say that you want to browse a certain web server, and so we have this web server over here, and its IP address is 110.90.45.96. Well, we know the source and we know the destination IP address to go back and forth and communicate, but now we have to differentiate and we need to tell this web server that we want to communicate with it by sending requests to specific port numbers. So how does it work? Well, step one, your computer is going to initialize a random high port number on its system to be able to communicate back and forth. So for example, your system is going to initialize this random port number here. So what it does is your operating system is going to assign this port number a random high port number for this session, for this communication, with you having, for example, Internet Explorer open. And you type in that web address. Let's just say it's my website, microgrinder.com, and you want to communicate with this web server. Well, you're going to send specific information. If you need to find out what the IP address is, then you're going to send a request for DNS to convert that domain name into an IP address to get that. So you're going to send a UDP request to port 53 to find out what the IP address is. Now, if you already have that in your table on your system, on your ARP table, then you don't need that. If you already know the IP address, then what you're going to do is, for example, if you want to communicate over just standard HTTP, and my website doesn't have any encryption in it, then you would send a request for TCP port 80 to get information off that website. Maybe you're sending a request just for it to load the home page. So you'll send a request to the IP address of 110.90.45.6 on port 80 TCP to have them send you the home page of that website. And it's going to go ahead and it's going to be listening in on these ports. So the web server is going to be listening, for example, on this instance, on port 80 for that HTTP request, and it's going to receive it from you. It's going to say, okay, well, I know to send that request back to 192.168.1.112 on port 1351 TCP on this system. And so it's going to send it back to you on that system. Now the same thing is going to work for an HTTP request, except it's going to be on port 443 on TCP. So for example, if you went to chase.com to do some banking, you would do a request to port 443 on TCP, and this server is going to be listening on there, and it's going to know that that's associated with HTTPS, and the data is going to be encrypted, and it's going to send encrypted data back to you on your side. And so that's how this works in a nutshell. Remember, you send a request with an associated port number, and they get that request and they send it back to you to your temporarily assigned port number. So that's ports in action. I know this was high level, and this is a bit of information to grasp. So for those of you that want to get a better understanding of how port communication works on the network, I recommend that you go out to Google, and actually I specifically recommend that you go to YouTube and try to find some videos, because there's going to be a lot of detailed information in there, but that's really beyond the scope of this class. I just want you to understand that port numbers are assigned to different protocols so we can do multitasking on networks, because we have different applications open, we have multiple protocols open, and we only have one IP address and one MAC address. So we need to assign these protocols to specific port numbers. So that's going to go ahead and conclude this lecture. If you have any questions, let me know. If not, thanks for watching, and we'll see you at the next lecture. In this section of the course, we're going to be taking a deeper dive look into IP addressing, and specifically we're going to look at IP addressing version 4, so IPv4. Now, before we get into all the details of that, I want to spend a few minutes and I want to talk about IP addresses and MAC addresses and just review what we discussed up to this point in the course. So IP addresses, what are they? Remember, this is that dotted decimal format that we see, the 192.168.100.25, and this is the logical address that's assigned to our system by the network. Now on the flip side, the MAC address, that's the physical address that's burnt into the network interface card, and we can't change it. Now, they operate on different OSI layers, so our IP addresses operate on OSI layer 3, which is our network layer, because they deal with networking addressing, and on the flip side, MAC addresses are on the OSI layer 2, our physical addresses at the data link layer. Now, how do they operate? How do they allow us to communicate? Well, with our IP addressing, this is for network-to-network communication with routers. So we're talking about wide area network communication. And remember, routers communicate with IP addresses, and that's what IP addressing is all about. Now, on the other side, there is communication within a local area network. So with our routers, our hubs and switches within only that local area network. That is where our MAC addresses come into place. And remember, we have our switches that communicate with MAC addresses, and they build that MAC address table. So that's where we use our MAC addresses for our local area network communication on switches and hubs, and never exiting our router to another network. So that's IP addresses and MAC addresses. Now let's go ahead and let's take a look at the anatomy and do a quick review of the anatomy of an IP version 4 address. So here's a picture of an IPv4 address broken down into details. And what we see with the naked eye, we see that dotted decimal format, that 192.168.1.131. However, this converts into binary numbers, so that's where we see these ones and zeros on the screen. The computer interprets it as ones and zeros, and it converts it into this dotted decimal format that we can better understand. You could simply type in the binary math information in here and convert this into a dotted decimal. And it's very simple binary math. However, it's beyond the scope of this course. But if you wanted to look at that and you wanted to convert it on your own, you can go ahead and do some research and do the binary math and look it up. It's very simple. Now, when we look at this, we want to look at the binary numbers here. And what you'll see is that they're broken up into 4 different portions. And these are each octets because there's 8 bits in each one. So there's 1, 2, 3, 4, 5, 6, 7, 8 bits for each octet. 8 bits equals 1 byte, and 1 byte equals 1 octet. So that's why I call this an octet. You can call it 8 bits, 1 byte, or 1 octet. But it's commonly referred to as an octet. Now, if we add all these up together, we have a total of 32 bits. And if you do the math, if you do 2 to the power of 32, that's where we got the total amount of numbers of IP addresses that we can compute and have available with IP version 4, which is up in the billions. So that's our quick review on IP addressing. What we're going to do throughout this section is we're going to be talking in a great level of detail of how version 4 addressing works, and you're going to have a better idea of the anatomy of it and the capabilities and just a really strong overview of IPv4 addressing by the end of this section. So when you look at an IP address, you're not going to notice it, but for those of us that work in the IT world, we understand that an IP address is broken up into 2 parts, and that's something that you need to know if you want to get into networking. So when you look at an IP address, there's other components associated with it, which is outside the scope of this course, but if we look at these other components, if we look at the IP address, its subnet mask, and its default gateway, we can determine what network it is on and what portion of that IP address is associated with the actual computer itself. So when we look at an IP address, it's broken into 2 parts. There is a network portion of it, and there is a host portion of it. So if you look at the bottom of the screen, we have our network address plus our host address. We take both of those, we combine them together, and we have our IP address. Now I'm going to show you how it works in detail in the future lectures, in the future slides, but before we get into that, I just want to do a quick analogy. So the easiest analogy would be your street address. So whatever your street address, let's just assume that mine is 7682 Wilshire Drive. Now if we look at that, you're just going to say this is my home address. But if you think about it more in detail, there's 2 parts to that. There is one that identifies the street that you're on, the Wilshire Drive, but it doesn't identify your actual house number. And then your number, the 7682, that identifies your house. So if we look at our street address, it's actually broken up into 2 parts. One is for the street, and one is for your house. And so if we take that 192.168.1.25, part of it's going to tell us what network we're on, and part of it's going to tell us what actual host we are on that network. And so that's my quick analogy. Now let's take a deeper dive look into it. So here's our familiar looking binary numbers breakout in our 4 octets for our IP version 4 addressing. And what you'll notice here is that I have class A, class B, and class C, and you'll see that I have network and host assigned here. So what does that mean? Well, what it means is that there's different classes of IP addresses in the IP version 4 schema, and different ones assign a certain amount of bits to a network portion of the IP address, and other ones set aside a certain amount of bits to the host portion. And so what you'll notice here is that I have up at the top IP version 4 class full addressing system. Well, what does that mean? Well, what it means is that back in the 1980s and 1990s, whenever they developed IP version 4, the people that developed it, they came up with this system, this classful addressing system, where they determined how they should break out the addresses to assign a certain portion amount to a number of networks that you can create in that class, and also the number of hosts that you connect to each network in that class. And so they came up with a Class A, a Class B, and a Class C type of a system here. And that's what we're going to talk about right now. So what you'll notice is that for our octets, our first octet for Class A, only the first octet is assigned to giving out different IP addresses for different networks. And the remaining 3 octets are assigned to hosts. For Class B, the first 2 are reserved for dishing out and assigning networks, and the last 2 are designed for assigning to hosts. And then for Class C, the first 3 are designed to assign to networks, and the last one is designed for hosts. So what does all that mean? So here's our notation down here to make it look a little bit easier. So for example, 192.168.1.25, if it's Class C, and in fact it is a Class C, the first 3 octets are assigned to the network portion, and the last one is assigned to give out to hosts. So what's that mean? Well, with this setup here, if you do 2 to the 8th power, that equates into 128. So for Class A networks, when they designed it this way, they designed it so they could create a total of 128 Class A networks to assign and register and give out to people. And for each one of those Class A networks, you could have a total of roughly 16.7 million hosts on each network. And so what they would do is they would give out Class A, Class B, and Class C networks to different organizations that needed them. So you'd have to register and request one. So for example, Google could go to the people that are assigning these out, and they could say, I need a network. And they could say, okay, well, in regards to your size, we will give you Class A because we can see that you may need this amount of IP addresses because you're going to have a really large network. So that's Class A. Now, Class B, they assigned 2 different octets, which would be 8 plus 8 bits, so 16 bits. So if you do 2 to the 16th power, that gives you a total of, they could create a total of roughly 16,000 different networks for Class B networks. And for each one, you could have roughly 65,000 computers on each network. So for each one of these, you can have 165,000 computers on a network. And then lastly, Class C. So they assigned the first 3 octets, which would be 24 bits. And if we do 2 to the 24, that will allow them to create roughly 2 million different Class C addresses. And for each Class C network, you can have a total of up to 254 hosts on that network. And so if you look at the way that they assigned this, they created it and they developed it so you could have millions of different small networks. You could have thousands of fairly large networks, and you could only have a handful of just insanely large networks. And so the way that it worked is that they would give these out to different people. And what happened is that this was really inefficient. I mean, if you look at this, if you look at the difference, we go from, you could have a Class A network where they're going to give you over 16 million, almost 17 million addresses. And the next step down was a Class B, where you can only have up to 65,000. So there's a huge discrepancy here. And then the difference from between here and here, 65,000 down to 254. And so you see why this is inefficient, because when they designed it, they didn't design it thinking that we would probably have, in 10 to 15 years, we would have millions of people connected to the internet across the globe, and there would be hundreds of thousands of small, medium, and large networks where there's needs for network spaces and network designs of anywhere in between all of these where there's a huge gap. So, in hindsight, you see that this is a bad design, but when they designed it back in the 80s or the 90s, they didn't know that, and they never could have imagined that, and they probably assumed that this would have been just fine. So this is inefficient, and that's why we've gotten to IPv6, and that's also why we do something called subnetting, where we can actually take these classes, if somebody assigns us a class, and break them up. And so we're going to talk about subnetting in this course, but we're not going to talk much more about IPv6. But that's what the IPv4 classful addressing system is. And just remember in here that you can either have a class A, a class B, or class C addressing system. And these are the amount of hosts that you can have on each one if you're assigned one of these. But it's inefficient, and we use subnetting to help us break it into smaller pieces. So let's go ahead and let's continue taking a deeper dive looking at IP addressing on our next lecture. Okay, so now we know that we have class A, class B, and class C network addresses. And we know that for class A, class B, and class C, they support a different amount of hosts on each one. Now, what if you wanted to find out what type of address that you're on? What if you wanted to see if you're on a class C, class B, or class A network? Well, all you need to do is look at your IP address and look at that first octet, and then look at this table and see where that number falls. And wherever it aligns in here, that's going to tell you what class of a network that you're in. So for example, most of us at home, we are going to be on a 192.1.something type of a network. And for that 192 network, that's going to fall within a class C. Now you're even going to find, let me scroll in my command prompt, and let me just go ahead and do a ping. So let's go ahead and ping Yahoo. What you're going to find is that a majority of the IP addresses that you're going to identify, they're going to be class B and class C networks. Class A networks, you're not going to see that often, but for the most part, they're going to be class B and class C. And so for example, we pinged Yahoo, and they're on a 206 network. So 206.190.36.45. So if we look at 206, that falls within a class C network. Now let's go ahead, let's do something different. Let's go ahead and ping irs.gov. And they are responding with a 166.123.218.220 IP address. And you'll notice that the ping is actually timing out because their name servers and their web servers are probably set up to not respond to ping requests because they're very high traffic and they're probably prone to network attacks. So if we look at the IP address of 166, it's going to be a class B network. So there you go. That's how you find out if you are on a class A, class B, or class C network. So in our IP addressing world, we have what we call public IP addresses and we have private IP addresses. So what's the difference? Well, a private IP address is nothing other than a non-routable IP address. So what's that mean? That means is that if you are assigned a private IP address within your network, if you try to communicate out of your network across a wide area network, once your request goes to your router is going to see that you have a private IP address, and it's not going to go ahead and process that request. It's going to say, you're on a private IP address, I can't process that request, so I'm going to drop your request altogether, and you're not going to be able to communicate outside of my network. And so that's what a private IP address is about. Now, so why do we use IP addresses at our private IP addresses? Well, the main reason is not for security, but it's more so for efficiency. So what does this mean? Well, it means that we can have private IP addresses within our own network, and somebody else can have those same private IP addresses within their network, and 2,000 other companies can have the same private IP addresses within their network, and we can all use the same ones. And so it allows us to reuse IP addresses. So why do we want to do this? Well, remember I told you that IP version 4 was very inefficient, and also that we're running out of IP addresses. So what they did is that they set up a subset of these IP addresses and listed them as non-routable IP addresses. And so for Class A, Class B, and Class C, you'll see a table down at the bottom. All of these specific IP addresses are designated as private non-routable IP addresses. And so what you do is that on your router, you configure one public address. And then within your network, everybody has a private address. And so everybody is then assigned a port number on that router. And the way that they communicate is that everybody just has one public IP address, and they have one port address if they need to communicate. And we do what is called something as network address translation. And so using network address translation, short for NAT, is a way that we can use our IP addresses that are private and make them routable. So once your request goes to the router, it's going to use NAT. It's going to use that public IP address. It's going to assign you a port number, and it knows what port that you're on. And then it allows us to all just use that one public IP address. So for example, if you're an organization of 500 people, you can use a Class C address that everybody else is using. For example, 192.168.1.0 address. That is a specific network. And 10,000 other organizations can use that exact same one. And then we'll just have that one public IP address that's assigned to your entire network. And so it allows us to be a lot more efficient. And if you go ahead and take a look, if you go into your work and if you do an IP config, take a look and see if your IP address is a private IP address. For the most part, a lot of organizations, that's what they use. They use these private IP addresses because it makes it a lot more efficient. And we've run out of public IP addresses, so there's no more to be given out. Now, if you're at home, again, do an IP config. I can almost guarantee if you're at home that you're going to have a private IP address. So that's what private IP address is, and that's why we use them. In this video, we're going to do an introduction to the concept of subnetting. So remember in a previous video, I talked about how IP version 4 addressing was very inefficient and that we're running out of addresses, and that you can either have a Class A, a Class B, or a Class C network. And within the Class A, you have millions of addresses. Within the Class B, you have roughly 65,000. And with the Class C, you have 254 addresses that you can use. And you see that huge discrepancy. Well, one way that we solve this issue as an interim solution is that we use the process of subnetting to break up our larger networks into smaller networks. So that's what subnetting is all about. Now, one thing that you're going to see in the IT networking world is you're commonly going to see subnet referred to as a network. So the word subnet and the word network, they're the exact same thing. So somebody may say that I'm on the 192.168.1 network, or somebody else may say I'm on the 192.168.1 subnet. It's the exact same thing. And so that's where the term subnetting came into play. So how does it work? Well, I'm going to show you a depiction of it further on in this lecture, but just as a quick introduction, the way that it works is if you remember that for all of our IP addresses, the Class A, the Class B, and Class C, a certain amount of bits are reserved for the network portion and a certain amount of bits are reserved for the host portion. So if you wanted to break up your host portions into multiple different networks, you could borrow some of those bits. So we're taking some of those bits to create more networks. And that's pretty much all there is to it. Now, I'm saying that's pretty much all there is to it, but there really is a lot of math behind it, and we're not going to talk about that in this course. So if you do want to learn the actual details behind subnetting, then I recommend doing some research outside of this course, going to YouTube and looking for videos or purchasing a book or something else, because simply I could spend hours teaching you subnetting. That's how detailed it is. And you're going to find classes just solely on subnetting all by itself. So let's talk a bit more about subnetting. So why do we do it? Again, we do it to break up our larger networks into smaller networks to make them more manageable. And if you aren't subnetting, you're really just putting yourself in an unrealistic situation. So for example, if you were a large corporation such as Google and you had 20 campuses across the world and you were assigned one Class B network, well, it's not realistic, and it really is unrealistic for you to try to utilize just one network because you're going to have multiple networks. So what you have to do instead is you have to subnet to take that Class B and break it up into multiple different smaller subnets, and then you're going to assign those to those different locations. And so that's why we subnet. Now let's go ahead and let's take a look. Let's visually look at how this works through an example. So if you look at this, assume that this is the whole pie. Let's assume that we are assigned one big network and we need to break it up into multiple ones. Well, just kind of picture an apple pie where you're cutting it up into pieces, and that's pretty much all subnetting is, where you're cutting up those pieces and you're giving them to everybody else. That's what it is. Now let's go through this example just to better illustrate it. So let's assume that you're a network administrator at a computer science department at CSUSB. So that's California State University, San Bernardino, where I went to grad school. So you're a network administrator there, you're in their computer science department, and you've been tasked with setting up 8 new 30-student computer labs. And you've been assigned one Class C network. You've been assigned the 200.15.178.0 Class C network. And you know that this Class C network alone supports a total of 254 hosts by default. But here's your dilemma. You need to set up 8 different computer labs. So you need to set up 8 different networks, but you've only been assigned one network. And so what do? Well, knowing this, you need to break this one network up into multiple networks. So we know that we have 8 different networks we have to set up, and each needs to support up to 30 different students. So that's going to be approximately 250 different computers we're going to need to support, and we have a total of 254 available. So what do? Well, we need to break this up into 8 smaller networks that support those, and we subnet. That's all that we do. And so subnetting is going to allow us to break this large network up into multiple different smaller networks, aka subnets. And that's where this picture of this pie comes into place. What you'll notice, I know that the font is small, but we have a total of 1, 2, 3, 4, 5, 6, 7, 8 different pieces here. And each one supports a total of 32 addresses. And so we've taken this Class C network and we've broken it up. And now we can go ahead and we can say, okay, this subnet is assigned to classroom lab number A, this subnet is assigned to classroom lab number B, and so forth and so forth and so forth. And if you think about it, if you weren't able to subnet, you would have to go back to whoever is assigning out the different networks, and you'd have to ask for 8 different Class C networks. But again, that's inefficient because each Class C network is going to support 254 hosts. But you don't need that many, so that's why we subnet. And that's just our quick introduction to subnetting. Down here is another example. We have 3 routers, so we have our wide area network down here. We have a local area network here with 2 systems. Again, we have a local area network here, and we have another one here. So for example, if you were the administrator of this network here, this larger multiple networks, and you needed to set it up and assign it different IP addressing schemas, then the most efficient thing to do would to be able to subnet your IP addresses, because if we look at this on these local area networks, there's only 2 devices connected to each one. So it's not efficient to use a Class C network. So that's why we subnet. That's our quick introduction. I know that this is very high level. This is really that 100,000 foot view into subnetting. But the main point that I want you to get out of this is that we can take these inefficient, large, classful, Class A, Class B, and Class C networks, and we can use the process of subnetting to break them up into smaller chunks to create smaller networks that we can hand out that are much more efficient. Again, if you want to find out more about subnetting, please look into it on your own, because like I said, you can purchase entire books, you can purchase entire courses, you can watch hours of videos just to learn all about subnetting. It really is that big of a topic. But anyways, if you do have any questions about this, please let me know. If not, thanks for watching, and we'll see you at the next video. In this section of the course, we're going to talk about the network design process. Now, I know this is an online course and there is no hands-on labs associated with it, so we can't actually design and build out a network. But I want you to be informed of what this process is as an aspiring IT professional or business professional. I want you to understand what the network design process is. So if, for example, you have a network administrator that comes to you and they need to build out a network, I want you to be able to provide valuable input into that process and to understand what's going on throughout that process, so you understand from a business perspective and from an aspiring networking perspective, if you want to get into that field, you understand from a high level what's going on. So let's go ahead and let's talk about what the process is. So in this video, we're just going to talk about the steps, and then I'm going to dedicate specific videos to each steps. So the first step in this process is that we need to identify the uses of the network, because if we don't know the uses, then we don't know the specs that we're going to need. After we identify the uses of the network, then we're going to list the tasks associated with each of those systems on the network, so we understand what each computer does on the network, what's its role and what's not its role. And then we need to determine what type of network do we need. Are we going to be doing a centralized type of design, or are we okay with a peer-to-peer network design? And then once we have all that information, and remember, you should already have a lot of this information, because if you went through the planning process, a lot of that filters into the design process. So all this should be filtering in from the planning, and if we need to get additional information during the design process, we can do that as well. But once we get past step 3, then what we're going to do is we're going to start selecting the equipment. So we're talking about the servers, the desktops, the printers, the network devices, the cabling, everything that we need to build out this network. Once we select what equipment we're going to use, we're going to draw a network design. So we're going to put a network design down on a piece of paper or on a system online where we're drawing it out. And then we're going to write the specific specifications of the network. So we're not only going to draw it out, but we're going to specify exactly what it should do, what it should not do. And then once we have all that in place, once we get the approval, go ahead and we'll build it. So that's the network design process. Let's go ahead and let's start taking a look at step 1 in the next video. Okay, so now let's take a bit of a deeper dive look at step 1. Remember, step 1 is that we need to identify the uses of the network, and if we did proper planning, we should already have a majority of this information. And if for some reason we didn't do proper planning, then this is a time where we need to go back and we need to find that information. So this does align with our planning phase, and we need to determine why the organization needs a network. So if we're a company, we need to determine what type of a need is this going to fulfill. So what type of an issue is there where we need this network, or if we're going to provide process improvement, if we're going to support the business, we need to justify why we need this network. And like I said, during the planning process, we can find out all this information via interviews with key stakeholders. So for example, we need to interview key stakeholders to find out what the business does. What's the business's core strategy and processes? So what do they do? That's the simple question. And if you can answer that, then you're going to have a good idea of what you're going to need the network to do. And then also ask yourself, how is the network going to change or improve business operations? So how can this network help the business and help our core processes? So think about those two things when you're going through your interviews. And when we're talking about key stakeholders, we're talking about the business's owners, the key executives, the managers, and even the day-to-day operations. So why the day-to-day operations? Well, if you think about it, those are the people that are going to be closest to the work. So they have the most intimate knowledge of what actually is going on a day-to-day basis, and they're going to know from a very fine level of detail what the network's going to be able to do. The owners and the executives and the managers, they're going to have, the 100-foot view, the 10,000-foot view, the 100,000-foot view. They're going to have that strategic idea of what they needed to do. But once you get down to the operations on a day-to-day level, they're going to tell you the detailed information that you need to know. So you need to interview everybody within the organization, not just the owner, not just the executives, not just the managers, and not just the operational staff. You need to interview everybody. And the more that you find out about the business during the planning phase, the better your design is going to be for your initial design. And when you submit that proposal with your initial design, the more likelihood you're going to get buy-in, support, and approval, rather than being told to go back and find out additional information or to redesign it. So that's step 1. In the next video, we're going to take a look at step 2. Okay, so step 2 is listing which tasks are executed by which computers on the network. And we can actually expand this out a bit. We can talk about not only the computers, but also the network devices themselves. So when we're talking about the computers and the network devices, we're not just talking about the hosts. We're talking about the host machines, we're talking about the servers, and we're talking about specialized networking devices such as firewalls as well. So we need to know what type of applications and what type of tasks have to be performed on each computer on the network. So for example, if you are a manufacturing company, maybe you have some manufacturing software that you need to run for example, your inventory management, or something that's going to actually run your hardware. So that's an example of an application that you're going to need to use. Or maybe you're an accounting firm and you have an accounting software application that's going to be used on a server, and also all the clients are going to have client software installed as well. So we need to think about all the different applications, and it can be as simple as identifying something as simple as Microsoft Office Suite, Internet Explorer, etc. So you need to think about all the different applications, and the more detailed the list, the better. So why the more detailed the list? I'm not talking about just all the most important applications. I'm talking about every single application. And this is important because we need to know how powerful each computer needs to be. So we need to know how robust each system needs to be, because they need to be able to support the needs of the business, not only for now, but potentially for the future growth as well. So we're talking about the capabilities like the power of the CPU, the amount of memory that we need to have installed, how much hard drive space we need, and maybe even if our users need 1 or 2 monitors, and how big those monitors need to be. And this goes for our servers and our client computers. So for example, if you're thinking about it, and a good example for you as an exercise is just to write out all the details of potential applications would be, think of a data entry user versus a video editing graphic designer. So what type of system would they need in terms of how powerful would it be, and what types of applications would they have to run? So that's just a good example to really think of these different processes. So that's step 2. Let's go ahead and take a look at step 3 in the next video. In step 3, we're going to determine what type of a network we're going to need. And when I'm talking about this, I'm talking about, are we going to be okay with a peer-to-peer network design, or do we need a centralized client-server architecture in place? And a lot of this is going to come down to the size of the network, your resource constraints, and also your security concerns. So a lot of this comes from your initial planning processes and understanding the overall needs of the organization and the size. Now, for a lot of smaller businesses, you can get away with a peer-to-peer design. But for a larger organization, you're going to want to go with a client-server architecture. Now, regardless if you're going to do a peer-to-peer or client-server, there's going to be different services that may have to be designed to be on some sort of a server for you to provide your users. And so you also need to think about what type of server services do you need to provide the network. And I listed a whole bunch of the common ones here. So for example, are you going to need a file server? Well, if you have a client-server design, you most definitely are going to need to. Are you going to need a print server, or are you just going to have network printers out there or local printers at each cubicle or each office? Are you going to need an email server, or are you going to use something like Gmail or Yahoo Mail or a web-based mail that's managed by your web host provider? Are you going to need specialized application servers? For example, maybe you're a dental office and you have specialized software to run your office and to manage all your patient records. Or can it be cloud-based and stored in the cloud and be web-based? Are you going to need a localized web server, or are you going to use a web hosting company that's going to manage everything for you? Are you going to need an authentication server where everybody has to authenticate to that to log into the network? Or are everybody just going to be on a peer-to-peer where they just do the local login? And what about data backups? Are you going to be doing data backups into the cloud out on the internet via some sort of online service? Or are you going to have a localized backup server on your network, and maybe even a local server itself that's going to be replicating all your data, so in case your primary server goes down, you have a secondary server in place? So these are all examples of different types of servers and services you need to think of. And if you're thinking about a physical server, the question is, well, if we need one physical server for one of these, well, the question is how, meaning how powerful does it need to be? Can we do virtualized? And I know I didn't talk about virtualization in this course, but virtualization is where you can have one physical computer and you can virtualize multiple different virtual machines on it to emulate multiple different servers on one physical server. So the question is, well, can we do virtualization? And then for the server itself, well, are we going to do a Windows server, or are we going to do a Mac server? And if we're going to do a Windows server, what can we add onto one physical server? Because if you have a powerful server for a Windows machine, if you're running the Windows Server platform, you can actually have one physical server have the role of multiple different services. So for example, you can have one physical server be your authentication server, your file server, your backup server, and your email server. Now, I wouldn't recommend that, but it is plausible and it is possible. So these are just some of the things to think about. Number 3, is it centralized or not? And if it is centralized or not, what type of server services and physical servers and applications do we need to support? So in the next video, we're going to take a look at step 4. So step 4 is all about selecting the proper equipment. So in this step, we're going to determine what type of networking equipment is right for us, that's custom tailored for our specific network design. And so when we're looking at this really takes into consideration everything that we've done so far. So we're looking at our planning process and our design process all the way up to step 4. So we've identified the uses of the network, we've identified what sort of tasks are done on each system on the network, and we know what sort of architecture we're going to do, whether if it's peer-to-peer or it's client-server. Now, when we are talking about our server equipment and selecting it, we need to consider some key constraints. So for example, our monetary constraints and also our resource constraints in regards to if we have the dedicated IT personnel that we need on staff to design out a client server or peer-to-peer network. So those are some constraints to consider, and also some additional potential needs that you're going to have. Now, some other considerations are going to be your reliability requirements. So how reliable does your network need to be, and what's the uptime availability requirements that you need? Another one are your security requirements. How secure does your network need to be? So how many network security devices do we need to have in place, and do we need to have an authentication server in place, or are we fine with everybody being on a peer-to-peer network? It's really up to you. It's based upon really not only what you want to do, but also based upon the laws and local regulations. So for example, a dental office, they'll have to abide by HIPAA laws as well. So they can't just say, well, no, this is fine by us. You have to follow the different state and federal regulations. And then also scalability requirements. So when we're talking about scalability requirements, we're talking about being able to, 1, scale up the network, and number 2, being able to grow with the business. So the network needs to be able to scale up as the business grows and per the business needs. So not only the current needs of the business, but also the future needs of the business. So let's go ahead and let's walk through some examples of looking at different types of items that you can purchase. So for example, when you're looking at your systems, you have to take a look at the different ones that are out there. And everything I'm doing right now, these are the snapshots that I did in the past of Dell and different options out there. Now these Vostro desktops, these are their business desktop systems. And so these are just a simple example of, there we have a 460 model, 260 model, and 260S. You're gonna have to take a look at the prices. You're gonna have to take a look at the specs to see what best fits your needs, because not every single desktop machine is created equal. So when you're looking at desktops, number 1, look at the price, and number 2, look at the specific design and see if that's going to meet the requirements and it's going to be robust enough or not for you and for your custom design and your business needs. So the next thing you need to look at is you need to consider your servers. So if we're going to be doing a client server architecture and we're not going to do a peer-to-peer architecture, well, we need to take a look at the different types of servers that are out there. And the prices can range from the hundreds up to the thousands. And so if you're doing a tower server design, for example, over here I have my first server solutions. These are going to be affordable options as well as the tower servers, but as we get to our rack servers all the way to our blade and power edge servers, then we're going to be spending thousands and thousands of dollars. So again, you need to look at your needs and your requirements and your constraints and determine what fits within your design budgetary needs and also your technical and business needs as well. Server selection is very customized, and it's going to be just like when you're looking at your desktops as well, but it's going to be a lot more detailed because there's a lot more configuration that goes into it. Again, here's some more servers. So here's some more PowerEdge servers, tower servers. This again just gives you an idea of the different prices. So for these tower servers, the cheapest one is $568, and for a tower server here, this starts at $1,500. Now, if you're looking at the blade servers and the rack mount servers, the prices are going to even be higher. And these are older models. I took the snapshot a while ago. So, prices may have gone down, but again, you're going to see a huge difference in power edge servers to their actual rack mount or their blade servers as well. So we need to think about our backup needs. So I put some pretty example. So we need to also think about our backup needs, and if we're going to be doing an online solution that's cloud-based, or if we're going to be doing something that's in-house. And the question is, can we do tape backups? Or are we going to do a file backup that's going to be on a disk, or are we going to replicate our data from one server to the other? So if you are going to be doing tape backups, you need to take a look at that. And I always recommend that when people are looking at backup solutions, that they look at the cost of a tape backup solution to a file backup solution. Now, one of the benefits of having a tape is that once you do your tape backup, you can take your tape and you can take it off-site. And that's one of the best practices for doing a backup, is that you always want to store your backups in multiple different versions of them off-site, because not only can your server fail, but you can have theft, or you could have a natural disaster where you lose everything. And if your data backups are stored in the same place where your hardware is stored, then you're going to lose everything. So that's one of the benefits of doing tape versus if you're replicating data from a server to another that's on the same actual physical location. You can't do that. Or if you have a hard drive hooked up, if it's not USB or if it's not hot swappable, again, you're going to run into that same situation where you're not going to be able to take that and store it offsite. Now, another thing a lot of people don't think about, and this really is part of your network design, is determining what type of interrupted battery backups you need in place. And this is not only for your desktop systems, but more so for your network devices and for your servers. Because I can guarantee you're going to have power outages. They may be short outages, they may be long outages, but the last thing that you want is for everything just to shut off when the power goes off, when the network goes down, especially your servers, because you can have corrupted data, you can have corrupted systems. You want them to shut down peacefully and properly. You don't want them to shut down when the power goes off. And so we need to look at what sort of battery backup solutions we have in place for not only our desktops, but for our vital servers and our vital networking equipment that we need to keep the networking running, to shut it down peacefully if we have a power outage. Now the fun part is you get to look at all your networking equipment. And I'm not going to show you slides on each specific one because we could spend another 15 minutes just talking about the different types. But when we're talking about our networking equipment, we need to determine what sort of a router do we need. Can we get away with a wired router, or are we going to do something like a SOHO device that's a wireless router? And same thing for switches. We need to look at our needs for our switches. So there's different speed requirements that you may need as a business. So you need to look at what type of switch you need, and you need to look at the amount of ports that it supports as well. Same thing goes for your cabling. Are you going to be doing Cat 5e, Cat 6, etc.? You need to determine what type of cabling you need, and your networking equipment needs to support that type of cabling. Also, we need to look at some other things. For example, are we going to be doing voice over IP within our network? If so, then we can look at those requirements as well. And then also if we need to do streaming media. So maybe we're a media company and we need to have a streaming media device. That's something we can look at as well. And then also on the last thing up there, we have our enterprise class networking equipment. So everything else here on the left hand side with these routers, these really aren't enterprise level. These are really small business level type of equipment here on the left hand side. But when you go into an enterprise networking type of equipment, your costs are going to go up drastically, but you're going to have much more reliability and it's going to be much more robust. So you need to think in terms of the size of your business, not only now, but for the future as well. And then lastly, we need to think about physical security. So a lot of people tend to not think about physical security as part of the design process, but if you're not securing your networking equipment, somebody could just walk out the door with it. They could go into your network closet if it's not properly locked, and they could just take one of your switches or whatever and unplug them and walk out with them. They could go into one of your offices and take one of your desktops if they're not locked. Same thing, they could do it with your screens as well. So if you're not locking down your LCD screens, you come in the office, you can't get on the network. So these are all part of the network. And we need to think about physical security. So we need to think about locking down all of our systems with our cable locks, with locking the doors and everything else. So that's it. We covered a lot of different things. We covered talking about our physical security. We talked about our networking equipment. We talked about our battery backups that we need, so those UPSs. We talked about our data backup solutions if we need to do tapes, or if we can get away with doing some sort of other backup solution. We talked about server selection, and we talked about desktop selection. So there's a lot that we talked about. If you have any questions, let me know. Thanks for watching, and in the next video, we're going to go ahead and we're going to take a look at step 5. So step 5 is all about drawing the network. And now I don't expect you to be doing this, but for you as a business professional or for you as an aspiring IT professional, then you should have some input into this. But this is really where your network administrators and your network managers are going to sit down with your IT managers, and they're going to design this network. But everything that you did so far, that you assisted them with, where you provided input into, that's going to lead us up to step 5. And so by the time that we reach this step, we have a really strong idea of everything that we need. Because if we don't, we really can't build out our design. We can't draw anything if we don't know what we need. So up to this point, you know the purpose of the network. You know what the network's going to be used to do. You know the number of users and the number of computers that you're going to need to support on the system. You know if you're going to be using a centralized architecture or if you're going to do peer-to-peer. And you should have an idea of the network topologies that you're going to need to use as well. And so in this step, these people, these professionals, your network administrators, your network managers, and your high level, your really in-depth knowledge IT professionals are going to sit down and they're going to draw the physical and logical design of this network. So what they're going to do is they're going to draw a physical layout of where the equipment goes on the blueprint. So you're going to have a blueprint of all the offices and cubicles and everything else. And they're going to lay out where everything's going to go on that physical layout design. They're going to put the server equipment in the server room. They're going to locate the networking equipment in the networking closets. They're going to locate where all the printers go throughout the office. They're going to place where all the computers go in the cubicles and the offices, so forth. And so that's going to be the physical design. That's going to show us physically where everything goes. And then on top of that, we're going to have them do the logical design. And so that's where they're going to assign the IP addresses throughout this network. And it may be multiple networks, so they may have multiple different IP address schemas, and that's where they come into play as the experts. And at this point in time, they're going to determine if they need to subnet or not. So if they were given a Class C, a Class B, or a Class A network, they're going to determine the most efficient way to utilize those IP addresses and to determine what to use and to determine if they're going to subnet or not. So that's step 5. Now, like I said, this is not your job. This is the network managers and the IT managers and the network administrators and IT administrators. That's their job, because do this than us as business professionals and us as non-techies and for us as beginning IT people. But we are going to provide input along the way. So now let's go ahead and let's take a look at step 6 in the next video. So step 6 is all about writing the network design specifications. So after your IT professionals and your network administrators and network managers, after they have their physical and logical design in place, what they need to do is they need to write up a network specifications documentation. And there's specific reasons why we need to do this. The first one is that we need to clearly define the scope of the network design itself. So when you have people come in and build out the network, it prevents any sort of scope creep. So with the specifications, we know exactly what the network needs to do and what it shouldn't do, and we need to use that to keep us within our specific constraints that we have. Now, the second thing is that this always provides us as a reference documentation for our network support people and our network administrators in the future. So once the network goes live, we need to support it, and having our specifications in place is going to allow us to more efficiently support the network than if we had no specifications to follow at all. So what should our specifications documentation include? Well, number one, it should state why we are building the network. So we need to talk about the technical needs and the business needs and how we're going to help or support the business. So really, this is justification for why we're building this. Number two, we need to talk about and include in here what the network is going to be used for. So what's its purpose? Number three, we need to talk about how many people and how many computers the network is going to support, not only now, but what it's going to be able to scale up to as well in the future. And then after that, we're going to talk about the architecture, whether it's a peer-to-peer or client-server architecture. So our people that are supporting it understand, and the people that are designing it understand as well. And then after that, we're going to talk about our response time and throughput requirements. So this is all about the bandwidth requirements and how robust the network needs to be. And so we need to make sure we put that in there, because we need to understand that once we start building out the network and once it goes live, we need to have a baseline for what it should be doing and what type of performance measures should be in place to ensure that it's operating efficiently. If we don't have response time and throughput requirements, then we don't know at what level of performance it should be operating at. After that, we need to talk about our security requirements. So we're talking about both our physical security requirements, such as locking the server room, locking the networking closet, locking down the servers and desktops with our cable locks and so forth. And then we're also talking about our logical security requirements, such as having firewalls in place on the border edges of each network, or having actual firewall applications on the desktops and servers as well. Then after that, we're going to talk about and make sure we need to put in the reliability requirements. So what I mean by reliability requirements, well, we're talking about the availability requirements of the network. We need to tell the people that are building it, and we need to have this in our specifications, the availability requirements of the network. So we need to know if the network needs to be up 100% of the time, 24/7, or if it only needs to be up Monday through Friday, 8 to 5 p.m. So we need to understand that, because understanding reliability requirements and availability requirements is really going to mold the way that the network is designed. And then we need to talk about scalability requirements. So we need to think about how much the network is going to scale up in the future and how much it's going to be able to support in the future. And then lastly, we need to talk about our actual specifications for all the different hardware and software that we're going to put in. And we also need to justify them. And we need to justify them because there's a cost associated with each one. And then once you have this in place, and once you have your design in place, your physical design, your logical design, and your specifications in place, you need to ensure that your organization buys into this design specification. So whoever is the sponsor for this design and for this network build out, you need to go ahead and get their approval before you move forward. So that's step 6. And then after step 6, really the last step is to build it. So once you've gone through steps 1 all the way through step 5, you have the design in place. You then go to step 6, you document everything with your specifications, you get the approval, and then you build it out. Now, again, this is not something that you should be doing as a business professional or an aspiring IT professional. Within the organization, you may be asked to provide input, but again, when we're talking about designing the specifications and doing a majority of this work, this is going to be the work of your IT administrators, your network administrators, and your IT and network managers. And so everything within this actual design phase is really going to be their realm. But we need to understand, and we need to be educated in this so we can provide input and we can understand what's going on, especially if we're a manager in the IT department, or if we have input into this and we're a key stakeholder. So we want to be able to provide valuable information. But again, that's really it. That's processes from step 1 all the way through step 7. If you have any questions about this, please let me know. If not, thanks for watching, and we'll see you at the next video. In this section of the class, we're going to take everything that we learned throughout this course and we're going to pull it all together by going over a couple different case studies. And so these are case studies that I developed for my classes when I taught this at the university. And they're 2 fictitious case studies. One is called the H&M Law Firm, and the other is the San Bernardo Dentistry. And what it is, it's new businesses where they're requiring you to set up and design a new network for them. And so it has a list of requirements, and we're going to go through those requirements, and we're going to go through some of the actual submissions from my students. So when I taught this at the university level, I had them work in groups, and throughout the entire semester, they combined this together into a final project. And so what I'll be doing is I'll be pulling together some of the better submissions, the ones that I thought were really good, and then we'll be going through those together in this course to give you an idea of the level of work that's been required in this and to show you how you can properly plan and design a network based upon a case study scenario. So let's go ahead and let's take a look at them in the next video. The first case study that we want to take a look at is the H&M Boutique Law Firm Scenario Case Study. And what this is, both of these case studies, these are fictitious case studies that I developed, and they are new businesses that are sending out requests for proposals for IT consulting firms to plan, design, and set up new networks for their new businesses. So with the H&M Boutique Law Firm and with the other case study, you'll notice that in the resources tab, I do have downloadable resources. So the actual case study, which you see here, you can download it as both a PDF and a Word document. Now, I did it as both a PDF and a Word document because you can take the Word document and you can go ahead and edit that and put notes directly into it. You can't do that with a PDF. So I decided to make both of them for you so you could download whichever one you want. And also at the bottom of each case study embedded, you'll see the actual office layout plan where you would do your network design. I also have that as a separate downloadable file as well, so you can download that as well. Now let's go ahead and let's get into the actual scenario. And let me go ahead and let me zoom in a bit on this so it's easier to read. So with this scenario, I'm not going to go through it in a very fine level of detail. What I want you to do is take time to read through this, and once you've read through this, we'll go through, and when the next video, we'll be doing an analysis of this, and we'll be going through some actual student submissions when I taught this course as a group project at the university level to undergraduate students. And so I'm going to pull some of the better final proposals, and we're going to go through those to give you an idea of the level of work that they went through, and also the type of designs that they came up for their network design, to give you an idea of what you should be thinking about when you're doing these case studies yourself if you want to do it on your own. So everything we talked about in this class, we talked about planning and designing the network and putting it together. That's what we're going to do in here, and you're going to get an idea of what some actual groups of students did as undergraduate students that were business students that were brand new to computer networking when they started this course. And at the end of the semester, they were able to put together a really fine and detailed and quality business proposal and network design for a fictitious business. So let's go ahead and let's get started. So in this scenario, in a nutshell, we have two young aspiring lawyers, and they were working for one of the big law firms in Los Angeles, and they decided they wanted to go out and start their own boutique law firm to cater to upcoming small businesses in downtown Los Angeles. So they went out and they rented a small office space, and now they're sending out requests for proposals to different IT consulting firms to design a network for them. And what they did in this scenario is they came up with a list of business requirements that they need. And we'll go through these quickly, but again, I do want you to go through these on your own as well. So print this out and go through it, and then when we do the analysis, you can take notes. So the first business requirement is that they want wireless access for their business clients in the waiting room, but they don't want their business clients to be able to access their internal business network, meaning their servers, their own files, and their desktops, and their printers, and so forth. Both of the owners of the business, they're going to require their own desktop computer that's networked in their offices. They plan to hire both a receptionist and a paralegal, and they're both going to need computers. So the receptionist is going to be at a receptionist desk, so they're going to go ahead and they're going to need a desktop. Now, for the paralegal, they don't have dedicated office space for the paralegal, so the paralegal is going to be roaming throughout the office in the conference room / law library in the receptionist area, and also be working in their offices when the offices are open as well. So they're going to need that person to have a laptop, and they're going to need to have an internal wireless network for that person as well, in addition to the wireless network for their clients. Now, they also are stating that they're going to handle a lot of sensitive and critical information because they are lawyers. So they want to make sure that they have a secure centralized file server to access this information, and they want to make sure that it's secure on there. So they want to make sure that only the firm employees have access to get into that, and also to log in to any of the firm computers. So they want strict login and access control policies. So that's telling us that they need a file server, and they also need an authentication server. Now, they're also stating that they're going to be doing research, and they'll be on the internet on a regular basis, so they want to make sure that they have fast and reliable but affordable internet connection. And they're also stating that they're going to be printing a lot of material. So they're requesting that they have a centralized high-speed laser printer in the receptionist area that everybody can print to, and that they have their own personal printers in their offices as well. Now, they are stating that the information within their business is a very critical key asset to the company. So they want to make sure that their data is backed up on a regular basis. And they want to make sure that if any device fails on the network, whether it's a network device or the server, that they're able to bring the network back up fairly quickly. So they don't want work stoppages. And if there are any work stoppages, they want them to be very minimal. So they're stating that they need an adequate level of redundancy and fault tolerance built within their network design. And because they are a small firm and they are strapped for cash, they have limited financial resources. So they're stating to keep the overall cost of this design and plan and build out of their network to $10,000 or less. So that's the H&M Boutique Law Firm. Like I said, print this out and go through it yourself. And what we'll be doing in the next video, and maybe the next 2 or 3 videos, depending upon the level of analysis, is we are going to go through and analyze this and go through some submissions that my groups of students did when I taught this course at the university level. In this video, we're going to go over the business proposal submitted by one of the groups of students in my class. This was the A+ Consulting Firm. That's what they named themselves. I did take their names out of here to sanitize the information, but we're going to go ahead and go over their submission. So it is uploaded to the course on Udemy, but I'm going to go ahead and pull up the PDF so it's easier to read for this video. So let me go ahead and scroll the PDF over, and let's go ahead and make this a bit easier to read. And so what you'll notice is that when you're going through this process, remember that business requirements are going to lead to technical requirements, and that's the process that they went about. You go through the planning process, you find out the business requirements, you then determine the technical requirements, and then you design the network. And so in their final proposal, let me go ahead and make this a bit larger. They go over the business requirements, they go over the overall network design plan, they have a physical design, they have a logical design where they set up the logical topology and the IP addressing, and then they do a cost breakdown to show that the proposal is within the financial resource constraints. And so, I'm not going to go over everything in here. I just really want to focus on the actual physical design for the scope of this course, but I do want to scroll through this. So you'll notice here is that they talk about the business requirements, and they have an overall network design plan in place. And then they go ahead and they talk about the physical design and all the aspects of it. They talk about how they're going to be storing the data, how they're going to be backing up the data. They talk about their cabling, what type of cabling they're going to use, and how that meets the requirements of the business. And then they have the physical design. And so this is what we really want to focus on for this class. And let me zoom in a bit more so you can see this a bit better. And so you'll notice that they have Cat 6, Cat 6E, and they have their AC power listed in here as well. And so based upon the design that they wanted for the scenario for the business, you'll notice here that they satisfy that design. So they have the internet connection here going into a router, and then they have a firewall to protect the local area network of the business. And what you'll notice off the firewall here is that they have multiple different ports. And so they have the firewall going off to the public Wi-Fi access here for the reception area down here. And so that's for the clients to access that information. And because it's going to the firewall is going to protect the rest of the network. And so they're only going to have access based upon what we configure in the firewall to protect the network. Again, over here they have their file server on a different port on the firewall. So again, we can set up different rules, so only certain people and certain types of applications and network traffic have access to that file server. And then again, another port going off the firewall into the internal network for the business. And what you'll notice also within here is that they have a backup power supply going all to all the different primary devices to ensure that if the power goes out, then the network is still up and running. And then off this firewall, they have a mesh design of the network. So remember that Ron and Jeff stated that they needed to ensure that their network had adequate fault tolerance and redundancy. Well, they made sure that they put a mesh in place right here on the core network. So they have 2 switches instead of 1. And you'll notice one switch goes over to here, over to the reception area where we have their receptionist computer and the laptop, sorry, not the laptop, but the networked printer. And then over here, you'll notice that it's mesh, so if for some reason one of these ports goes down, it can still access across. And then over here, we have the private Wi-Fi set up for our paralegal. So wherever the paralegal is in within the office, they have access to Wi-Fi in the network. And then you'll notice that we have redundant lines over here going to another switch on the mesh network, going to Ronald and Jeff's office. And so we have the switch here. We have the redundancy built in, and they both have their own printers, they both have their own computers, and they both have their own backup supplies. And so you'll notice, based upon how they design this, they set up an adequate level of fault tolerance and redundancy in place with a mesh network. And you'll also notice that they went above and beyond the design. They also put a closed caption TV type of a camera setup for security cameras, and that includes a DVR, so they're always monitoring everything going on in the office, and if anybody breaks in, then they have that information to give it to the police if for some reason data and information is stolen. And so that's their physical design. Now they also talk about the logical design, and again, we didn't talk about how to subnet and do our IP addressing in detail, so I don't expect you to understand this, but I do want to go over it. So they talk about their internet connection in regards to the logical design. They're stating they're using a T1 line to make sure they have adequate bandwidth. They do have a mesh design for redundancy and fault tolerance, which I talked about. They have their access points in place so different people can access different areas on the network. So remember, we have our public Wi-Fi and we have our private Wi-Fi on the network. And they talk about their computers and printers on the network, their file server, their backup server to back up their data. And if we keep going down, this is the actual logical design here where we have our IP addressing in place. And like I said, we didn't go over the IP addressing in this course to the point where I expect you to know how to go ahead and subnet and assign IP addresses, but we will go ahead and quickly take a look at this because based upon this logical design, we can see how this is set up again in a secure manner. So again, we have a router here, we have our firewall, and our internet is over here, our T1 line coming in. We have our firewall here, and on one port to the firewall, we have our file server, where they're also backing up their data. Again, we have another one where we have our public access point for our clients to access their network and to access the internet. But when the clients access this, when it goes to the firewall, they can only access out to the internet. They don't have access to the file server, or they don't have access to the internal network over here. And then off of the firewall, you notice that they have a mesh set up. So you'll notice they have a full mesh between these switches here. We have 1, 2, 3 switches on this firewall. We have a full mesh, almost a full mesh, a partial mesh, because we don't have direct from here to here. And so, for example, if one of the cables goes down, we can still get across and so forth. And if one of the switches go down, we can easily reroute by plugging into another switch. We have the receptionist computer, we have the network printer for the office down here, and over here we have another switch that connects the two different owners, Jeff and Ronald's computers, and their own personal printers. And then lastly, the internal wireless access point for the internal network for their paralegal as well. And if Ronald and Jeff want to get a laptop as well, they can access the network via Wi-Fi as well. And then lastly, they do a cost breakdown of all the equipment, and it gives a total summation of the cost, and then a conclusion. So I did go over this quickly. We went over this in about 7 minutes. My recommendation is that if you want to really look into this and look into the fine details, I do recommend just, either printing this off or downloading it and just browsing through it leisurely on your own, because it's going to give you more insight into the overall process. I just didn't want to spend 30 minutes going over every single aspect of their 11-page proposal. I just wanted to give you a quick highlight overview and really focus on the physical design and kind of talk about the logical design to see how we took that initial case study, and then we took that case study, and as students of this course, we can take that and put it into a physical design. So we take those business requirements, we turn them into technical requirements in our planning process, in our design process, and then we design our network. So if you have any questions about this case study, let me know. Now, you might find some flaws in the design, and that's perfectly fine because, again, these were undergraduate business students. This was their first networking course, like many of you here on Udemy. So I don't expect you to have a 100% perfect design network. You are going to have flaws here and there. but that's okay. It's a learning process, and I just want to show you that what you can come up with on your own once you complete a course like this. So again, if you have any questions, let me know. If not, thanks for watching, and we'll see you at the next video. Our second case study is our San Bernardino Dentistry DSS case study. And in this case study, we have a dentist, Chris Reynolds, and he decides that he wants to open up his own dentistry office. So he's leased out a small office. And again, he's sending out a request for a proposal for you as a consulting firm to go ahead and plan, design, and build out his network. So let's go ahead and let's look through the business requirements for this case study. So business requirement number 1, he needs a personal desktop computer in his office to perform administrative duties. He is also going to have an office manager that's going to need their own personal desktop computer in her office to perform her administrative, accounting, and payroll duties. He's going to also have a receptionist that will need a personal desktop computer in the receptionist area in order to manage patient information, including patient appointments and billing information. Now, he intends to perform digital x-rays using specialized software to create digital images of x-rays on the computer. So he's not going to be doing the old school types of x-rays. Everything's going to be digitized in the new era. And so he's going to need an x-ray computer in the x-ray room. And he's also going to need digital x-ray software that he intends to use. And he's going to have a dedicated application server that he thinks he's going to need, and as well as client software as well on each computer. So he may have multiple different rooms that are going to require this actual application and client softwares on all the examination rooms, as well as a dedicated server. He is suspecting that these digital x-rays are going to take up a decent amount of bandwidth on the network as well. So he thinks that his network is going to require a decent amount of bandwidth and throughput on a regular basis rather than just a minimal amount. He's stating that each patient room is going to require a computer because, again, he's going to have this x-ray software on there. He's going to have his patient software on there as well. And so he wants to be able to go over treatment plans with the patients in each patient room. So if he has multiple different patient rooms, he wants to be able to do this in each single one. And he's going to utilize the latest dentistry patient management software as well. Now, this is in the United States, and in the United States, we have what is called the HIPAA Act, which requires that he keeps his patient information secure and private on his computer network. So he's going to be required to securely store all this patient personally identifiable information on his network, on his client machines that are on all the different patient rooms, and on his servers as well. So he would prefer that all patient information records are digitally stored rather than physical patient folders as well. And so he's going to want you to set up so he can utilize a secure central file server and authentication server that's going to make sure that all this patient information is kept securely on his network. Now, he does not anticipate that he's going to be doing that much printing, and so he thinks a single network printer in the receptionist area is going to suffice for his entire office. And because he's going to be relying on the network to run his business, he needs to ensure that it's going to be designed to minimize network outages and network devices and server failures. And so for him, downtime in his office is going to equate to a lot of lost profits, because if he can't work, then he can't go ahead and he can't be a dentist and he can't bill patients. Therefore, he wants to make sure that his network design has an adequate level of availability and redundancy and fault tolerance. Now, again, this is our startup firm. This is his first dentist office, and he has limited cash to dedicate to the design and build out of the network. And so he's asking for the overall cost to stay below $15,000. And this is a screenshot of his office. And so you can go ahead and go through here on your own time. Again, my recommendation is to print this out and to read through it as well before you jump ahead and go to the next videos, because I want you to have a good understanding of what his business and technical requirements are before we start going through the actual analysis walkthrough. And just like with the previous case study, again, I'm going to pull some of the submissions from my class when I taught this at university level. I'm going to pull some of the better submissions, and we're going to go through those as well. So again, you can see what my business students that had never had any previous experience designing and building out computer networks, what they were able to do at the end of the course. So let's go ahead and let's jump into that. But again, before you do, go ahead and print this out and read through it before you jump to the next video, so you have a good understanding of what we're talking about. In this video, we're going to go over our case study analysis for the San Bernardo Dentistry DDS office, and this again is going to be a case analysis final proposal submitted by one of the groups of my students in my undergraduate course, and it is uploaded here, but I'm going to go ahead, just like I did in the previous one, I'm going to go ahead and pull the PDF in so it's easier for us to watch in this video. So let's go ahead and let's see what they came up with. So here's their final proposal they submitted at the end of the term, and you'll notice that this is very similar to the H&M submission, but it's going to be a bit different. Different scenario, different group, different class. So you're going to see differences in how they went about doing this final proposal. So let me go ahead and zoom in a bit so we can see what they went. So they have initial letter to the buyer, they have a mission statement, they have their network design, their network legend, their network addressing schema, and their network addressing legend, their equipment that they choose to put in this proposal, a cost breakdown, and then their packet tracer diagram. So in the course, my students use the Cisco packet tracer for their logical design. A lot of them did. We don't have access to this in this course because you have to be part of Cisco's networking academy to get that, but this is something that if you are looking into getting networking, the Cisco packet tracer is a great way to learn how to design networks in your own physical, I would say not physical, but logical network where you're setting it up with the software on your computer. Anyway, let's go ahead and get into this. So the first thing they did for the proposal, they started off with a letter to the owner, talking a bit about what they're going to do and the mission statement behind the company. And then they go right into their network design, and let's go ahead and let's take a look at this. And let me actually zoom back in a bit. So based upon the design here, remember that for the dentist office, he wanted to have different software, different servers set up. He wanted to have his x-ray software. He wanted to have a patient management software. He wanted to have a computer in his office. He wanted to have a computer for his office manager. He also wanted to have a computer in each of the patient rooms and also a computer within the receptionist area. So let's go ahead and take a look and see how they satisfied this. The first thing we have is where everything comes in through the router, and they have an all-in-one router. So this is fine for a small business. You can use a Soho router instead of a separate router and a firewall. So this includes a router, a switch, and a firewall all in one, and it's all configurable. So they have this coming in, so we'll assume that this is a firewall, switch, and a router. This goes into a core switch over here, and this, you'll notice this connects to the receptionist computer, connects to the receptionist printer, connects to the x-ray computer in the x-ray room, connects to patient room number 2 here. It also connects to the dentist's main office, so here's this computer as well. And then we have this comes over into a second switch, and also off this main switch as well, we have this connecting to our patient room over here and our office manager. And then our second switch where we have this connects, this comes over here, and this is where we connect in all of our server equipment. So we have one server, we have a second server, and we have their backup. Now they're not listing which one is which, but I'm assuming one of them is the X-ray server and the other one is the application server for the patient management, or maybe a combination of both along with an application server and a backup server. So let's go ahead and let's go back down a little further in here. They have their legend talking about, just one all the way up through, it looks like, different, well, these are actually how many they purchased. So one of these different tower systems, 6 of these monitors and so forth, and the different cabling. And so this just is a legend of the devices and what they are. They also have their logical design here, which is this here. If you remember in the class, this is a class C. This is a private addressing, so this is non-routable. And then we go down further, they talk about the different IP addresses for everything within the network. They talk about their equipment, and so they talk about what the equipment is, they talk about the specs, and they talk about how they're going to use them. And that's all they included in this one. So you'll notice the difference between the first case study analysis that was submitted by a different group versus this one is that I didn't include the cost breakdown. This was an attached document. I didn't notice this at first, and I didn't include the packet tracer diagram. But the main aspect that we wanted to take a look at on here was really their physical network design. And they do meet all the requirements by doing this, by having their different servers set up in place for the different applications for the X-Way software, for the patient management software, and they are performing their backups. And then of course, all the different systems throughout the dental office. Now, one thing that I am assuming off here that I did not see in their design is that the dentist needed to provide by HIPAA requirements. And so one of these are going to have to be an application server where it's not an application server, sorry, but an authentication server where only the people on here can log in. So this is not a peer-to-peer design. Hopefully you see that this is a client server design. So we have our servers here, and they are managing everything. They're managing our authentication, they are managing our patient records, they are managing our X-ray records, and then everything else in here. These are all client systems. So if you have any questions about this design, let me know. This is one of the main things you want to focus on. If you want to do this on your own outside of this class, I recommend taking a look at this design and then also looking at what they purchased and what they put in. So thanks for watching. If you have any questions, let me know. If not, we'll go ahead and we'll see you at the next video.